Hello everybody, welcome to the course on graph algorithms. The first unit in this course, we're going to be talking about various algorithms to compute various sorts of decompositions of graphs. But to begin with, we're going to start with the very basics about what is a graph, what are they good for, and how do we sort of interpret them and draw them. So to start with, a graph is sort of an abstract idea, and it's an abstraction that sort of represents connections between objects. And graphs are useful both in computer science and elsewhere in the world because they can be used to describe many important phenomena. For example, the internet often can be thought of as a graph, where you've got various web pages and they're connected to each other by links. And this is sort of a very, very high-level view of the internet that sort of pays no attention to the content of a given page and other things like that. On the other hand, if you want to do something like Google's PageRank algorithm, makes sort of heavy use of sort of this very high-level view of the internet and connectivity within it. Another example is maps. You can think of maps as a graph, sort of where you have intersections that are connected by roads. And this is a view that would be very useful if you, say, wanted to plot a course between two locations. You need to find some, connection, some path along this map that gets you from one place to the other. Social networks can also be interpreted as graphs. You have people connected by friendships or following relationships or whatever, and this provides you another example of a graph structure. You can also sort of use more complicated things. If you have some sort of robot arm that can be in many possible configurations, what you could do is you could think of sort of the configurations are some of them are connected to each other by various motions. And then if you want to solve problems like how do I best reconfigure this robot arm from this position to this other position, you again want to sort of consider this graph relating these things to each other in order to figure out how best to do that. Okay, so these are the sorts of problems that we would like to be able to deal with using graph theory. So what is a graph? Well, the formal definition of an undirected graph, we'll talk about directed ones in a few lectures, is that it's a collection V of vertices and then a collection E of edges, each of which connects a pair of vertices to each other. So when you draw them on the paper, what you do is your vertices are usually drawn as points or circles or something, and the edges are lines or curves or something that connect pairs of these points. So, for example, the graph drawn on the screen has 4 vertices labeled A, B, C, and D, and it also has 4 edges, one between A and B, one between A and C, one between A and D, and one between C and D. And so, to make sure that we're all on the same page, if we drew the following graph below, how many edges does it have? Well, the graph here has 12 edges. You can sort of count them all, and sort of each of these segments between 2 of these points gives us an edge, and so there are 12 of them. Now, there's one thing that sort of fits into this definition of graphs that I gave that is a little bit weird, perhaps, or unusual. One thing that you might have is loops. This would be an edge that connects a vertex to itself. So here we just have the one vertex A and then a loop that connects A to itself. And there are some instances in which you might want to use this. Sometimes you actually do have, a traffic circle that just goes in a loop or something like that. But only sometimes is this sort of a thing worth talking about. Also, sometimes you can have multiple edges between the same pair of vertices. So in this picture, we have 2 vertices A and B and 2 edges between them. And somehow, if you're just talking about can I get from A to B, it doesn't matter if there's 1 edge or 2 between them. But sometimes having both of them is relevant. On the other hand, a lot of the time, these loops and multiple edges are just sort of a degeneracy that we don't really need to deal with. So oftentimes we work with what are known as simple graphs, which are graphs which don't have loops and don't have multiple edges. And so this is sort of the basics of what a graph is that we've just covered. Next time we're going to talk about a couple of things. Firstly, we're going to talk about how to represent graphs on a computer. And then we're going to talk a little bit about how we talk about runtimes for graph algorithms. So I hope this has been a useful introduction, and I'll see you at the next lecture when we talk about these other things. Hello everybody, welcome back to our graph algorithms course. Today we're going to be talking about how to represent graphs on a computer. And then after that, we're going to talk a little bit about how to talk about graph runtimes and sort of how it depends on what graph you're using. So the first thing is graph representation. So from last time, recall that a graph is a thing that consists of a bunch of vertices, sometimes called nodes, and also a bunch of edges that connect pairs of these vertices. And what we're going to want to do is we're going to want to do a lot of computations on graphs to determine various properties of them. But before we can get to any of that, we first need to talk about how to actually represent a graph inside a computer. And there are, in fact, several ways to do this, and exactly how we do it will affect the runtimes of some of these algorithms. So we're going to spend a little bit of time talking about that. So the first thing to do is, well, you want your vertices and you want your edges. A natural way to do this is just store a giant list of edges. Each edge is a pair of vertices, so this is sort of a big list of pairs of vertices. But now what we have is we've got these 4 vertices, A, B, C, and D, and then we just store a list. One is an edge between A and B, and then there's an edge between A and C, and there's an edge between A and D, and there's an edge between C and D. And this is a perfectly good way to store this graph on a computer. But there are other ways of thinking about it. One of them is the following. So at least if you have a simple graph, the only thing that really matters is which pairs of vertices have edges between them. And so if I give you a pair of vertices, sort of the only thing that you need to know is there an edge between them or is there not? So what we can do is we can just sort of build a lookup table for this. We build a matrix where you have an entry that's 1 if there is an edge between that pair of vertices and 0 if there's not. So for example, in this graph, there is an edge between A and D, and therefore the AD entry of this matrix is 1. There isn't an edge, however, between B and C, so the BC entry is 0. And so you just fill this in and you get this nice 4x4 matrix of zeros and ones. That is another way of representing this graph. On the other hand, there's sort of a third, maybe a hybrid way of looking at things. And the idea here is that for each vertex in the graph, it's going to have a bunch of neighbors. It's going to have other vertices that have edges from the one we're considering to them. And another way of representing the graph is for each vertex, we can just keep a list of its neighbors. So vertex A in this graph is adjacent to B, C, and D. B is adjacent to A. C is adjacent to A and D. D is adjacent to A and C. So for each of these vertices, we store a list of just all of its neighbors. And that's another way to represent the graph. Now, for example, just to be sure we're on the same page, if we have the following graph, what are the neighbors of vertex C? Well, we just draw all the edges that leave C, and it connects to A and B and D, and F and H and I. And those are its neighbors. Okay, so we have these 3 ways of representing a graph. And it turns out that different basic operations you want to perform could be faster or slower depending on which representation you have. For example, if you want to determine if there is an edge between a specific pair of vertices, this is very fast in the adjacency matrix representation. All you have to do is check the appropriate entry of the matrix, see if it's 0 or 1, and that's your answer. Constant time. However, when you have an edge list, the only thing you can really do is scan the entire list of edges to see if that particular edge shows up. That takes time proportional to the number of edges. For the adjacency list, it's a little bit faster than that. What you do is you pick one end of this edge that you're looking for and then look for all of its neighbors. If we want to know if A is adjacent to B, you look at the list of A's neighbors and see if B is on the list. And so the time there is proportional to the degree of the vertex, the number of neighbors that this one guy has. Now, another thing you might want to do is list all of the edges in a graph. And the adjacency matrix is terrible here because the only thing you do there is you scan through every entry of the matrix and each one gives you an edge. But that takes time proportional to the number of vertices squared. However, the edge list does this very easily. It just lists all the edges in order, which is what it does. O of E time. The adjacency list is about as good, though, because you just need to, for each vertex, you find all of its neighbors. Those are a bunch of edges. And you just do this for every vertex. And this actually counts each edge twice, because if there's an edge between A and B, you count both that A is a neighbor of B and that B is a neighbor of A. But it only counts them twice, so the time is still proportional to the number of edges. Finally, if you want to list all the neighbors of a given vertex, the adjacency matrix is pretty slow here, again, because the only thing you can really do is scan through that row of the matrix and find all the ones. Now, in the edge list representation, you have to scan through all the edges in your graph to see which ones include the vertex you want. Whereas the adjacency list, you just scan through the list of neighbors of the vertex, and it's very fast. Now, it turns out that for many problems that we'll be considering this on and throughout most of the rest of this unit, what we'll really want is the adjacency list representation of our graph. Just because a lot of the operations that we need, we really want to be able to find neighbors of a given vertex. Okay, so that's how you represent graphs. Let's spend a little bit of time to talk about runtimes of graph algorithms. So when we talk about algorithm runtimes, it's generally a function of sort of the size of the input. And for most of the algorithms we've seen so far, the input sort of has one size parameter, n. And so you have runtimes like O of n squared or O of n cubed or something to that effect. However, graph algorithms, well, the graph sort of has two measures of its size, the number of vertices and the number of edges. And so the graph algorithm's runtimes depend in some way on both of these quantities. You could have runtimes like O of size of v plus size of e, which is generally considered to be linear time. But you could also have O of size of v times size of e, or size of v to the 3/2, or v log v plus e. And there are many different possibilities for types of runtimes that we have. And an interesting question, though, is, again, if you sort of only have one parameter, it's easy to compare n log n runtime versus n squared versus n cubed. But if you want to say which one's faster, say one algorithm runs in time size of v to the 3/2, and the other one runs in time size of e, it's not actually clear which one's faster. And in fact, which algorithm is faster actually depends on which graph you're using. In particular, it depends on the density, how many edges you have in terms of the number of vertices. If you have many, many, many edges, O of e is going to be worse. However, if you have few edges, it's going to be better. And in terms of density, there's sort of two extremes to consider. On the one hand, you have dense graphs. Here, the number of edges is roughly proportional to the square of the number of vertices, meaning that like almost every pair of vertices, or some large fraction of the pairs of vertices, actually have edges between them. If you're a band and you're going on tour and want to like plot a route between a bunch of cities, well, there is actually some transportation option that will get you between basically any pair of cities on the map. Now, it might be indirect or take a while, but you should still probably plot all of these out in order to plan your tour. Just what will matter is not whether or not it's possible to get between two cities, but sort of how hard it is to get between these cities. But for this time, you actually want sort of a dense graph that talks about sort of all pairs relations between these vertices. On the other end of the spectrum, we have sparse graphs. Here, the number of edges is small relative to the number of vertices, often as small as roughly equal to the number of vertices, or some small constant times the number of vertices. And in a sparse graph, what you have instead is that each vertex has only a few edges coming out of it. And this is actually very reasonable for a lot of models you want to think about. If you think of the internet as a graph, well, there are billions of web pages on the internet, but any given web page is only going to have links to a few dozen others. And so the degree of any given vertex, the number of neighbors that any given vertex has, is much smaller than the total number of vertices. So you end up with a very sparse graph. And a lot of things like this, like the internet, like social networks, like actual maps that you've drawn on a piece of paper, these tend to be sparse graphs. But whether or not your graph is sparse or dense will affect the runtime of your algorithms and may even help determine which algorithms you want to be running. Okay, so that's it for today. Next time, now that sort of the basics are out of the way, we're going to actually talk about some algorithms. In particular, we're going to talk about how to explore graphs and sort of figure out which vertices can be reached from which others. So come back next time and we'll talk about that. Hello everybody, welcome back to the Graph Algorithms course. Today we're going to talk about algorithms for exploring graphs. In particular, sort of ways to tell us sort of which vertices can be reached from which others. So, for an example of sort of the type of problem we're trying to solve here, suppose that you're playing a video game and you found the exit to some level, but you don't want to go there just yet. You want to first sort of explore this whole level, make sure you found all the secrets inside it, make sure you get all the loot and XP that there is to be found. And you can certainly wander around between the various rooms and find a bunch of passageways and so on. And you've been wandering around for a while and maybe haven't discovered anything new yet, but you'd like to make sure that you've really found everything before you leave. How do you accomplish this? How do you make sure that you found everything? And this sort of is a notion of exploring a graph. I mean, you've got these rooms, they're connected by passageways, and you want to make sure that everything, at least everything that's reachable from where you started, you can actually get to it and explore the entire region. And this is actually this and sort of related questions are actually very useful in a number of applications. For example, if you have a map and you want to find a route between, some location on the map and some other, it often depends on this sort of exploration of the graph, making sure that you can find some sequence of roads to follow to get you where you want to go. This could also be used if you're sort of building a road system and want to ensure that the entire thing is connected. You need to have some sort of algorithm to tell what can be reached from what. And finally, it has sort of more recreational things, the video game example, but also like if you want to solve a maze, this is very much can I get from the start to the finish in this sort of graph that connects things. But also various puzzles, if you think of sort of vertices as sort of possible configurations and then edges that describe moves that you can make and want to say, can I rearrange the puzzle to end up in this location? Again, this sort of exploration algorithm becomes very important. So before we get into this too much, we really want to formalize what we mean. In particular, we want to know what does it mean to be reachable from a given vertex. And basically the idea is you start at the vertex and you're allowed to follow edges of the graph and you want to be able to see what you can end up at. And so to formalize this, we define a path in a graph G to be a sequence of vertices, v0, v1, v2, etc., such that each vertex is connected to the next one by an edge of the graph. So we get some sequence of edges to follow. So the formal description of the problem that we would like to solve is, given a graph G and a vertex S in G, we'd like to find the collection of all vertices V in the graph such that there is a path from S to V, everything that we can reach from S. So just to get a little bit of practice, if we have the following graph, which vertices here are reachable from A? Well, think about it a little bit, and you find out that A, C, D, F, H, and I are all reachable. And it's easy to see that these vertices sort of do all connect up from edges, but you then can't get to B, E, G, or J. And this is sort of because there are no edges that connect any of these vertices we can reach to any of these other vertices. And so there's no way to escape except for these 6. And this is sort of the actual idea behind the algorithm. What you want to do is you want to make sure that you can actually find everything that you can reach. And so what you do is you sort of expand. You find a bunch of vertices. These are a bunch that I can reach. But then if there are any edges that connect ones that you can reach to ones that you can't reach so far, well, you have to sort of explore those edges and find the new vertices on the other end and sort of add them to the list that you know about. And you sort of keep expanding this list of vertices that you can get to until you can't connect to anything new, and then you're done. So to formalize this algorithm a little bit, we're going to keep a list of discovered nodes. And this starts out just with the vertex S that you're supposed to start at. But then what you do is, while there is an edge E that leaves this set of discovered nodes, it connects something you have discovered to something that you haven't discovered. Then what you do is you take the vertex at the other end of that edge and add it to your list of discovered nodes. And you just keep doing this until there's nothing new to be found. And then you return this list of discovered nodes. Okay, that's a reasonable algorithm and it does work. But in order to really code this up, you need to do some work to handle the bookkeeping that's required for this algorithm. You need to do things like you need to keep track of which vertices you've discovered and which edges you've dealt with, which edges you've actually checked and which ones you haven't. You also need to know sort of what order to explore new edges in. If there are several possible edges to follow, which one do you follow next? And so, what we're going to do now is we're going to talk about a specific way to implement this and deal with these sort of bookkeeping issues. The first thing that we need to do is we need to keep track of which vertices we've already found. And for this, we're going to associate a Boolean variable to each vertex, visited of v, which basically tells us, have we visited it yet? The next thing that we're going to need to do is we're going to need to, most of the vertices that we visited will have already sort of checked all of the edges relating to them. But some we haven't, and we somewhere need to keep track of a list of vertices that still have edges hanging off of them that might connect us to something new. Now, this list isn't going to appear explicitly in our program. It'll actually sort of be hidden in the program stack. So this is at points a little bit subtle, and we'll sort of see it once we introduce the algorithm. The final thing is we need to discover which order to follow new edges in. And for this, we're going to use what's known as the depth first order. What this means is we're just sort of going to start at our initial vertex, and we're going to start following a chain of edges. We're just going to follow some really long path forward until one of two things happens. One thing is we could stumble across a vertex that we've already seen before, in which case there's no reason to have followed that edge. We'll just back up to where we were before. The second thing that could happen, though, is we hit a dead end. And when we actually hit a dead end and can't go any further forward, then we actually back up. And then once we backed up, though, we don't just back all the way to the beginning. We just back up one step and then try going forwards again from that new vertex that we've found. Okay, so that's the basic idea. How do we implement this? Well, part of the beauty about this is that we have a very simple recursive algorithm. So, explore of v. The first thing you do is you set the visited marker of v to be true. We say we have visited it. Next, for each neighbor w of v, for each w that's adjacent to v, if w has not already been visited, we recursively explore w. Okay, so this is a very compact program. Let's sort of actually see what it does on an example. Oh, right. Also, I should mention that in order for this program to execute reasonably efficiently, we really want an adjacency list representation of our graph. That's because we have this for loop where we want to iterate over all of the neighbors of v in our graph. And for that, if you have an adjacency list, which gives you a list of all the neighbors of v, that's incredibly easy to do. If you don't have an adjacency list, on the other hand, this algorithm really isn't that efficient. Okay, fine. So let's look at an example. Here's a graph. We're going to start by exploring that vertex. So we mark it as visited. We then check for unvisited neighbors. And hey, look, there is one. So we recursively explore that other vertex. We mark it as visited. We search for unvisited neighbors. And we have this one. So remember, now we're sort of 3 layers into the program stack here. This is sort of a subroutine of a subroutine. But now when we're exploring this vertex, it has no unvisited neighbors. So after we've done a little bit of checking, we decide that we're done exploring this guy, and we pop the stack. This other guy still, we visited both of its neighbors. We popped the stack back to the original explore call. Now, this vertex does have some unvisited neighbors left, so let's visit one of them and explore that. Mark it as visited, find an unexplored neighbor, explore that. Mark as visited, unexplored neighbor, mark as visited, unexplored neighbor. Now when we explore this vertex, though, once again, we're stuck. So we wrap up exploring that guy, pop a level up the stack, go back to exploring this other vertex, who now actually does have another unvisited neighbor, so we're going to go visit that one. Now we've actually visited everything in the graph. So all we're going to do is, at each vertex, we're going to note that all of their neighbors have been visited. We're going to pop up the stack and get back to where we started and conclude. So here we actually have found all these vertices. And in fact, if you look at it, we've actually figured out how to reach them all. If you look at sort of these darker edges, which are the ones that our algorithm sort of actually followed when we ran it, these sort of connect up to all the other vertices. And they actually tell us, if you sort of follow these edges, they give you a unique path to any other vertex that we can reach. Okay, so that's our algorithm. Let's talk about correctness. And the theorem is that if all the vertices in our graph start as unvisited, when we run explore v, it marks as visited exactly the vertices that are reachable from V. And the proof here isn't so bad. The first thing to note is that we only ever explore things that are reachable from V. And that's because, well, the way our recursive calls work are we either start at V or we explore a neighbor of a vertex that we've already explored. So any vertex that we end up exploring, it has to be a neighbor of 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 the original vertex or something. But that does basically give us a path and say that whatever we got to was reachable. The next thing to note is that a vertex W is not marked as visited unless it has already been explored, which is just the only way we mark things as visited is when we explore them. But finally, we should note that if W gets explored, well, we then look at all the neighbors of W, and either those neighbors have already been visited, in which case it means they've been explored at some point, or we end up exploring them. So in other words, if W gets explored, all of its neighbors also get explored. So to finish things, suppose that we have some vertex U that is reachable from V. That means that we've got a path from V going up to U. And if we actually explored everything along this path, we'd be done, because we would have explored U at some point. So let's assume that we don't. Assume that W is actually the furthest thing along this path that we've explored. However, by what we had on the previous slide, if you explore a vertex, you also explore all of its neighbors. So the next vertex Z along this path must also be explored. And so this is a contradiction. This says the only way this can work is if we've actually explored every vertex along the path, but that means we've explored U, which is good. Okay, so this explore algorithm is actually really great if we just want to find the vertices that are reachable from a given one. But sometimes you want to do a little bit more. You actually want to find all the vertices of the graph G, not just those coming from a given one. So for this, we're going to use a slightly more complicated algorithm called depth-first search. And for this, what we do is the following. First, we mark everything as unvisited. Then, for each vertex in the graph, if it has not yet been visited, we explore that vertex. So to look at an example on this graph, we find an unvisited vertex, say that one, and we explore it. So we find a neighbor and another neighbor, and then we pop back up the stack and then find something adjacent to our original vertex and come back. And now we're done exploring that first vertex. So now we look for a new vertex we've never visited before, like say that one. We explore its neighbor, come back. We're done exploring that guy. We find a new vertex that we haven't visited, that one. We explore its neighbor and his neighbor, and then come back. And now that we've actually visited all the vertices, only now do we sort of wrap up and conclude our algorithm. So to analyze the runtime of this algorithm, we have to note a few things. Firstly, whenever we explore a vertex, we immediately mark it as being visited. That's the first thing that we do. The next thing to note is that no vertex ever gets explored if it's already been visited. In fact, if you look at every time we make an explore as even a recursive call, then we always first check if it has not been visited, then we explore it. And this means that no vertex gets explored more than once. In fact, this means that each vertex gets explored exactly once, because the outer loop in the DFS explores every vertex if it hasn't already been visited. So, but each vertex in our graph gets explored exactly once. But for each vertex, when we explore it, there's this inner loop where we have to check all neighbors of that vertex. And so we have to do work for each neighbor of each vertex. And so we have to do work proportional to the total number of neighbors over all vertices. And that's proportional to the number of edges. Because each edge connecting A and B says that A is a neighbor of B and that B is a neighbor of A, so it contributes to sort of two neighbors. But the total amount of work is still O of the number of edges. So the total work, we do O of 1 work per vertex and O of 1 work per edge. And the total runtime is O of size of V plus size of E, a nice linear time algorithm. So that is depth-first search. Next time we're going to talk a little bit more about reachability in graphs and give some more applications of this algorithm. So I'll see you then. Hello everybody, welcome back to the Graph Algorithms course. Today we're going to be talking about notions of connectivity in a graph. In particular, talk about connected components and how to compute the connected components of an undirected graph. So, to begin with, last time we talked about this notion of reachability. What does it mean to be able to reach another vertex from a given one? And what we'd like to understand now is really what sort of classifies reachability in a graph. We really, not just from a single vertex, we sort of want to understand which vertices are reachable from which others. And it turns out that for an undirected graph, there's actually a very clean categorization of this. In particular, for any graph G, we can always partition it into connected components, such that two vertices V and W are reachable from each other, if and only if they're in the same connected component. So sort of we break this graph up into islands where any two islands are completely unconnected from each other, but within any island you can get from anywhere to anywhere else. So just to make sure we're on the same page, if we have the following graph, how many connected components does it have? Well, this graph is going to have 4. Sort of if you look at these 4 things, from each of these things they're all connected up, but there are no edges between any pair. Okay, so let's see how the proof of this theorem works. Why can we always divide it into connected components? And basically the idea is you need to show that reachability is an equivalence relation. That means 3 things. Firstly, that V is reachable from V, which is easy. Also that if V can be reached from W, W can be reached from V, which sort of is just following the path in the opposite direction. And then there's the difficult one, that if V is reachable from U, and V is also reachable from W, then W is reachable from U. What this says, if you sort of take V and you take everything that it connects to, in fact, everything in that whole region connects to everything else in that whole region. And that last step is not so hard once you write it down. The point is that you can reach U from V, which means there's a path from V to U. You can also find a path from V to W. And if you just sort of glue these paths together at V, then you have a path from U to W. So they can be reached from each other. Okay, so that completes the proof, but what we'd now like to do is do this algorithmically. Given a graph G, we'd like to find the connected components of this graph. Okay, fair enough. Let's find an algorithm. Well, the basic idea of this is pretty simple. If you run explore of V, this finds the connected component of V. It finds everything you can reach from V, that's the whole connected component, and you just need to repeat this to find all the other components. And it turns out you can do this actually with only sort of a slight modification to the original depth-first search algorithm that we saw. Now, in order to make this algorithm we're about to see a little bit more cleanly, we're going to modify our goal a little bit. Instead of actually sort of returning sets of vertices that are our connected components, what we're going to do is we're going to label the connected components. We're going to give everything in the first one a label of 1, and everyone in the second component a label of 2, and so on and so forth. Okay, so how does this work? Firstly, we modify our explore procedure. We visit the vertex. We also make sure to, visit all of its neighbors, but we also assign the vertex a number corresponding to its connected component, this CC number. Now, the thing is that this variable CC is not going to change as we make these recursive calls to explore, and so everything else that gets found in sort of the same explore will all get assigned the same number. However, when we actually run our depth-first search, we're going to, between different explorers, between different vertices that we explore and then go off to find a new vertex, we increment this number. And so the second explore that we do, everything gets a number 1 bigger. So to see how this actually works, on this graph our counter starts at 1. We find an unvisited vertex, say that one, it gets labeled with a 1. We keep exploring from that vertex and we find these other 3. All of them get labeled with 1. But now we're done exploring that first vertex, so we increment the counter and find a new unexplored vertex. So say that one, which we now label 2. We keep exploring and the other vertex that we found also gets labeled with a 2. But then we finish that explore call. We now increment our counter to 3 and find a new vertex, this one. We explore that and everything we find gets labeled with a 3. And now we're done. We've got 3 connected components. Everything in the first one is labeled 1. Everything in the second one is labeled 2. And everything in the third one is labeled 3, which is sort of what we wanted. Okay, to show that this is correct, we note that each new Explorer call finds a full new connected component because it finds everything connected to that V. And of course, because V had not been found yet, it was not in a connected component that we'd already seen. Secondly, because of the way this outer loop in depth first search works, every vertex eventually gets found, because every vertex we eventually check to see if it's been visited, and if not, we explore it. Now, the runtime of this is basically just the runtime of depth first search. We only made sort of cosmetic modifications to it. So the runtime is still O of size of V plus size of V. Okay, so that's our discussion of how to compute connected components. Next time, we're going to talk about some other applications of depth first search. So I'll be happy to see you in the next lecture. Hello, everybody. Welcome back to the Graph Algorithms course. Today, we're going to talk about pre-visit and post-visit orderings. And these are sort of some numbers that you can do when running a depth first search that sort of records some information about the order in which you visited vertices. And we're going to discuss a little bit about why these numbers might be important, but mostly it's going to be that they will turn out to be very useful in some algorithms we're going to discuss later. Okay, so let's talk about depth first search, which is an algorithm that we came up with last time. And it's a little bit weird as an algorithm. Because, well, what happens when you run depth first search? It doesn't return anything. It does modify the state of some things. It marks vertices as visited or unvisited. But in the end, it just ends up marking every vertex as being visited. If all that you wanted to do was mark every vertex as visited, there are easier ways to do it. On the other hand, like the order in which we sort of find these vertices in sort of a way that involves their connectivity is actually very useful. For example, with slight modifications, keeping track of a little bit of data, we saw how to use depth first search to compute connected components. So in general, if we want to make depth first search useful, we need to keep track of some extra information about its execution. So what we're going to do for this is we're going to augment some of its functions in order to store additional information. So for example, let's look at Explore. What we're going to do is we're going to mark the vertex V as visited. But then before we do anything else, we're going to run some pre-visit function. This is just some extra things that we're doing to sort of maybe record some information or do a little bit of extra work, sort of just as we found this new vertex. Then we go through this loop over neighbors and exploring all the unexplored neighbors. And then right before we're about to finish exploring V, we run some other post-visit blocks, some thing that we do it right before we're finishing up. Okay, so what are these functions going to be? They could be a number of things. We'll come up with an example shortly. But the idea is to augment our functions a little bit to keep track of some extra information. So what sort of extra information do we want? Well, one thing we might want to do is to keep track of sort of what order we visit vertices in. And so one way to do this is we sort of have a clock. This clock keeps track of time. It ticks forward once every time we hit a pre-visit or a post-visit for a vertex. Every time we discover a new vertex for the first time or sort of leave an old vertex for the last time. And every time we do one of these things, we'll also record the time at which that happens. So for each vertex V, we'll have a record of the pre-visit time and the post-visit time. So to see what I mean by this, let's look again at this example. The clock starts at 1. We visit our first vertex. It gets its pre-visit number assigned as 1. From there, we explore the second vertex, which is pre-visit 2, and then the third vertex, which gets pre-visit of 3. From there, we're done exploring that vertex. All of its neighbors have already been visited, so we assign it post-visit 4 and move on. This other vertex gets post-visit 5. We now have a new vertex to explore. It gets pre-visit 6 and post-visit 7. And our original guy gets post-visit 8. And that wraps up our first explore. We now find a new vertex who gets pre-visit 9 and his neighbor pre-visit 10. And then they get post-visit numbers 11 and 12. Finally, we've got a new guy with pre-visit 13. And his neighbors get 14 and 15. And then they get post-visit 16, 17, and 18 as we wrap them up. And we're now done. We've just assigned the numbers 1 through 18 as the pre-visit and post-visit numbers of these 9 different vertices. So the way we compute these is actually pretty easy. We just have to initialize our clock to be 1 at the beginning of our depth first search. And then in the pre-visit block of our explore, we set the pre-visit number of v to be this clock value and increment the clock. And for the post-visit block, we set the post-visit number of the vertex to be the clock value and increment the clock. Very easy, doesn't really change the runtime of anything, but allows us to compute these numbers. Now, what are these useful for? Well, really the pre-visit and post-visit numbers, they tell us something about the execution of the depth-first search. And we'll see a little bit of this as we prove the following lemma. So suppose that you have any two vertices u and v. From these you get intervals, pre of u to post of u, and then pre of v to post of v. These are two intervals, and the claim is that these intervals are either nested or disjoint. And in particular, whether they are nested or disjoint will actually tell us something useful about the sort of way in which the depth-first search ran on these two vertices. So let's take a look at what we mean by this. If you have two intervals, there are a few ways in which they could intersect with each other. Firstly, it could be the case that one interval is strictly contained in the other one. This means that they're nested. It could also be that they're disjoint from each other, that they don't overlap at all. Finally, we could have two intervals that are interleaved. They sort of overlap over part of their ends, but not over the entire interval of either side. And what we're saying in this lemma is that the interleaved case is actually not possible. Okay, so let's see the proof. We first assume that without loss of generality, the first visit to u happens before the first visit to v. We now have two cases to consider. Firstly, it could be that we find v for the first time in the midst of exploring u. And this sort of means that in the depth-first search tree that we produced by this exploration, we found v as a descendant of u. We sort of found v while exploring u. The second thing is we could find v after we're done exploring u. So sort of v and u are on different branches of the tree. They're cousins of each other. Okay, so let's look at the first case. If we explore v while we're in the middle of exploring u, then explore v is actually being run as a subroutine of explore u. And because of the way subroutines work, we can't finish exploring u until we're finished exploring v. And therefore the post of u is bigger than the post of v, and these two intervals are nested. In the second case, we explore v after we're done exploring u. So we start exploring u, and then we finish exploring u. And then sometime later, we start exploring v and then finish exploring v. And so these intervals are going to be disjoint. And so these are the only cases. The intervals are nested or they're disjoint. And which case we're in will actually tell us something useful about the order in which we visited vertices in this graph. Now, just to review, we've got these two tables here of sort of pre and post numbers, but only one of them is a possibly valid table of pre and post numbers. Which one is not valid? Well, the one on the right can't be correct because these two intervals from pre to post for vertices A and B are interleaved, and that can't happen. Okay, so that's sort of pre and post orders. We'll see a lot more usefulness later, but in the next lecture, we're going to introduce something a little bit more new. We've been talking a lot about undirected graphs. Here we're going to be talking about what happens when the edges actually have an orientation to them. So please come back next time and we can talk about that. Hello everybody, welcome back to the Graph Algorithms course. Today we're going to start talking about directed graphs versus undirected. In particular, talk about directed acyclic graphs and some of their properties. So what's the motivation for this? The point is that sometimes we want to talk about the edges of a graph that have a direction. This is just because, sometimes like pairs of things are related in a way, but the relation isn't symmetric. One of them comes before the other, or it's sort of a one-way viewership or something like that. And so we define a directed graph to be a graph where each edge has sort of a designated start end and an end end. So what are examples where we might want to use this? For example, if you've got a city map where lots of your streets are one-way roads, the direction that the roads point in is actually very relevant if you want to navigate the city. You can't just follow any series of roads you like because you'll be driving down some one-way streets in the wrong order. So you really do need to keep track of this orientation if you want to navigate the city. But I mean, also some of the examples that we gave. Links between web pages. The web graph is probably a directed graph, because usually if you've got two web pages and A links to B, B probably doesn't link back to A. Similarly, if you have followers on a social network, it depends on the social network. I mean, in Facebook, friendships are symmetric, so they're sort of two-directional. That might be an undirected graph. But on lots of them, you can follow somebody without them following you, and so then you end up with wanting to have a directed relation for when someone's following someone else. A final example that we'll look at in some more detail today are sort of dependencies between tasks. So we have this directed graph, and we've already built up a lot of this theory that works for undirected graphs with the sort of Explorer and DFS algorithms. But most of this sort of actually still holds for directed graphs. We can still run DFS on a directed graph. The slight modification now is that when we run our explorers, we only want to check for directed edges out of V. So when we say for all neighbors W of V, if W has not been visited, etc., we really want to say neighbors where V points to W, not the other way around. And what this will do is it means that when we explore V, we find things that are actually reachable from V using the edges in the direction that they're intended. So we're only sort of allowed to follow these one-way roads in their appropriate direction. Now, using this new depth first search, we can still compute pre- and post-orderings. They still have many of the same properties. The algorithm for DFS still runs in linear time. Basically, everything's the same. The context is now a little bit more general. Okay, so let's look at a sort of specific example where directed graphs are important. In particular, suppose that we have the following morning routine. We've got to do a bunch of things every morning. We need to wake up, we need to get dressed, we need to eat breakfast, we need to go to work, we need to shower, all of these things. But we need to do these things in some order, but we can't do them in any old order because, well, we need to wake up before we get showered, and we need to dress before we go to work, and we need to eat breakfast before we go to work, and all of this stuff. And one way of representing these sorts of dependencies is by a directed graph. If we need to do A before we can do B, then we draw a directed edge from A pointing to B. And so this gives us some sort of dependency relation. And it's not just these sort of trivial examples of, how do I get dressed in the morning, but if you've got some sort of complicated system of libraries where some of them require other ones in order to work, you can end up with some sort of similar graph of dependencies, which you actually do need similar techniques to handle. Okay, so what do we do when we have these dependencies? Well, one of the things that we'd like to do is we'd like to find an ordering of the tasks in a way that respects these dependencies. We'd like to wake up before fine. For example, suppose that we woke up at 7 o'clock and then showered at 7:05, got dressed at 7:15, had breakfast at 7:20, and went to work at 7:30. This puts all of our events in some order, and you'll note that this order respects all of our dependencies. We wake up before we shower, before we get dressed, before we go to work, and we eat breakfast before we go to work, and everything works out nicely. And so if we have one of these dependency graphs, we'd like to linearly order the vertices to respect these dependencies. Now, one thing to ask is it always possible to do this? And it turns out the answer is no. The sort of best counterexample is this following chicken and egg problem. I mean, the point is that you need a chicken in order to lay eggs, and you need eggs to hatch chickens. And so you can't put them in some order where one of them comes first. If you put chickens first, then you've got this pointer from eggs back to chickens going in the wrong direction. If you put eggs first, there's this pointer from chickens back to eggs in the wrong direction. Without some place to have gotten started, there's sort of no way you can get this ordering going. In fact, in general, there's a slightly more complicated way in which this can fail to happen. In fact, if your graph has any cycle, a cycle here is a sequence of vertices, v1, v2 to vn, such that each one connects to the next using a directed edge. So you've got a bunch of vertices arranged in a circle such that each one connects to the next one all the way around. And the theorem is that if G contains a cycle, it cannot be linearly ordered. Okay, so just to make fine. Let's take a look at the proof here. So suppose that our graph has a cycle, v1 through vn, everything connected up in order. And suppose that additionally we can linearly order this graph. Well, if you linearly order these things, there are finitely many. Some one of them needs to come first. So suppose that vk comes first in this order. But now we're putting vk before vk minus 1. And vk minus 1 points to it. So we have an arrow pointing in the wrong direction, which gives us a contradiction. So if we have a cycle, we cannot be linearly ordered. So what this means is that in order to be linearly orderable, you need to be what's known as a directed acyclic graph, or a DAG. And this is just a name for a directed graph that has no cycles. Fair enough. Now, by the above theorem, it is necessary to be a DAG in order to linearly order. But one question we should ask ourselves, perhaps, is it sufficient? Can we necessarily linearly order it if it's a DAG? Well, okay, this is a question to ask a little bit later, but for now, let's just review. We have the following 4 graphs. Note that the edges here are sort of the same except for their orientations. And which ones of these graphs, or which one of these graphs, is a DAG? Well, it turns out that only A is. B has the cycle noted in red, and C has this other cycle noted in red. But if you work out A, you can actually see that it does not have any cycles to it. Okay, but the question that we were posing was, is it the case that any DAG can be linearly ordered? And the theorem that we'll actually show is that yes, if you have any directed acyclic graph, you can linearly order it. And next time what we're going to do is we're going to prove this theorem. But not just that. In addition to proving this theorem, we're actually going to make it algorithmic. We're going to come up with an algorithm that, given a DAG, actually produces this linear ordering. So that's what you have to look forward to next time, and I'll see you then. Hello everybody, welcome back. Today we're going to be talking about the algorithm for topological sort. And we're going to talk about this. We're going to show, in fact, that any DAG can be linearly ordered, and we're going to show you how to do it. So remember from last time, we were talking about directed graphs, and in particular, we wanted to be able to linearly order the vertices of this graph such that every edge pointed from a vertex with smaller index under this linear ordering to something that's larger. Now, we noted that in order for this to be possible, our graph needed to have no cycles. It needed to be a DAG. And today we're going to show that this is actually sufficient. So one way to look at this is if you have this linear ordering, let's think about which vertex comes last in this order. Well, if it comes last, it can have edges pointing to it, but it can have no edges pointing out of it. And so this gives us a motivation for a useful definition. We say that a source is a vertex in a graph that has no incoming edges. So a source can have as many edges as it likes going outwards, but it can't have any coming inwards. Similarly, a sink is a vertex with no outgoing edges. It can have a bajillion edges coming into it, but nothing can escape. So, to be clear that we're on the same page, the following graph has 9 vertices. How many of them are sinks? Well, the following highlighted 3 vertices are sinks. They each have no edges coming out, but every other vertex in the graph does have a few, or at least one edge leaving it. Okay, so here's the basic idea for how we're going to produce our linear order. We're going to first find a sink in the graph. There needs to be a sink because there needs to be something at the end of the order. And when we have a sink, though, we're perfectly fine putting it at the end of our ordering. And the reason for this is, well, I mean, it's got edges that point into it, but as long as the vertex comes at the end, everything pointing to it is coming from before it. So once we put it at the end of the order, it's sort of dealt with, and we just need to order the rest of the graph. So what we do is remove that vertex from the graph and repeat this process. So to see what this means, we have this graph on 5 vertices. D is a sink, so we put it at the end of our ordering and remove from the graph. Now we find another sink, say C. Put it at the end, remove from the graph. E is next, goes at the end, then B, then A. And finally, we have this ordering, A, B, E, C, D. And this, it turns out, is consistent with the ordering that we had on our original graph. Now, this is all well and good, but it depends on us being able to find a sink. And before we even ask that, we should ask, how do we even know that there is a sink in our graph? And it turns out that for DAGs at least, there's an easy way to show that there is. And the idea is the following. What we're going to do is we're going to start at some vertex v1, and we're just going to follow a path. We're going to follow directed edges forward and just keep going, finding vertices v2, v3, v4, etc., and just keep going. Now, eventually one of two things will happen. Either we could hit a dead end. We could end up at some vertex with just no outgoing edges. We just can't extend this path anymore. And if that's the case, we've found a sink. We've found a vertex with no outgoing edges. The second possibility, though, is that maybe this path just keeps going forever. But if it does, since there are only finitely many vertices in our graph, eventually we'll have to repeat something. We'll have to find a vertex for the second time. But when we do that, it means that there was a path that started at that vertex, went forward a bunch, and eventually came back to itself. That means we have a cycle. And so, at least if we're a DAG, that can't ever happen. Okay, so let's take a look at the algorithm. What we're going to do is, while G is non-empty, we're going to follow a path until we can't extend it any further. That vertex at the end is going to be a sink, which we'll call V. We take V and put it at the very, very end of our ordering, and then remove it from the graph, and then we just repeat this. So, on this graph here, well, we start at A, we follow a path A, B, C, D. Now we're stuck. D is a sink, so we can remove it from the graph. We now follow a new path, A, B, C. C is a sink, we remove it from the graph. A and E. E is a sink, we remove it. Path A, B. B is a sink, we remove it. A is already a sink, and so we remove it, and now we're done. We have our order. Now, what's the runtime of this algorithm? We need to compute one path for each vertex in the graph, so O of V many paths. And each path could be pretty long. It could include up to all the vertices in the graph. It could take O of V time. So the final runtime of this algorithm is O of V squared, which is not great. On the other hand, we're doing something a little bit inefficient with this algorithm. We started at this vertex. We followed this huge long path until we found a sink, and then we removed it from the graph. Then what we probably did was we started at that same vertex again, followed basically the same path until we got almost to the very end, until we get to right before that vertex that we removed. And we're sort of repeating all of this work. Why do we need to follow this whole path again? We could just back up one step along the path and then keep going from there. And so that's what we're going to do. Instead of retracing our entire path, we're just going to back up one step along our path. So to see what this does in this example, we go A, B, C, D. D is a sink, which we can remove. But now instead of starting back at A, we start at C, which is already a sink, and B, which is already a sink. Now at A, we have to follow the path to E to find the next sink, and then we're done. And this algorithm reuses our steps a lot less, and so it's a lot more efficient. In fact, if you think about what this algorithm does, it's basically just a depth-first search. We're starting at a vertex, we're following a path forward until we can't anymore. And then finally, once we're stuck, we turn around and we sort of stop using that vertex again. Then from that one step previous, we just keep going forward again. This is exactly the depth-first search ordering. And in particular, whenever we finish the post-visit block at a vertex, we put it at the end of our ordering. So the order in which we're sorting our vertices is just based on the post order. In particular, vertices with small post order go at the end of our ordering, and ones with large post order go at the beginning. So the algorithm is now super easy. We run depth-first search on the graph, and then we sort the vertices based on the reverse post order. And note, we really don't actually have to do any sorting here. We just have to remember the order in which we left our vertices. Okay, so that's our algorithm. Let's take a look at the correctness. So basically what we're saying is that if we've got G as a DAG, then we want to say we can order them by the reverse post order. Now, for this to be consistent with our graph ordering, it needs to be the case that whenever we have an edge from U to V, U comes before V, which means that the post of U is bigger than the post of V. Okay, let's prove this. There are three cases to consider. Firstly, we could explore U before we explore V. Next, we could explore V while we're exploring U. And finally, we could explore V after we're done exploring U. Of course, this last case can't happen since there's an edge from U to V, which means that if we haven't already visited V, we will visit it as part of our exploration of U. But okay, the first two cases are still possibilities. Let's take a look. Firstly, if we explore V before we explore U, well, it turns out that we can't reach U from V. And this is because we have a DAG. If there was a path from V to U, and then we add in the edge from U back to V, that would give us a cycle, which we can't have. So it must be the case, therefore, that since we can't discover U as part of exploring V, we have to finish exploring V before we can even start exploring U. And that tells us that the post of U is bigger than the post of V, which is what we wanted to show in this case. Now, in the second case, the analysis is a little bit different. If we explore V while exploring U, remember that this means that our explorer of V is a subroutine of exploring U, and therefore it needs to finish up first. And that again tells us that the post of U is bigger than the post of V. So that completes the proof of our theorem and shows that this algorithm for topological sort actually works. So we've got now this nice algorithm for this sorting. Next time we're going to talk about something a little bit different. We're going to talk about connectivity in digraphs. So I'll see you then. Hello everybody, welcome back to our graph algorithms course. Today we're going to be talking about notions of connectivity in directed graphs, which it turns out will be a little bit more complicated than those in the undirected case. And we'll talk about various notions, then get to this idea of a strongly connected component. So in undirected graphs, connectivity is a pretty simple notion. We have these connected components where any two things in the same component you can get from one to the other. And if you've got two different components, they've got no edges between them. Nothing connects at all. In directed graphs, the story is a bit more complicated. So let's consider the following example graph. Now, in one sense, this graph is connected. You can't separate it out into two islands such that you can't reach one island from the other. On the other hand, if you want to look at which vertices can be reached from which others, the story is a bit more complicated than that. From vertex D, it turns out you can reach every other vertex in this graph. However, D is a source vertex. Once you leave D, there is no way to get back to it. There are just no edges that come into it. Now, edge is sort of, F is sort of the opposite here. From every vertex in the graph, you can reach F, but once again, once you do, you can't get back. Then again, G and A, neither of them can be reached from each other. H and I, you can get between them, but once you leave again, you can't get back. It's sort of a lot more complicated if we want to figure out which things are reachable from which others. Now, there are actually a bunch of possible notions of connectivity that show up in directed graphs. The first one is sort of that these 2 points can't be separated from each other, that you can't put them on two different islands, where nothing in one island connects to anything in the other. And this sort of says that it means you can get from one vertex to the other following edges in any old direction. And I mean, okay, this says you can't put them on different islands, but it doesn't say you can reach either from the other one without breaking traffic laws by following one-way streets in the wrong direction. So a second notion is that maybe we want one of the vertices to be reachable from the other, using the actual edges in their intended direction. And this is a more practical notion. However, it has its weird irregularities that makes it hard to deal with. So a third notion that's maybe a little bit stronger is that you should have two vertices, V and W, where not only can you reach W from V, but you can also go back and reach V from W. And this third notion turns out to be pretty nice. So when we say that two vertices V and W in a directed graph are connected, we mean this. We mean that you can reach V from W and also can reach W from V. But the theorem now is that using this notion, we actually recover much of the power that we had in the undirected case. A directed graph can always be partitioned into strongly connected components, where two vertices are in the same strongly connected component, if and only if they're connected to each other. So, for example, the graph that we looked at has 5 strongly connected components. F, you can get all around there, but there's no way to get from it to anything else. H and I, you can get from one to the other, but not necessarily to other things. A, B, C, and E from any of those 4 vertices, you can reach any other one. But once you leave, again, you can't get back. D and G are each their own components, and that's it. Within each of these components, you can get from everywhere to anywhere else. But again, once you leave it, you can't come back. So to make sure we're on the same page, we have the following graph. What is the strongly connected component of A in this graph? Well, it turns out to be the following set. A, B, E, F, G, and H are in this component. The other ones aren't. And to see this, we can see that sort of you can actually get around any of these 6. A goes to E, goes to H, goes to F, goes to B, goes back. B goes to G, goes to H, goes to F, goes back to B. Sort of, you can use these to navigate around everywhere you like. But from D, you can't get to D from this other component. And C and I, once you get there, you can't come back to the other vertices here. So the result is that if you have a directed graph, it can always be partitioned into strongly connected components, such that 2 vertices are connected if and only if they're in the same component. And the proof of this is very similar to the proof of the sort of similar thing in the undirected case. Again, we need to show that connectivity in the strong sense is an equivalence relation. That if U is connected to V and V is connected to W, then U is connected to W. But well, if these connections happen, there's a path from U to V and a path from V to W. And so pushing them together, there's a path from U to W. Similarly, there's a path from W back to U and from W back to V and V back to U. And composing them again gives you a path from W back to U. And so that completes our proof. Now, there's something more to say, though. Once we split our graph into connected components, they still have edges connecting these components to each other. So one useful thing to do is to draw what's known as the metagraph, which sort of tells us how these connected components connect to each other. So this metagraph has vertices that correspond to the connected components of the original graph. And you have an edge between 2 of them if there's an edge in that direction connecting those vertices. So D connects to A, so there's an edge between D and the component of A. It also connects to G, A, B, C, or E. Those guys have edges leading to H and leading to F, and so they have edges into those components, and so on and so forth. And this is our metagraph. Now, one thing to note about this metagraph is if you stare at it for a little while, you can actually see that it's a DAG. And this is, in fact, no coincidence. It turns out that the metagraph of any graph G is always a DAG. Now, the proof of this is not so hard. Suppose that it's not. What that means is that there's a cycle. And what happens if you have a cycle is that every node in the cycle can be reached from every other node because you just travel along the cycle until you get there. Now, this would be true if they're individual vertices, but it's also true if you have a cycle between strongly connected components. Because since everything in one component connects to everything else, you could just get to the guy leading to the next component and then to the vertex leading to the next component and sort of follow this all the way around the cycle. And so everything in all of those components are all connected to each other. But since everything's connected, they should all be the same strongly connected component. However, the single vertices of the metagraph are strongly connected components, so you can't have 2 vertices that are connected to each other. And that gives us a contradiction. Okay, so in summary, we can always partition our vertices into strongly connected components. We have a metagraph that describes how these strongly connected components connect to each other, and this metagraph is always a DAG. So this is what we have. Next time what we're going to do is we're going to actually talk about how to compute these things. How do we compute the strongly connected components of the graph? How do we find the metagraph? So come back for the next lecture and we'll talk about that. Hello everybody, welcome back to our graph algorithms course. Today we're going to talk about how to give an algorithm to efficiently compute the strongly connected components of a directed graph. So if you recall from last time, what we had is we find this notion of connectivity in directed graphs where 2 vertices were connected if you could get from one to the other and back. Now we said that this graph necessarily would be divided into strongly connected components, where within a component you could get from everything to everything else, but sort of once you leave the component you can't get back. Now, these components are connected to each other by what we called the metagraph, and the metagraph was always a DAG, which was sort of a useful thing, as we'll see today. So the problem we're going to look at today is, given a graph G, a directed graph G, how do we find the strongly connected components of G? Now, there's a pretty easy algorithm for this, it turns out. For each vertex V, you run explore on V and determine all the vertices reachable from V. Once you've done that for every vertex, you note that for a vertex V, what you want to do is you want to find all the vertices U that are both reachable from V and can also reach V. And that, it turns out, will give you the strongly connected component of V. And so this gives you the strongly connected component of V. You run this for all V. That gives you all the strongly connected components. And so the runtime of this algorithm is a little bit slow because you need to explore from every single starting vertex. So the runtime is something like O of V squared plus V times E. This is okay, but we'd like to find something faster. And what's the idea? The key idea of this algorithm is the following. If you take a vertex V and run explore, you find everything you can reach from V. Now this includes the component of V, but if there are other components downstream of that, you might find vertices from other connected components as well. However, there's a case when this doesn't happen. If V is located in a sinc strongly connected component, that means there are no edges out of that strongly connected component. And so when you explore from V, you will find exactly its strongly connected component, which is good because we want to find the strongly connected components. If you actually find one, that's a good start. So how do we do this? Well, we need to find a vertex in a sinc strongly connected component, which takes some thought. Well, there's a theorem, it turns out, that will help. If C and C prime are two strongly connected components, where there's an edge from some vertex of C to some vertex of C prime, it turns out that the largest post number in C is larger than the largest post number in C prime. Now, to prove this, we split into two cases. When we run our depth first search, either we visit a vertex in C before we visit a vertex in C prime, or it could be the opposite way. We visit a vertex in C prime before we visit a vertex of C. In the first case, where we visit C first, well, from a vertex in C, you can reach everything else in C because it's the same component. There's also an edge from C to C prime, so you can also, it turns out, reach everything in C prime from that vertex. And that means that while you're still exploring that first vertex in C, you actually explore everything else in C and everything in C prime as a subroutine. And this means that because of the way subroutines work, you have to finish exploring all those vertices before you finish that last vertex in C. And so that one vertex in C has the largest post number of any vertex in either component. The second case is you visit C prime first. Here the claim is that you can't actually reach C from C prime. Because if you could reach C from C prime, then you sort of follow the edge from C back to C prime and you'd have a cycle. And this is not just any cycle, this is a cycle in the metagraph, which you can't have because the metagraph must be a DAG. And this means, since you can't reach C from C prime, when you explore C prime, you'll never actually find C in the middle of that exploration. So in fact, you have to finish exploring C prime before you can even begin exploring C. And so once again, the vertex with the largest post has to be in C. Okay, so what does this mean? If you look at the large vertex with the single largest post order number in the entire graph, what can we say about that? Well, it has to come from a component with no other components pointing to it. That vertex needs to be in a source component, which is great. It's almost what we wanted. What we wanted was a vertex in a sinc component. Well, there's a trick for doing this. So if you have a graph, we're going to define what's called the reverse graph, which is just what you get by taking your graph and reversing the directions of all the edges. So if the graph on the left is G, the graph on the right is the reverse graph. The edges are all the same, they're just pointing in the opposite directions. Now the cute thing here is that the reverse graph and G both have the same strongly connected components. I mean, V and W are connected if you can go from V to W and W back to V. But if you reverse all the edges, you can just follow those paths in the opposite directions, from V to W and W back to V. And so, the strongly connected components are the same, but the edges in the metagraph are different, because if you have a source component in the reverse graph, that means that you have edges coming out of it but not into it. Well, when you reverse the edges to get the original graph G, the edges come into it and not out, and you find a sync component. So in order to find a vertex in a sync component of G, what you do is you run depth first search on the reverse graph, which, by the way, is easy to compute. You just take every edge and reverse the direction. So you run depth first search on the reverse graph and take the vertex with the largest post order number. Okay, so just to review, which of the following is true? The vertex with the largest post order number in the reverse graph is in a sync component. The vertex with the largest pre-order number is in a sync component. Or the vertex with the smallest post order number is in a sync component. Well, all of these sound roughly equivalent, but if you work them out, only one of them is true. The first one. The vertex with the largest post-order number is in a sync component. The other ones sound plausible, but just don't work. Okay, but this gives us an algorithm now. And the point is the following. We run depth first search on the reverse graph. We let V be the vertex with the largest post number. And this has to be in a sync component of G. We now explore V, and because it was in a sync component, the vertices we found are actually a strongly connected component of G. So we take them, we remove them from G, and then we repeat. So here's our graph. We depth first search the reverse graph. The largest post number is that 18. So we explore at that. We find one vertex. That's our first component. We're now going to remove that from the graph and try again. Depth first search on the reverse graph. 16 is the largest post. We explore from there. We find this new component. Great. Depth first search the reverse graph. Find the largest post. Explore that. We have a third component. Depth first search the reverse graph. 10 is the largest. When we explore from that, we find these four guys as a component. And then there's the one vertex. We find that. So that gives us our strongly connected components. Unfortunately, this algorithm's a little bit inefficient again, because we need to run depth first search repeatedly on the reverse graph. But it turns out that that's actually unnecessary. Because remember, the theorem that we had was that if you have an edge between two components, the one that was further upstream always had the larger post order. In fact, when you reverse the edges, now it's the one downstream has the largest post order, but whatever. But the point is that after you remove the sync component, and if you just then look for the vertex with the single largest remaining post order, that's going to be a sync component of the new graph. It doesn't point to anything else except for maybe some components that you've already removed. And so the new algorithm, we just run depth first search once on the reverse graph. Then we look for V in the graph in reverse post order. Any V that has not yet been visited, we explore that V and mark the vertices that we found as a new strongly connected component. So we have this graph. We depth first search on the reverse graph. We record the post numbers. Now the largest post is 18. We explore that vertex, find this component. Next is 17, which we explore and find this component. Then 15 finds this guy. 10 finds these four. And 6 finds the last guy. And that's it. A much faster algorithm. In fact, the runtime, we essentially just ran a depth first search on the reverse graph, and then ran another depth first search on G, with just the slight modification that we wanted to visit our vertices in this outer loop in some specific order, and also we needed to record the connected components as we found them. But basically, this is just two depth first searches. The runtime is linear, O of V plus E. And this gives us a nice, efficient algorithm for finding our strongly connected components. Well, that completes our unit on sort of these graph exploration and decomposition algorithms. These tell us how to find ways to get from one vertex in the graph to another. However, when you're actually trying to solve these problems in practice, you don't just want any route on your map that gets me from, where I am in San Diego to, say, Los Angeles, the route that I find might pass me through New York and Florida on the way. And I don't want to do that. What I really want to do is I want to find an efficient path. How do I get there with spends as little time as possible, or maybe as little money as possible? And this is what we're going to start talking about in the next unit, where Michael is going to be talking to you about how to find shortest paths in graphs. So I hope you enjoyed this unit, and we'll come back for the next one.
Hi! In this module, you will study shortest paths in graphs and algorithms to find them. These algorithms have lots of applications. For example, when you want to go from one city to another, you don't want to switch your transport many times. And in the travel planning system, there are algorithms that help you to minimize the number of such switches. For example, to get from Hamburg to Moscow with the minimum possible number of flight segments. When you start a navigation app on your smartphone to get home from work faster, one of these algorithms is used to give you the fastest route possible. Also, one of these algorithms is used right now to direct the network packets with data through the internet so that you can watch this video online. In this module, we will start with the most direct route problem about flight segments. We will then consider the problem of getting from point A to point B with the fastest possible route. And in the end, we will consider the problem about currency exchange, which doesn't seem to be a problem about graphs or shortest paths, but actually the same algorithms will help you to exchange currency in the optimal, most profitable way. Let's start with the most direct route problem. It is formulated very simply. What is the minimum number of flight segments to get from one city to another? For example, if we look at this map, you could go from Hamburg to Moscow with 5 flight segments. But this is obviously not optimal, because you could go from Hamburg to Moscow with a direct flight. We can consider it as a graph problem, on a graph where nodes correspond to cities and directed edges correspond to available flights from one city to another. The edges are directed because flights can be available one way and not available another one, for example, because there are no tickets left. And of course, in the typical real-world graph, there are many more cities and many more possible flights, but this is just an illustrative example. So here, the graph problem is to get from node corresponding to Hamburg to node corresponding to Moscow. And one way to do that is to use these 5 edges corresponding to the 5 flight segment we saw on the map, but this is obviously not optimal in terms of minimization of number of edges. For example, you could get from Hamburg to Paris first and then from Paris to Moscow, and that would be just 2 edges. Or in this case, you could go just directly from Hamburg to Moscow, and obviously this is the optimal way to use just 1 flight segment, which is not always possible. For example, to get from Hamburg to Helsinki, you would need at least 3 edges on this graph. Also notice that as soon as we formulate it as a graph problem, we don't need to name the nodes like Hamburg or Moscow. We can just rename them to A, B, C, D, E, and then solve the problem on an abstract graph. So let's talk about paths in graphs. So we define length of the path, L of P, where P is the path, as the number of edges in this path. For example, if we consider the path from D to B, which consists of edges from D to E, then from E to S, from S to A, and from A to B, then the length of this path is 4. And note that this is an undirected graph, but we will also look at the directed example soon. Another example of a path is from D to B again, but through S, from D to S to C to B, and the length of this path is 3. Now, the distance between 2 vertices or nodes in the graph is the length of the shortest possible path between them. For example, the distance between D and B is just 3, because this is the path from D to B, which contains just 3 edges, and there are no paths that contain less than 3 edges. And the distance from C to A is just 2, because there is a path through S, there is another one through B, which is also of length 2, but there is no direct edge from C to A. The situation changes a little bit when the graph is directed, because not all edges can be taken, and so distance from D to B in this graph, which looks like the same but has directed edges, is now 4 instead of 3 in the undirected case. This is because we cannot take the edge from D to S, because it is directed in the wrong direction. So distance from D to B is 4 because there is this path in green and there is no shorter path. And the distance from C to A in this case is infinity, because there is actually no path from C to A, because you cannot go from C to S, and even if you go from C to B, you cannot go from B to A because the edge is going in the wrong direction. Now let's consider the paths from some origin node S. It turns out that to find the shortest path from A to B is not simpler than finding shortest paths from A to all other nodes in the graph, or at least almost all the other nodes in the graph. And so we will be studying the problem of finding shortest path from one starting node S to all other nodes in the graph. When we select the starting node, we can lay out the same graph in a different way using distance layers. In this case, we have 3 distance layers. The first one is layer 0, which contains just node S, which is at distance 0 from itself. Then we have layer 1, which contains 4 nodes at distance 1 from node S. And then we have layer 2, which contains just one node B, which is at distance 2 from node S. If we added another node to this graph, for example node F, which is only connected with B, then it will have 4 layers, and additional layer 3 contains just node F, which is at distance 3 from node S. Note that there cannot be an edge from D to F in such layered graph, because otherwise there would be a path from S to F of length 2, S, D, F, and then F would be in the layer 2, and there would be no layer 3. And another example is that there cannot be an edge from S to F, because in this case the distance from S to F would be 1, and so F would be in the layer 1, and again there wouldn't be no layer 3. And the general property is that the only edges which are allowed in such layered graph are edges inside the layer, like edge from D to E in this example, and edges between a layer and the next layer, like edges from S to layer 1, edges from A and C to B, and edge from B to F. Now let's consider the directed case. We directed all the edges downwards, and so the layers didn't change. We still have layer 0 with just S, layer 1 with 4 nodes, and layers 2 and 3 with nodes B and F correspondingly. What about additional edges here? For example, can F be connected to D? So yes, it can be connected to D, but in this direction, from F to D, because this edge from F to D doesn't give us any shorter path from S to F, and so the shortest path is still of length 3. Also, it is possible to connect F directly to S in this direction, or to connect B directly to S, because the shortest paths don't change. However, it is not possible to add an edge from C to F, because if we add this edge, the layer structure will change, because the distance from S to F will be just 2, from S to C and from C to F. And the general property is that there cannot be any edge from a layer to another layer which is farther from S by at least 2. So there can be an edge from a layer to the next layer. There can be an edge within the layer, such as an edge from D to E in this example. And there can be an edge from a layer to any of the previous layers, such as the green edges in this example. But there cannot be any red edges, such as an edge from C to F, which is an edge from the layer 1 to the layer 3, which is at least farther by 2 from S than layer 1. So there cannot be any such edges in the layered distance graph. And in the next video, we will discuss an efficient algorithm to traverse the graph layer by layer, so that in the end every node is assigned to some layer, and we know the distance to this node as the number of the layer to which it was assigned. Hi, in this video we will discuss breadth-first search, an efficient algorithm to find distances from an origin node to all the nodes in the graph. And we will use the layered distance structure of the graph from the previous video. We will start from the version of the algorithm which is easier to understand. We marked as S a blue node, which will be our origin, and we will find distances from this origin to all the nodes in the graph. We start with the state when all the nodes are colored in white. And a node colored in white means that this node hasn't yet been discovered. During the algorithm, we'll discover some nodes, and then we will process them. When we discover a node, we color it with gray. And first we discover the origin node, S. And when we process the node, we color it with black. And of course, after discovering the origin node, we start processing it. We will process the graph layer by layer. So we start with layer 0, which only consists of the node S, and we start processing it. When we start processing a layer, we take all the edges outgoing from this layer, and we discover all the nodes at the ends of those edges. So basically, when we start from layer 0, we discover the whole layer 1, because the edges from the layer 0 node S go to layer 1 nodes. Of course, there could be an additional edge from S to itself, but then we would ignore this edge because it goes to the node we've already discovered. In this case, there is no such edge, so all the ends of the edges outgoing from S are new nodes, white nodes, which are not yet discovered, and we color them with gray to mark the fact that we have discovered them. After we have discovered all of them, all the layer 1, we start processing all those nodes simultaneously. So we process all 6 nodes of the layer 1. And to do that, we take all the edges outgoing from those nodes and discover the new nodes at the ends of those edges. You may notice that there are a few red edges, and those are the edges which go from the nodes in the layer 1, but which go to the nodes which were already discovered previously, to S and to the nodes of the same layer 1. And there are a lot of bold black edges which go also from the nodes of the layer 1, which we're now processing, but they go to the new nodes which were not discovered previously, and we mark those nodes with gray. And when we process edges from the layer 1, we get all the nodes at the layer 2, because the edges from layer 1 go to layer 2, to the same layer, and to the previous layers. When edges go to the same layer or to previous layers, we mark them with red, and we don't do anything with the nodes on the ends of those edges. And when the edges go to the next layer, we discover nodes of the next layer. And of course, all the nodes of the next layer, of the layer 2, have some incoming edge from layer 1. So after processing layer 1, we've discovered the whole layer 2. And after we've discovered it, we start processing it. So we process the outer circle, all the nodes from the layer 2. And to do that, we consider all their edges which are outgoing from them, and you see that there are only red edges, because all the edges from layer 2 go to either the same layer 2 or to S or to layer 1 nodes, and all of them have been discovered before that. So we don't do anything with those nodes, and so we don't discover any new nodes, and it means that we don't have anything new to process, so our algorithm stops with that. And we now can assign each node to a layer. Obviously, node S, origin node, is in the layer 0. The nodes we discovered on the first step are the nodes of the layer 1, so they are at the distance 1 from S, and the nodes discovered on the next step are nodes of the layer 2, and they are at distance 2 from S. And so we found distances from S to all the nodes in the graph. But actually not to all of them, because there can be some nodes which are not connected to S, which are not reachable from S. And such nodes must have infinite distance from S. And we solve this issue by initializing all the distances from S to all other nodes with infinity. And then setting the distance from S to itself to 0 and implementing the algorithm that I've just told you. Then every node which is reachable from S will get some finite distance from S, and all the nodes which are unreachable from S will stay with their infinite distance. Now let's look how this same algorithm will work with an undirected graph. So we have basically the same graph, we just removed the arrows from the edges. So all the edges became undirected. And again we have the same origin S marked with blue. We start with all the nodes being white because they are not discovered yet. We discover node S and color it with gray. And then we start processing it and color it with black. To process it, we take all the edges outgoing from it. And you see that now there are more edges outgoing from S, because some of the edges which were incoming into S in the previous example now are also outgoing from S because they are undirected edges. So we discover 7 nodes instead of 6 as in the previous example. And after we discovered all these 7 nodes, this is our layer 1. These are all the nodes at distance 1 from S. We discovered them, now we start processing them. And to do that, we consider all the edges outgoing from those 7 nodes. All black ones but for S. And you see that some red edges appear. Those are edges inside layer 1 and edges from layer 1 to S. And there are a lot of bold black edges. Those are the edges from the nodes of layer 1 to the new nodes, which are not discovered before. And we've discovered almost all the nodes of the outer circle, but for the one in the bottom, which was discovered before. So we've discovered 11 new nodes. So we've discovered them, now we need to process them. And to do that, we consider all the edges outgoing from those 11 nodes. And all of those edges are red, because they all go to the nodes we previously discovered. So nothing new is discovered, and we stop our algorithm. And now we can assign distances. So again, distance from S to itself is 0. Distance from S to the nodes discovered in the first step is 1. This is layer 1. And distance from S to the 11 nodes in the outer circle is 2. This is our layer 2. And again, we found all the distances from S. And we found all the layers. And also, if there are some nodes which were not connected with S initially, we initialize the distances to infinity, and so they stay with this infinite distance to them. This is basically how the algorithm works, and it is more or less clear that it finds distances correctly because it just goes through the graph layer by layer. But to actually implement the algorithm, we need to do everything turn by turn. We cannot just take a couple of nodes and process them simultaneously. We need to have some order on those nodes. And now let's solve this problem. So we return to our initial example of a directed graph with S origin. And now we want to process each node one by one. To achieve that, instead of processing each layer of nodes simultaneously, we will have a queue of nodes. So the nodes will get into the queue and wait for their turn. And as soon as every node which was in the queue before this node has already been processed, this node goes out of the queue and it is being processed. So when we discover a node, we put it into a queue, and when we need to process it, we take it from the queue and process it. And it means that the nodes which were discovered earlier will also be processed earlier. And so, in general, the order of layers won't change, because first layer 0 node will get into the queue, then all the nodes from layer 1 will get into the queue, and then after they all are processed, we will process nodes of layer 2, which were discovered after nodes of layer 1. Now let's see how all that works. So we discover node S, and we already know by that time that the distance to S is 0. It is layer 0, and there are no more nodes in the layer 0. Now we'll start processing this node, and to do that we process the edges outgoing from S in some order. It doesn't mean which is the order, it can be just the order in which they were saved in our data structure for the graph. So we traverse first edge and we discover node to the right, and we know that the distance to this node is 1 because this is a layer 1 node. We discover it, and instead of starting to process it, we go to the next edge from S and we discover another node of layer 1 and assign the distance to 1, and again and again, again and again. And so now we have discovered all the nodes from the layer 1, and we put them all in the queue in the order starting from the node to the right and counterclockwise order. So now we've processed our node S, and we need to process something else. What to process? The node which is the first in the queue, and this is the node to the right from S. So we start processing this node, and we go through the edges from this node in the order they were saved. I don't know that order, so let's see. Okay, so the first edge outgoing from this node was to another node from the first layer, so it is a red edge because it goes to the node which has already been discovered. We don't do anything with this edge. Then the next edge goes to the right, and we discover a node from layer 2 which is to the right, and we set its distance to 2. Then the edge goes to the node right and up, and we also assign distance to this node to 2, and the last edge goes to the node to the right and down from our node, and it also gets distance 2 because this is a layer 2 node. And what do we do next? We've processed our node to the right from S, and we need to process something else, and this something else is the next node from the layer 1 in the counterclockwise order. This is this node to the right and up from node S. We start processing it. In some order, we process edges from it. So the first edge is a red edge to the left, and we don't do anything with it. The second edge is a red edge to the node to the right and up from it, which is from layer 2, but it has also been already discovered. And then the next edge gives us a new node from layer 2, and the next one also gives us a new node from layer 2. So we finished processing this node, and we go to the next one. Again, red edge, new node discovered, next node from layer 1, a red edge, a new node from layer 2, a new node. And again with another node from layer 1 and the last node from layer 1, we process it. Okay, so we've processed all the nodes from layer 1. We've discovered all the nodes from layer 2 in some order. I don't even remember the order of those nodes. It is mostly counterclockwise, but not completely. So let's see in the slides what is the correct order. So the first one to be discovered was the node to the right, and we start processing it, and there is a red edge from it, and another one, and there are no more edges from this node, so we start processing the next one in the counterclockwise order. And there is a red edge from it, and it looks like there are no more edges from it, so we finish processing this node, and then we go to the node to the right and down, and there is a red edge from it, and that's all. And so we go through the nodes in the second layer, and all the edges from them are obviously red because we've discovered everything that connected to S already. So we go and test that all the edges are red, and now we've finished. And again we have the graph which is layered. Node S is in the layer 1, 0, 6 nodes in the layer 1, and 12 nodes in the layer 2. And if we had some node which was not connected to S, then it stays with the distance estimate of infinity. So this is how breadth first search actually works. And in the next video, we will discuss the pseudocode that actually implements this algorithm. Hi! In this video, we will implement the breadth first search algorithm from the previous video and analyze its running time. Let's look at this pseudocode. The procedure BFS is called after breadth first search, and it takes graph G and origin node S as input parameters. It also uses array dist to store the distances from the origin node S to all nodes in the graph. It can be not an array, it can be a map from nodes to distances, depending on what are your nodes. If your nodes are numbered from 0 to n-1, then it was probably convenient to use an array of size n to store distances for those nodes. But if your nodes are labeled with some strings or some other objects, then it may be wise to use a map from nodes to distances and call this data structure dist. Anyway, we'll use this dist data structure to store our estimations of distances from origin to all the nodes in the graph. And we initialize all these distances with infinity, with the exception of the node S itself, which gets an estimation of 0 from the beginning. And we will also use another data structure Q, which is a queue, the data structure which works in the principle of first in, first out. So the first element that goes into the queue is the first element that goes out of the queue. And we initialize this queue with just one element, the origin node S. And this symbolizes that we already discovered node S and put it in the queue. So all the discovered nodes are those which are in the queue. All the nodes which haven't been in the queue yet are white nodes, which are not discovered yet. And the black nodes, in the terms of the example I showed you before, are those nodes which are already out from the queue and are being processed or have been processed before. And we will take nodes from queue one by one, process them, discover new nodes, and put new discovered nodes back into the queue. So we start with queue initialized with only starting node S. And while this queue is not empty, we take the first element from it using method dequeue. So we get it to variable u. So this is the first node in the queue, and we start processing it. And to start processing, we traverse all the edges outgoing from this node u in the graph. So we have a for loop for all edges uv in the set of edges of the graph, and this means that we traverse all the edges which have starting node u and some other node as its end. And we look at node v, and now we need to determine whether this node is already discovered and maybe already processed or not. And to determine that, we will use our dist values. So if dist value of the node is infinity, then it means that this node hasn't been discovered yet, because as soon as it will be discovered, we will change the estimation of the distance to it, and it will become finite. While it is still infinite, it means that the node hasn't been discovered. And vice versa, if dist is finite, then we have discovered this node already. And so if this node was discovered previously, then we don't need to do anything with it. This is a red edge, and we don't do anything with a red edge from our currently processing node to the node which was discovered earlier. But if the edge is to a white node, which was not discovered previously, we need to process this edge. And by processing it, we first discover the end of this edge, v, and we do that by calling nq, so adding this v to the end of the queue. And we also change the estimate of the distance to this node v, and we set it to distance to the current node plus 1, because we know that when we process a node from some layer, some of the edges are red because they go to the same layer of one of the previous layers, but the edges that go to the undiscovered nodes go to the next layer. So the distance to v is equal to distance to u plus 1. And we repeat and repeat this process while our queue is not empty. And we need to make a few notes. First, this infinity thing. Of course, in a real programming language, there won't be any infinity, so you will have to use something special for that. One variant is to estimate what is the maximum possible distance from origin node to any nodes in the graph, and just use a constant value or some computable value which is definitely bigger than that. For example, distance from origin cannot be bigger than the number of nodes in the graph, because every path without cycles inside it will have at most number of nodes minus 1 edges. Or you can just say that it is not bigger than the number of edges in the graph, because you won't use the same edge twice in the shortest path from origin node to your node. So anyway, you can assign infinity to number of nodes plus 1, or number of edges plus 1, or some other big value. And another thing you can do is you just, instead of using integer numbers for storing distances, you create a special structure which has two fields. One of them is distance, if it is determined, and another field is just a Boolean field which tells you whether the distance is defined or it is still not defined, and then this means infinity. And another note is that why this algorithm even stops. And the key observation is that we only put a node into the queue once, because as soon as we put this node in the queue, we unqueue it, we also change the estimation of distance to this node, and it becomes finite. And so when we'll try to put it in the queue next time, we'll compare the distance to it with infinity, and it won't be equal to infinity. And so we won't put node into the queue again. And it means that we put at most number of nodes in the graph, elements in the queue. And on each step of the while loop, we take some node out of this queue. So its size decreases. So it can increase at most number of nodes in the graph times, and it decreases on each step. So this means that this algorithm definitely stops, and it definitely stops after at most number of nodes in the graph steps of the external while loop. Now let's estimate the running time of this algorithm more precisely. I state that the running time of breadth first search is proportional to the number of edges plus number of nodes in the graph. Why is that? First, we've already discovered that each vertex, each node of the graph is unqueued at most once. So the number of iterations of the external while loop is at most number of nodes of the graph. Another observation is that each edge is examined either once for directed graphs or twice for undirected graphs. Why is that? Well, the edge is examined when one of its ends is processed. The node, which is one of its ends, is processed. And if the graph is directed, then the edge is actually examined only if its start is processed. And if the graph is undirected, then for each of its nodes, the edge is examined when this end is processed. Of course, this edge will work and discover a new node at most once out of those 2 times it is examined, but still it will be examined twice from both ends. And of course, if the edge is not connected to the original node, it won't be examined at all. But we say that each edge, in any case, will be processed at most twice. And what it means is that the total number of iterations of the internal for loop is at most number of edges of the graph. And so adding those up and adding the constant number of operations in the start and adding the initialization of the dist values, which goes in time proportional to the number of nodes of the graph, in total we get number of edges plus number of nodes in the graph. And in the next video we will prove that breadth first search actually returns correct distances to all the nodes from the origin node. Hi, in this video we will prove the correctness of the breadth first search algorithm for finding distances from an origin node to all the nodes in the graph. We will also prove some properties of this algorithm which can be useful when you want to extend this algorithm to other kinds of problems. First, recall that a node U is called reachable from node S if there is a path from S to U. And the lemma states that the reachable nodes are discovered during breadth first search and they get a finite estimate of distance from S. And unreachable nodes are not discovered during breadth first search and they stay with infinite distance estimate, infinite dist value. First, let's prove it for reachable nodes. So suppose, for the sake of contradiction, that some reachable nodes were not discovered during the breadth first search. Then select out of those nodes the one closest to S in terms of the length of the path. So let's assume that U is the closest to S unreachable node which was not discovered during the breadth first search. Then take the shortest path, some shortest path from S to U. It goes from S to some node V1, from there to V2, and so on, and up to Vk, and from Vk it goes to U. Then U will be discovered actually while processing Vk. Why is that? Well, because first we will discover and process S, then we will discover and process V1, then we will discover and process V2, and so on, and we will go up to Vk, and when we process Vk, U will be discovered. So this is a contradiction with the assumption we made for the sake of contradiction that some reachable node is not discovered during breadth first search. So we proved that reachable nodes are discovered. And of course they will get a finite estimation of distance, because this is how the algorithm works. As soon as the node is discovered, it gets estimation of distance bigger by 1 than the estimation for the node being processed. Now let's prove the statement about unreachable nodes. Let's suppose again, for the sake of contradiction, that some unreachable node were discovered. And let U be the first such unreachable node to be discovered. Now let's see when it was discovered. It was discovered while processing some other node V. And as U is the first unreachable node that was discovered, and V was discovered before U, because U is discovered when V is already processed, it means that V is a reachable node, and it means that there is a path from S to V. But then it means that there is a path from S to U through V. So U is actually reachable, and this is a contradiction. And so we proved that unreachable nodes are not discovered during the breadth first search. So it works correctly, at least in the sense that it finds some distances to reachable nodes and doesn't find any finite distances to unreachable nodes. Now we will prove the order lemma, which states something about the order in which nodes are discovered and dequeued from the queue. So it says that by the time some node U at distance d from the origin node is dequeued, it started processing, all the nodes at distance at most d have already been discovered. So they have already been enqueued in the queue, and maybe some of them have already been processed, some of them are still in the queue, but at least they have already been discovered. So let's prove this again by contradiction. Suppose that this lemma is not true, and consider the first time this order was broken, so that some node U at distance d has already started processing, and that's why it is filled with black, and some other node V at distance d prime, which is at most d, has not yet been discovered. Let's suppose that. So we know that d prime is at most d, and we know that node U was discovered while processing some other node U prime, and we know that the distance to this node U prime is at least d minus 1, because if the distance to U prime was less than d minus 1, then the distance to U would be less than d, because there is an edge from U prime to U. Also, we know that the node V has an edge from some node V prime with distance d prime minus 1 from S, because there is some shortest path from S to V, and there is the previous node before V on this path, and this is V prime, and distance to V prime is exactly d prime minus 1, because this is a shortest path, so it can be less than d prime minus 1, because otherwise distance to V will be less than d prime, and it cannot be bigger than d prime minus 1, because then the shortest path to V would be longer than d prime. So distance from S to V prime is exactly d prime minus 1. And we know that d prime is at most d. And from that we know that d prime minus 1 is at most d minus 1. And it means that V prime was discovered before U prime was dequeued, because we know that the first time that order lemma was wrong was with nodes U and V, and nodes U prime and V prime were before that. So at that point of time order lemma still worked. So we know that V prime was discovered before U prime was dequeued. So it means that V prime was gray before U prime became black. And this means that Also, v prime became gray before u became gray, because u became gray while processing u prime. So v prime was enqueued and filled with gray before u was enqueued, discovered, and filled with gray. What that means is that because our queue works as first in, first out, and v prime was discovered before u, it means that v prime was also started processing before u. So v prime was dequeued and filled with black before u was dequeued. And immediately after v prime was dequeued, v would be discovered, because there is an edge from v prime to v. So either v was discovered even before that, or it was discovered during processing v prime. And we see that v is already discovered and u is not yet dequeued. So it is a contradiction with the fact that when u was already black, v was still white and not discovered. So we proved our order lemma by contradiction. Now the main result is that when node u is discovered or enqueued during breadth first search, the dist value, the estimate of distance to this node from origin, is assigned exactly the correct distance from node S to node U. Let's prove this. To prove it, we'll use mathematical induction, and as a base case we see that when node S is discovered, this is the first node to be discovered, the dist value is assigned to 0, and this is actually the correct distance from S to itself. So we'll use induction on the distance to the node. So the inductive step is that suppose we proved our statement about correct distances for all nodes which are a distance at most k from the origin, and now we will prove it for nodes at distance exactly k plus 1. If we do that, we prove the lemma itself. So now, take a node v at distance k plus 1 from the origin. We know that for all nodes which are closer, the correct distances are found during breadth first search. Now let's prove it for this particular node v. So we know that v was discovered because it is reachable, and we proved that all reachable nodes were discovered during breadth first search. So it was discovered while processing some other node u. Now let's estimate the distance to u. From one point of view, we know that the distance from S to V is at most distance from S to U plus 1, plus this edge from U to V, through which V was discovered. And we know that distance from S to V is exactly k plus 1, and it means that distance from S to U is at least k. From the other hand, we know that V is discovered only after U is dequeued, and using the order lemma, we can state that the distance to U is strictly less than distance to V, because otherwise V would be discovered before U is dequeued. And so distance from S to U is strictly less than k plus 1. And we already know that it is at least k. And we also know that this distance is integer number. And so the only option is that distance from S to U is exactly k. And then see what happens when we assign dist value for V. We assign it to dist value of U plus 1, which is k plus 1, which is the same as the distance from origin node to V. So we proved our lemma by induction that when the node is discovered, at that point it is assigned correct distance estimate, and it is saved in its dist value. And the last property we want to prove, just to understand better how breadth first search works and to apply it to some non-standard situation, is that the queue which we use in the breadth first search looks like this. It first has some nodes at distance d for some d, and maybe in the end it also has some nodes at distance d plus 1, but it doesn't contain any other distances. If the first node in the queue has distance d, then there are no nodes in the queue with distance less than d, there are no nodes with distance more than d plus 1, and maybe there are some nodes at distance exactly d plus 1, but they all go after all the nodes at distance d in the queue. Let's prove that. So first, we know that by order lemma, all nodes at distance d were enqueued before first such node is dequeued. And nodes at distance d plus 1 are only found when a node at distance d is dequeued and processed. So this means that nodes at distance d were enqueued before nodes at distance d plus 1 were dequeued. Also, we know the same thing for nodes at distance d minus 1. So they were all enqueued before nodes at distance d. So by the time node at distance d is dequeued, all the nodes at distance d minus 1 are already dequeued from the queue. So there are no more nodes in the queue at distance d minus 1 or less. And regarding the nodes at distance more than d plus 1, they will be discovered only when we start dequeuing nodes at distance d plus 1 and more. But those nodes are all going after nodes at distance d. So at the point when the first node in the queue has distance d, no nodes at distance more than d plus 1 can be in the queue, because no nodes at distance d plus 1 were dequeued, and so we couldn't put anything at distance more than d plus 1 in the queue. So we proved this property also, and now we have a proof that our algorithm finds correct distances to all the reachable nodes in the graph, that it finds infinite distances to the unreachable nodes in the graph, and we also know the structure of the queue at any given moment in time. And in the next lecture, we will also learn how to actually not only find distance, but also reconstruct the shortest path from the origin to the node we need. Because we don't want to just know that the distance in terms of number of flight segments from Moscow to San Diego is 2. We also want to find those 2 flight segments to actually get from Moscow to San Diego. So see that in the next video. Hi, in this video you will learn what is a shortest path tree, how to build it, and how to use it to reconstruct the shortest path from origin node to the node you needed shortest path to after finding distances with breadth first search. And we will need to slightly modify breadth first search procedure for that. So what is a shortest path tree? On the left we see some undirected graph with 9 nodes, and suppose we selected node S as the origin. And then on the right we see the layered structure of this graph, where S is in the layer 0, 4 nodes in the layer 1, 2 nodes in the layer 2, and 2 nodes in the layer 3. So we know all the distances to those nodes. But what we also can remember is how did we come to this or that particular node during the breadth first search. So for example, we came to the node A during breadth first search directly from S, and so we draw a directed edge from A to S, saying that S is the node from which we came to A when we discovered it. And we also draw an edge from B to A, saying that in our breadth first search algorithm we discovered B from A. So we can draw such an edge for all the nodes but for S itself, and we will get some graph, and we'll prove later that it is a tree. But to make it a tree we also need to make it undirected, so we just remove all the arrows from the edges, and this already will be a tree. So the lemma states that shortest path tree as we defined it now is indeed a tree, so that it doesn't contain any cycles, because the fact that it is a connected component is by construction. We only add those nodes in the tree which we reached during breadth first search, and we'll always connect a new node which is just discovered to some node which was already in the tree, so the graph is obviously connected. We only need to prove that there are no cycles in this graph. Let's prove that, as usual, by contradiction. So suppose there is a cycle in the shortest path tree, and suppose this is a cycle of length 5, A, B, C, D, E. Now this is an undirected cycle, but the edges of the cycle have to be ordered somehow initially. So for example, the edge between A and B can be either from A to B or from B to A, but it doesn't really matter. Let's assume that it goes from A to B without loss of generality. Now what we know is that in the shortest path tree, at most one outgoing edge from each node, because for each node other than S, we just saved from which node we discovered it, and there is only one such node from which it is discovered. So there is at most one outgoing edge from each node, and so if we look at the edge between A and E, we know that there is an outgoing edge from A already, so the edge between A and E cannot be an outgoing edge from A, because then A would have two outgoing edges. And so the only way this can work is that there is an outgoing edge from E to A. And similarly, the edge between D and E can only be an edge from D to E, and the same with edge CD, and the same with edge BC. So now we see the directed loop. So looks like it can work, but unfortunately it cannot. So now let's look at the distance from S to A. We know that when we go by the directed edge of a shortest path graph, we go from node which was discovered from some node to the node from which it was discovered. And we know that the distance to the newly discovered node is assigned to distance of the node from which it was discovered plus 1. So if we go by this edge to the parent in the shortest path tree, we decrease our distance from S by exactly 1. We begin, we stay in the node which is closer to S exactly by 1. So if we go from A to B, the distance to S decreases by 1. If we go from B to C, it decreases by 1. So we start with some distance D from S to A. Then when we go by edge AB, we stay at node B, and we know that the distance from S to B is at most D minus 1. And then the distance to C is at most D minus 2, and distance to D is at most D minus 3, and D minus 4 for E. And now we make a conclusion that distance to A is at most D minus 5. So D is at most D minus 5, which is a contradiction, which cannot happen. So by contradiction, we prove that there cannot be any cycles in the shortest path tree in D. Now, how to construct the shortest path tree? We've defined it in such a way that it is very easy to do. We only need to add two statements to the code of the BFS procedure. We need another array or map, which is called prev. So in prev, we will store for each node the previous node from which it was discovered. And we initialize it with pointers to nowhere with a special pointer nil, which basically means we don't have any previous node. And when we discover a node in the end of the procedure, we not only update the distance to this node, but we also save the node from which it was discovered. And this is the only moment when prev changes, because next time we won't discover this node again and we won't change its prev. So that's the whole code for constructing shortest path tree. Now for every node we know what is its parent in the shortest path tree. How do we reconstruct the shortest path given the shortest path tree? So the nice property of the shortest path tree is that it somehow contains all the shortest paths from the origin to all the nodes. Why is that? Because if we go by edge of the shortest path tree, we decrease the distance exactly by 1. So if we start from some node and go by edges of shortest path tree by directed edges one by one, we will each time decrease the distance by 1. And so it means that if the distance to the node was D, then exactly after D steps, we will end up in the origin node, because we will be at distance 0. So we will make D steps. We will have a path of length D, where D is the shortest path length from S to this node. So we will have the shortest path itself, because its length is the same as the distance to this node. So what do we need to do in the code? We write down a procedure reconstruct path, which takes in the origin node S, the node U for which we need to reconstruct the path, and the array prev, which BFS procedure built for us. And the result variable will store the path itself. So we start with an empty path, and then we will go back from node U until we come to node S. So we start with our node U, and while it is not yet equal to S, we append it to the shortest path, and then we go by the edge of the shortest path tree by assigning prev of U to U. And then we repeat it until we come to node S, and U will be equal to S, and our while loop will stop. By this time, we have the shortest path from S to U in the result variable, but for one thing. It is in the reversed order. So we have first the end node, which is u, then we have the prev of u, then prev of u, and so on up to s. So the path is in the reverse order. So to return the actual shortest path from origin to node u, we need to reverse this path. And then we return the result. So of course this procedure works fast. It only needs amount of steps which is equal to the distance from node S to node U, which is definitely less than or equal to number of nodes in the graph, for example. But in most cases it will be even less than that. So in conclusion, we can now find the minimum number of flight segments to get from one city to another if we have the graph of cities and available flights between them. We can also not only find this number of flights, but we can actually reconstruct the optimal path between some city and another city. For example, we can go from Moscow to San Diego in the minimum number of flight segments. And we also can build the tree of all shortest paths from one origin. So we not only can build a shortest path from one node to another, but we actually can build all the shortest paths from one node to all the nodes in the graph. And all this works in time proportional to number of edges plus number of nodes in the graph. Hi! In this lecture you will learn the algorithm for finding fastest routes, which is used, for example, when you open your navigation app to get home from work faster, or by logistics companies when they want to deliver the goods to their customers in time but use less cars and less people. So let's first state the problem. It's really easy to do. For example, what is the fastest route to get home from work? Or more generally, what is the fastest route from point A to point B right now? And below you see a screenshot from a popular navigation app, Yandex Navigator, which is given a task of getting the fastest route from the point you are currently in, which is marked by a circle with the letter Y in it, to the finish, which is your destination. And it suggests you a few variants. So the default suggestion is the fastest route, but there are two others, and there may be, for example, a route which uses less turns, or the route which is easiest for a novice driver, and sometimes there can be a shorter route which is not the fastest one, but shortest one in terms of distance. So in this problem we can represent the city or the country as a graph where nodes are some positions in the country, for example the crossroads, and the edges are the roads that connect those crossroads, and there are some weights on those edges, and weight on an edge is in this case the time in seconds or in minutes you need to get from start of the edge to the end of the edge. And what you need to find is the shortest path in this graph, but not shortest path in the graph in terms of the number of edges, shortest path in terms of the sum of the weights of those edges. So if you want to get from A to B in the smallest amount of time possible, then you get by some path with some edges and some weights on those edges corresponding to the time, and you just sum up those weights of the edges and you get the total time it will take you to get from A to B. You want the fastest route, so you need the shortest path in terms of the sum of the weights of edges on this path. Let's see now, does the breadth first search algorithm from the previous lesson maybe help us? So let's look at this graph. Here we see that node A has a direct edge from A to the point B where you need to get. And so what our breadth first search would say us is that we already know the optimal path from A to B, because there is a direct edge, and so there is no point in getting to some other nodes. You just go directly from A to B, right? Well, this doesn't work. For example, in this case, let's suppose that it takes 5 hours to get from A to B, and the corresponding weight of the edge from A to B is 5. And let's suppose there is another node C, such that there is an edge from A to C, which takes 2 hours to go through it, and another edge from C to B, which also takes 2 hours to get through it. And of course this looks a little bit strange, but if there is a traffic jam on the road from A to B, and roads from A to C and from C to B are free roads where there is no traffic jam, then this can happen. And so then we see that going from A to B through C will take just 4 hours, while going directly from A to B takes 5 hours. And so our breadth first search algorithm doesn't work. So maybe it's vice versa, maybe it's always better to work around, to go around some node, not to go directly. But that's not also not the case, because if the edge from A to B is 3 hours and edges from A to C and from C to B didn't change, and we just removed the traffic jam from A to B and it became 3 hours instead of 5, it is now better to go directly from A to B. So there is no universal rule to go directly or not to go directly. We need something more clever than that to solve our shortest or fastest route problem. Now let's gain some intuition about this problem. So let's look at this graph below and assume that we stay at origin node S, and we only know that the edge from S to B is going to take 3 hours, and from S to C is going to take 5 hours. So can we be sure that the distance from S to C is equal to 5, that it will take 5 hours for the optimal route from S to C? Okay. So no, this is not the case, because, for example, the edge from B to C can have weight 1, and so the shortest route from S to C will be from S to B and from B to C, which is only 4 hours instead of 5 hours if we go directly. So we cannot be sure that the shortest, the fastest route from S to C is 5 hours. Now another question is, can we be sure that the distance from S to B is equal to 3? And in this case the answer is yes, because if we don't go directly from S to B, what other options do we have? We can go only from S to C and then go by some other edges to come to B. But if we go from S to C, we spend already 5 hours. And after that, we also spend some time to get to B. And that time is non-negative, so we cannot spend less than 3 hours time in the end. We actually cannot spend even less than 5 hours in the end. So going from S to B directly by 3 hours is beneficial for us. In terms of the graph and the weights of the edges in it, it means that there are no negative weights on the edges. All the weights are non-negative numbers, and so we cannot decrease the length of the path by going through them. So if we have already a path of length 3 and all other paths start from spending more time, we cannot improve this direct path. And in the next video we will use this idea to create a naive algorithm that solves our fastest route problem. Hi, in this video we will solve the fastest route problem using the idea from the previous video, but we will do it using a naive algorithm, which we will need to improve in the next video. First, let's make an observation that if we have some optimal path, some fastest route or some shortest route, then any part of it between some node in the middle and some other node in the middle is also optimal in the same sense. Let's prove it. Consider an optimal path from some origin S to some node T, and consider some two vertices U and V on this path. They can coincide with S or T, or they can be somewhere in the middle. Suppose there was some shorter path from U to V, which is marked with green. Then we would be able to go from S to U as in the original path, take a shorter path from U to V, take a shortcut, and then go by the original path from V to T. And in total, this new path will be shorter than the initial path, which was optimal. So this cannot happen, and so we know that actually any part of an optimal path is also optimal itself. Corollary from that is that if there is some shortest path from S to node T and U is the previous node on that path, then distance from the origin to the final destination T is equal to the distance from origin to node U, which is the previous to destination node, plus weight of the edge between U and T. And we will use this property to improve our estimates of distances from origin to some nodes gradually. You remember that in the breadth-first search algorithm we had an array or a map called dist, and we used these dist values to store our estimation of the distance from the origin to this particular node. In the breadth-first search algorithm, these distances started from infinity, and then as soon as they got updated, they became correct distances from origin to the corresponding node. This will not be the case in this algorithm. These distances will change several times, maybe, before they become correct. But in the end, they will become correct. And during the process, these distances will be upper bounds on the actual distance. So they will be more than or equal to the real distance from origin to the corresponding node. And we'll use the procedure called edge relaxation. And it means the following. We take the edge uv and we check, is it better to go to v through the optimal currently known path from s to u and then following the edge from u to v? Does it improve our current upper bound on the distance to v or not? So we have some upper bound dist value, dist of v, and we achieved it maybe using u on the way or not. We might have come to v in a different way, and we might have come using the same distance as if we go from s to u and then follow edge uv, or we could use longer path. So we just check whether it is possible to improve our current estimation of distance of v via using distance of u plus weight of the edge to u. So here is the code of relaxation procedure. It takes one edge from u to v as input, and it checks if the current distance estimate of v is bigger than the current distance estimate of u plus weight of the edge. It means that definitely we can come to node u from s with a path with length at most dist of u, and if we then follow edge uv with the weight w of uv, we will improve the distance estimate of v. So in this case we update this distance estimate, we decrease it always, as you see, and we also remember that the node from which we came into v is now u. Remember that in the breadth-first search algorithm we stored in pref the node from which this node was discovered. In this case we use the same data structure to store the node from where we've updated the distance to our node last time. Now we're ready to suggest a naive algorithm to solve our fastest route problem. Procedure naive takes graph G and origin node S as inputs. It uses dist values and pref values the same as in the breadth-first search, and we initialize dist values with infinities and pref values with pointers to nowhere. We also initialize the dist value of the origin node with 0. And then the only thing we do is we relax some edges. More specifically, on each iteration of the do-while loop, we try to relax each of the edges in the graph. And if at least one such relaxation is effective, that is, some dist value changes, then we continue to the next iteration. And we only stop when the whole iteration, after going through all the edges in the graph, couldn't relax anything. And we state that this naive algorithm works. Basically that it stops, and when it stops, it finds correct distances to all the nodes. To prove that, assume for the sake of contradiction that at some point no edge can be relaxed, and there is a vertex v such that the distance to that vertex is bigger than the actual distance from origin to the node. We know that this estimation of distance cannot become less than the actual distance, because this is always an upper bound. It starts from infinity, and it is only decreased when we find a better path from origin to this node. So there is some path from origin to this node of length exactly dist of v, so it cannot be less than the actual distance from origin to this node. And this also means that there can actually be no such situation that we do relaxations and relaxations, and we do many iterations, and we don't stop at any point, because after any successful relaxation, some distance estimation is decreased by at least 1, and if we started with infinity, then the value just becomes finite, but that can happen at most a number of nodes times. And if the value was already finite, it just decreases by at least 1. And if we started with some number of finite values which are bigger than the actual distances, and at each iteration we decrease at least one distance by at least 1, this process cannot be infinite. It will at some point come to the stage when the distance and the distance estimate are the same, and so this edge cannot be relaxed anymore. And if that happens for all the edges, our algorithm will stop. So our algorithm definitely stops. The question is whether it comes to exactly the same dist values as distances from origin to the corresponding nodes. So for contradiction, we assume that it does not, and that for at least some node v, dist value is bigger than the actual distance from origin. Then we consider some shortest path from S to this node v. And v definitely is a broken node in the sense that its dist value is bigger than the correct distance, but there can be some other nodes on this path from S to v which have the same property, which are broken. And so let uv the first node if counting from S on this path, which is broken in the same sense. Then u is definitely not the same as s, because for s we know that the dist value is 0 and the correct distance is 0. So u is at least the second node on the path, or maybe much later there. So there is some previous node on this path before u, and let's denote it by p. And let's look at s, p, and u. What we know is that p is not a broken node, and so its dist value is the same as the distance from origin to this node p. And so we know that the distance from S to U is actually equal to the distance from S to P plus weight of the edge from P to U. Why is that? Because the part of path from S to U is optimal, because it is a part of an optimal path from S to V. And also part of path from S to P is also optimal, and so this equality is true, that distance from S to U is equal to distance from S to P, and then add to it weight of the edge from P to U. But we also know that distance from S to P is equal to dist value of P, and so the second equality is true, that it is equal to dist value of P plus weight of the edge from P to U. But we also know that node U is broken, and the dist value of U is strictly bigger than the correct distance from S to U, which we know is equal to dist value of P plus weight of the edge from P to U. But this inequality is exactly the property we check to determine whether an edge from P to U can be relaxed or not. And so from one hand we know that this edge can be relaxed, and from another we know that we cannot relax any more edges in our graph, and our naive algorithm stopped, and this is a contradiction. So now we've proved by contradiction that our naive algorithm returns correct distances from origin node to all the nodes in the graph. We won't analyze the running time of this algorithm, because in the next video we will improve this algorithm and then we will estimate its running time. Hi, in this video you will learn Dijkstra's algorithm, which is an efficient algorithm to find shortest paths from origin node in the graph to all the nodes in the graph with weighted edges, where all the weights are non-negative. First, let's improve our intuition. So let's say we are in the node S, and this is the origin node. What we know exactly is that the distance from this node to itself is 0. We don't need to see anything else to decide that, because all the edges are non-negative, so it's better just to stay in S, and this is the shortest path from S to itself. Okay? So now let's look at all the edges outgoing of node S. And let's relax all those edges. So now we see that there are edges of length 5 and 10, and they go to nodes A and B, and so we can determine that the dist value of A is 5 and the dist value of B is 10 after relaxation. Now, if there are no more edges outgoing from S, we already know that the distance from S to A is exactly 5, because we cannot go around it and spend less time. So we're sure about distance for A. So now let's relax all the edges from A, and we will see that the distance to B will improve, and the distance to B becomes 5 plus 3, which is just 8. And also we'll discover two more nodes, C and D, and we will relax the edges from A to them, and C will get an estimate of 12, because it's 5 plus 7, and D will get an estimate of 6, which is 5 plus 1, which is the weight of edge from A to D. So now the question is, what is the next node for which we already know the correct distance for sure? And this node is D, because it has the smallest dist value estimate, and it means that there is no way to go around it. We can go directly to it from S through A in distance 6, but if we go through any of the other nodes, it will take us at least 8 to get there, and also some non-negative amount after that. So we cannot really improve this dist value estimate of 6. So we now know exactly that distance to D is 6, and we can continue by relaxing edges from D. While for B and C, it is still possible that their dist values are larger than actual distances. For example, if there is an edge from D to B of length 1, then the dist value of B will improve even better, it will be 7. And if we get an edge from D to C of length 1, then the distance to C will be just 7 also, which is much less than 12. So now we have this intuition that at any moment of time, if we've relaxed all the edges outgoing from some known set of nodes for which the distances are already known correctly, then the node with the smallest dist value estimate is also a node for which we know the distance correctly. So the main ideas of Dijkstra's algorithm is that we maintain some set R of vertices for which dist value is already set correctly. We call this set R a known region, and initially we only have node S, the origin, in the set R, because for this node we definitely know that the distance to it is 0. And then on each iteration we take the node outside of this region with the minimum dist value out of all nodes in this outside region, and we add this node to the known region and relax all the outgoing edges. And so after a number of iterations, which is equal to the number of nodes in the graph, we will know all the correct distances from origin to all the nodes in the graph. Let's see how it works in an example. So here we have 6 nodes, some edges, and the edge weights are written nearby the corresponding edges. And on top of each node and then under the bottom nodes we have the current dist value. So we start with infinities in all the nodes but the origin node to the left, which has dist value of 0. Now we add this 0 node to the known region, and we now know for sure that the distance from the origin to it is 0, and so we color the dist value by green because we are sure that this is the correct distance from origin to this node. And then we color our node in black and we start processing it. So we color nodes in black when we start processing them in the same way we did in breadth first search. Now we relax all the outgoing edges from this node. First we relax edge of length 3 and we improve the dist value from infinity to 3. And next we traverse edge of length 10 and improve the dist value from infinity to 10. Now what do we know? We know that the node with the minimum dist value outside of the known black region is the node with dist value of 3. So this node actually has a distance of 3, and we color the distance with green and the node with black, and we start processing this node. So we process the outgoing edges, first edge of length 8, which goes to the node with distance 10, but new estimate is 3 plus 8, which is 11, which is bigger than 10, so nothing changes because of this edge. And we also have an edge of length 3, and we improve the dist value from infinity to 6. And there is also an edge of length 5, which improves the dist value from infinity to 8. And now what we see is that the node with the minimum dist value is the node in the top right corner, which has dist value of 6. So we color it with black, color the distance to it with green, and process it. This edge gives us improvement from infinity to 8. This edge gives us improvement from 8 to 7. And this edge gives us an improvement from 10 to 9. Now the best node is in the bottom to the right and has distance 7. And it improves the distance estimate for the rightmost node from 8 to 7. And notice that there is an edge of weight exactly 0. This is allowed because 0 is non-negative. We only forbid the edges from being negative, but non-negative, including 0, is okay. So now we don't have any more outgoing edges from this node to the right in the bottom. And so we select the next node to process, which is the rightmost node with the estimation of 7. But we don't have any outgoing edges from it. So we process the last remaining node, which has distance of 9, and we can try to relax some edges, but they don't work because this is the farthest node from the start. So now we know all the distances from the origin to all the nodes in the graph, and this is how Dijkstra's algorithm works on this example. Now let's implement this algorithm. So the procedure Dijkstra takes again graph G and origin node S as inputs. It will also use dist values and pref values. It will initialize dist values with infinities, but for the origin node S, for which dist value is 0, and it will initialize pref values with pointers to nowhere. It will use also some data structure, which can be an array or a priority queue. Depends on your choice of data structure, and the running time will depend heavily on that. But anyway, this is a data structure for which we need just 3 operations: to create it from a set of dist values, to extract the minimum value from it, to get the node outside of a known region with the minimum dist value, and to change the dist value of some node which is currently in this data structure. So we will talk later about which data structure to choose, but for example, we can use an array here. Just create an array from all the dist values and then work with it. So while this data structure is not empty, we take out of it the node with the minimum dist value. And this data structure will contain only those nodes which are not in the known region. So it will contain initially node S and all the nodes, but then after we make the first iteration, we will extract node S from this data structure H, because node S has dist value of 0 and all the other nodes has dist value of infinity, so node S has the minimum dist value. So we extract minimum from it, which means that we take the node with the minimum dist value and we remove it from the data structure. And then we process this node U. Basically, we take all the outgoing edges from U in the graph and we try to relax them. To relax them, we check if it's possible to relax the edge, and if it's possible, we update the distance to the end of this edge, the dist value to the end of this edge. We update the pref value of this node V, and most importantly, we change the priority of this node V in our data structure H. What it means is that we improved the dist value for this node V, and now this node could become potentially the node with the minimum dist value, for example. So we need to account for that. So in our data structure, we need to do something. For example, if we store everything as an array, we just need to decrease the value of this array corresponding to node V. And then if we store everything as in an array, then when we do extract min, we just go through all the values of this array and find the minimum value and the node corresponding to this minimum value. So this all happens while our data structure is not empty, but basically it will happen at most number of nodes times, because it starts with all the nodes in the data structure, and then it just extracts next node each time, and the size decreases one by one. Now let's prove that Dijkstra's algorithm actually finds correct distances from the origin node to all the nodes in the graph. And the lemma states that when a node is selected as the node with the minimum dist value out of all nodes outside of the known region, its dist value is actually equal to the correct distance from origin to this node. Let's prove that, and again by contradiction. So let's assume this rule is broken at some point. Let's select first such moment. So at this moment we have some known region R, which contains node S and maybe some other nodes colored in black. And all the nodes colored in white are outside the known region, so C, D, E, F, and G in this case. And they have some dist values, which are written in blue near the corresponding nodes. What will happen next is node C will be selected as the node with the minimum dist value out of all the nodes outside known region. And we suppose that this dist value of 6 is wrong. What we know about dist values is that they are upper bounds on the correct distances. That is, if we have some dist value, then we can also show some path of exactly the length equal to this dist value. And so the shortest path to this node is less than or equal to this dist value. So there can be only two cases. Dist value is equal to the correct distance, but we assume it is not. And in this case, it is strictly bigger than the correct distance. So we know that dist value of 6 is strictly bigger than the length of the shortest path from origin to node C. Now let's think about this shortest path. It starts in the node S, which is inside known region, and it ends in the node C, which is outside of the current known region. So there is some edge which goes from inside known region to outside of the known region in this shortest path. Let's consider this edge. This can be an edge, for example, from B to F. It can also go directly into C. That doesn't matter. What matters is what happens next. After it goes from known region to outside, it also goes through some path of non-negative length, or maybe this path is empty if the edge from known region to outside of it goes directly into C, but anyway, this rest of the path is non-negative. What it means that if we just consider the first part of this path, which ends in the end of the edge from known region to outside, then this part of the path is also strictly less than the dist value of C, strictly less than 6. So we know that there is a path which goes from S, goes somewhere inside the known region, and then goes outside, and its length is strictly less than 6. But it means that actually some of the edges, it means that this edge could be relaxed in the current situation, because we know for sure that the distance estimate for node B is equal to the shortest path from S to B, because the first moment when this rule breaks is with node C. It was not broken with node B. Okay? So the distance estimate of node B is exactly equal to the shortest path from S to B. When we add the length of the edge from B to F to it, we will get the same thing as we get when we go by shortest path from S to C, but take only the part of it which ends in the node F. So if we add to the dist value of B the value of the length of the edge from B to F, we will get value which is strictly less than 6. And so it is strictly less than the dist value of F, because dist value of F is greater than or equal to the dist value of C. So we could relax this edge, but we didn't do it for some reason. But we know that we've relaxed all the edges from the known region to outside of the known region. So this contradicts our algorithm. And this contradiction proves that this rule is actually not broken. And when we select the node with the minimum dist value outside of the known region, its dist value is actually equal to the correct distance from origin to this node. And this proves that Dijkstra's algorithm finds correct distances from the origin to all the nodes in the graph. Now let's estimate the running time of Dijkstra's algorithm. So in the beginning it just initializes dist values and pref values, and that takes time proportional to the number of nodes, but our estimate will be bigger than that, so we just ignore this part. And other than that, it creates a data structure to store dist values and extract minimums from it. It extracts the minimum node from this data structure v times, where v is the number of nodes in the graph, and also it examines the edges. Each edge is examined at most once when the start of this edge is processed, and during processing it updates dist value, pref value, and changes priority in the data structure. Updating dist value and pref value is constant time, so the main part is in the change priority part. So now this running time estimation depends on how do you actually implement the data structure, from which you do extract min, change priority, and which you build by make_u. One way to implement it is just using an array. Actually, we'll need two arrays. First array is just of size v, where you store in the cell number I, you store the dist value of the node number I. But you also need to remove nodes from this array, so we'll use another Boolean array where you store a flag, whether this node is still in the data structure or it is not already. So to build such arrays, you need time proportional to the number of nodes, because you just basically write down these values for all the nodes and you write all the flags, you say that they are true. Then each extract min operation in the array takes time proportional to the number of nodes, because you need to go through the whole array, check whether this particular node is considered to be in the data structure or not. Just look up in the second array, and then if it is, then try to improve the minimum. And after you found the minimum, you just mark the flag as false, that this node is not longer in our data structure, and you take the minimum value from the array. So each extract min operation works in time proportional to v, and we make it v times, so this is v squared time. Now, change priority operation is very easy in case of array, because to change priority you just need to change the dist value of one node. So you just get the number of that node and you just change the value in the first array corresponding to that node. So that takes constant time. And so in this case the total complexity is v plus v squared plus e. And v squared is bigger than v, obviously, and also v squared is bigger than or equal to e, because there can be at most one edge between each pair of nodes. So v squared is the leading term, and so our running time is big O of v squared for the array implementation. And there is another way to implement this data structure using a binary heap or priority queue built on top of binary heap. We know that to build a binary heap from an array of size v, we need time proportional to v. We know that extract min works in logarithmic time, so the total time for extract min will be v log v. And the tricky part is change priority. Change priority operation can be implemented in the binary heap, but it is a little bit tricky. So instead of implementing additional operation in the binary heap, we can actually cheat. And we can just insert a new element in the heap each time we need to decrease the dist value for some node. So we need to improve our dist value, and to improve it means to decrease it. And what we can do is we can just insert another element, a pair of a node and its dist value estimation, into the priority queue. So then when the time comes to extract that node, the pair with the minimum dist value will be selected, and you will extract it with the minimum dist value which was found by this time. And if at some other point of time you will also try to extract this same node but with different dist value, you can just ignore it. You can just write down that you've already processed this node, and so if you extract it again from the queue, you just don't do anything with it. So this will increase the size of the heap, and so the operations will be slower a little bit, but they won't be much slower, because how many elements can be in the end in this priority queue? It will be no more than the number of edges, because each time you change priority, you examine some edge, and you examine some edge at most once. So total number of change priority operations is a number of edges, and so you will add at most e new elements in the heap in addition to the values which were there initially. And we know that e is at most v squared. So logarithm of e is on the same, is like at most 2 logarithms of v, because logarithm of v squared is just 2 logarithms of v. So the last part, the total time for change priority, is proportional to e multiplied by logarithm of v. And the final estimation is v plus e logarithm v, which is much better than v squared in the case when there are not too many edges, because if there are very, very many edges, like on the order of v squared, then this will be equal to v squared log v, which is worse than in the case of array implementation. But if the number of edges is much less than v squared, if the graph is far from being full graph with all the edges, then this can be much, much faster than the array-based implementation. In conclusion, you now know the algorithm to find the minimum time to get from work to home, for example, and actually you also know the algorithm to find the fastest route itself, because the reconstruct path algorithm will be the same as you had in the breadth first search, because you have the same pref values and you can just reconstruct the path from them. And you know that this algorithm works for any graph with non-negative edge weights, so you can not only find fastest routes, but you can also find shortest routes and routes which are minimum in some other senses. And you know that it works either in time quadratic in number of nodes in the graph, or in time v plus e log v, depending on the implementation, either array-based implementation or binary heap-based implementation. Hi! In the previous lesson, you learned to find shortest paths in the graphs with non-negative edge weights. In this lesson, you will learn to find shortest paths even in the graphs where some of the edge weights can be negative. We will explore that using a problem about currency exchange, which doesn't seem to have anything to do with shortest paths, but we will soon find out it does. So the problem about currency exchange is that you are given some possibilities that you can convert one currency into another, for example, US dollars to Russian rubles, or rubles to euros, or euros to Norwegian crowns. And what you want to do is to take your initial $1,000 and convert it into Russian rubles, potentially doing many conversions on the way, such that you get as many Russian rubles as you can in the end. So one question is, what is the maximum amount of rubles you can get? And another question is actually, can you get as many as you want? And the same question about US dollars, can you get as many US dollars as you want? It may seem that if you can get as many rubles as you want, then you will also be able to get as many dollars as you want, but that's not always the case. It depends on your restrictions. For example, if you lived in the USSR, you might be able to get some rubles for dollars you got from your foreign country trip, but it's very unlikely you could buy some dollars inside USSR. So in this problem, we assume that you have some restrictions on which directions you can convert currencies and what are the rates. So this is an illustration from Wikipedia article called Triangular Arbitrage, which illustrates the fact that sometimes it is possible to make 3 trades and exchange first dollars to euros, then euros to Great Britain pounds, and then pounds to US dollars, so that you generate some profit. In this case, given $5 million, you generate a profit of 25,000 just by doing those three trades. These triangular arbitrages exist very rarely and only due to some market inefficiencies, but in theory this is possible. And this example has some numbers on the edges. For example, the rate of conversion from dollars to euros is 0.81, and you get 1.19 euros per British pound, and you get 1.46 dollars per British pound. So given these conversion rates, and of course those should also account for commissions and any other money that you actually don't get. So given those numbers, you can determine exactly how many dollars will you get from 5 million initial if you do all the trades shown on the picture. So we will be discussing this problem, how much you can get of each currency, and if it's actually possible to get more of the currency you had initially doing some trades. So how does this conversion work? If we have some path, if we convert first dollars to euros, then euros to pounds, then some other conversions, then we come to Norwegian crowns, and then we finally convert them to rubles, then how many rubles do we get per $1 US? Well, it is determined by the product of the conversion rates written on the edges. So for example, if for $1 we get 0.88 euros, and for €1 we get 0.84 pounds, and so on, and for 1 Norwegian crown we get 8.08 rubles, then for $1 US we will get the product of all those numbers in rubles. That's how conversion rates work if you account again for commissions and other payments in each trade inside this number which you write on the edge. So what are the possibilities for exchanges? It may look that there is only one way. You can just convert from dollars to rubles, or maybe use some intermediate currency, but actually there is an infinite number of possibilities. For example, in this particular case, you could exchange dollars to euros, euros to pounds, pounds to dollars, and go through this cycle for as many times as you want, then convert to rubles, or convert to euros and then to rubles. So there are many possibilities, and the result of each such path through the graph is the product of the numbers written on the edges of this graph. So the problem formulated in mathematical terms is that you're given a currency exchange graph with weighted directed edges denoted by EI between some pairs of currencies. Maybe you can convert some pairs of currencies, but you're not able to convert some others, and this graph doesn't have to be symmetrical or undirected, so it is possible that you can convert dollars to rubles, but not vice versa. And each edge has a conversion rate corresponding to this pair of currencies, and it is written as a weight of this edge, R with index EI. And what you want to do is to maximize the product of the weights of the edges over all possible paths, and potentially infinite number of paths, from the node corresponding to US dollars to the node corresponding to Russian rubles in this graph. Okay, and we could substitute these two currencies by any other pair, it doesn't matter. So now we want to reduce this problem to the problem about shortest paths, and we will do that using two standard approaches. First, we don't know what to do with products, so instead of products of weights, we want sums of weights, like in the shortest paths problems, and we will replace products with sums by taking logarithms of weights, and I will show that in a minute. And another problem is that we need to maximize something in this problem, while shortest paths are all about minimizing. So we'll have to also negate weights to solve minimization problem instead of maximization. So first let's talk about taking the logarithm. It is a known rule that x for any x is the same as 2 to the power of logarithm of x over 2. So we can take any product of two numbers like x and y and rewrite x as 2 to the power of logarithm of x and y as 2 to the power of logarithm of y. And then it is equal, xy is equal to 2 to the power of logarithm of x by 2 to the power of logarithm of y. And now we know the rule of summing the powers. So this is equal to 2 to the power of logarithm of x plus logarithm of y. And so if we want to maximize product of x and y, this is actually the same as maximizing the sum of logarithm of x and logarithm of y, because if the sum becomes bigger, then 2 to the power of the sum becomes bigger, and if the sum becomes smaller, then 2 to the power of the sum becomes also smaller. This is true not only for two numbers. For example, if we have three specific numbers, 4, 1 and 1 over 2, which want to multiply, on one hand we get 2, which is 2 to the power of 1, and on another hand, if we sum up the logarithms of 4, 1 and 1/2, we get sum of 2, 0 and minus 1, and the logarithms can be both positive and negative. They're positive when the number is bigger than 1, and they're negative when the number is smaller than 1, and they're 0 when the number is equal to 1. So in this case we get the sum of 1, which is the same as the power to which we exponentiate our 2. So you see that it works not only for two numbers but also for several numbers, and in general, to maximize the product of k numbers r with indices ej, it is the same as to maximize the corresponding sum of logarithms of these numbers. And note that this only works if all these numbers are positive, because we cannot take logarithms of negative values and we also cannot take logarithms of 0. But if all the exchange rates are positive numbers, hopefully, then we can just take logarithms and we reduce our problem from maximizing product of some numbers to maximizing sum of some numbers. Now we want to go from maximization to minimization, but that is easy. If we want to maximize sum of logarithms, it is the same as minimize minus this sum. And we also want to work just with the sum, not with the minus sum, so we can insert this minus inside the summing operator. And so finally we get that maximizing the sum of logarithms is the same as minimizing the sum of minus logarithms. Joining those two ideas, we get the following reduction. We replace the initial edge weights, conversion rates, REI by minus logarithm of REI, and we find the shortest path between the node corresponding to US dollars and the node corresponding to Russian rubles in the graph. And this is equivalent to the initial problem about how many rubles you can get from $1,000. So now it looks like we've solved the problem, because we can create the currency exchange graph with the conversion rates, we can replace those weights with minus logarithms, and we can find the shortest path from US dollars to Russian rubles using Dijkstra's algorithm, which we learned in the previous lesson. And then we can just do the exchanges corresponding to the shortest path in the graph which we found. However, that doesn't exactly work, because Dijkstra's algorithm heavily relies on the fact that the shortest path from S to T goes only through vertices that are closer to S than T. And this is because the edge weights are positive. But if edge weights can be negative, this is no longer the case, and the example is below. If we used Dijkstra's algorithm, as soon as it saw only two edges from S to A and to B, one of them with weight 5 and another with weight 10, it would decide that the shortest path from S to A is exactly 5, because we cannot improve it. But in this example we can improve it. We can go from S to B and then from B to A, and the path will be already minus 10, which is much less than 5. So Dijkstra's algorithm doesn't work in such cases. Such example is also possible in the currency exchange problem. Here is a graph with realistic conversion rates between rubles, euros and US dollars. And our goal is to convert rubles in the US dollars in the most profitable way. And it turns out that if we take minus logarithms of these conversion rates, then although the number on the edge from rubles to US dollars is less than the number from rubles to euros, it is still beneficial to go through euros to US dollars because of the negative edge between euros and US dollars. And it's really true that if we multiply the conversion rate between rubles and euros and then between euros and dollars, it will be slightly bigger than if we convert directly from rubles to dollars. So all problems in the graphs with negative weights come from negative weight cycles. For example, in this graph we have a negative cycle A, B, C. What it means is that we can go from A to B, then from B to C, then from C to A, and if we add those weights we get -1. So the sum of the edges on the cycle is negative. And because of that, if you want to convert, for example, from S to A, if you want to go from S to A and find the shortest path, this is not possible because we can go from S to A and use distance of 4, but then we can just go around the cycle ABC, ABC, ABC many times, as many as we want, and the distance will only decrease. So the distance from S to node A is actually -infinity, it's not defined. You can do as short a path as you want. And the same is true about nodes B and C, of course, because they're on the cycle, so you can do the same thing with them. And the same is also true about node D, because it is reachable from the cycle. So you can go to the cycle, then make a lot of round trips on this cycle, and then go to node D either from B or from C. So all these nodes are the infinitely close to S, like the shortest path is -infinity. And it turns out that in the currency exchange problem, a negative cycle can potentially make you a billionaire if you are lucky and if you have enough time for that. But you will learn how to do that a little bit later in this lesson. Hi, in this video you will learn Bellman-Ford's algorithm, which is an algorithm for finding shortest paths in graphs where edges can have negative weights. Actually, do you remember the naive algorithm from the previous lesson about Dijkstra's algorithm? Turns out it's not so naive, and Bellman-Ford's algorithm is almost the same as the naive algorithm. So that naive algorithm just relaxed edges while dist changed, and at some point it stopped. We didn't estimate the running time of that algorithm, but it turns out that this algorithm has a benefit over Dijkstra's algorithm, that it works even for negative edge weights. It is a little bit slower than Dijkstra's algorithm, but it works in graphs with any edge weights. So here is Bellman-Ford's algorithm, and it takes as input graph and origin node again, and we'll find shortest paths from this origin node to all the nodes in the graph. And there is an additional comment that this algorithm assumes that there are no negative weight cycles in G. Otherwise it will work still, but it won't return correct distances for some of the nodes. So if you know that there are no negative weight cycles in G, this algorithm will give you the answers you need. If there are negative weight cycles, we'll discuss later what to do in this case. So this algorithm uses the same dist values and pref values as BFS and Dijkstra's algorithm. It initializes them the same way, infinity for distances apart from the origin node S, and prefs just point to nowhere. And then we repeat exactly v minus 1 times. V is the number of nodes in the graph. We relax all the edges in the graph in order. So this is the Bellman-Ford's algorithm. And actually, this repeat v minus 1 times is excessive. Actually, we can just return to the naive algorithm interpretation when it repeated relaxation of all the edges until no relaxation is possible. So this can be done, and this will even work faster than Bellman-Ford in the case where there are no negative weight cycles. However, we write this pseudocode in this form just because it is easier to prove the algorithm's correctness this way, but you can just know that if at some iteration during these v minus y iterations nothing changed, no edge was actually relaxed, you can just stop there and the distances will already be correct. Now let's estimate the running time of this algorithm, and I state that it's proportional to the product of number of nodes and number of edges. So that is longer than Dijkstra's algorithm, which was v squared in terms of array-based implementation, and even e plus v log v in terms of heap, binary heap implementation. So this is longer than that, but it works with negative edge weights, so it's good. So initially we just initialize dist and pref values in time proportional to number of nodes, and then we do v minus 1 iteration. Each iteration takes time proportional to the number of edges because relaxation is a constant time procedure. So totally we get time proportional to VE. And now we'll look at an example of how Bellman-Ford's algorithm works on a real graph. So the origin node is again S, and the numbers 0 and infinity in blue are the dist values, and the numbers near the edges are the edge weights. So what we do is we take all the edges in order, starting from the edge with weight 4, and we try to relax it, and we improve the dist value for A from infinity to 4. We take the next edge with length 3, and we improve the dist value of B from infinity to 3. We take the edge with weight minus 2, and we further improve the dist value for B from 3 to 2. Then we consider edge from A to C and improve infinity to 8. Then we consider edge from B to C and improve it further from 8 to minus 1. Then we consider edge from B to D and improve from infinity to 3. And we consider the edge from C to D and improve from 3 to 1. This is just one iteration of Bellman-Ford's algorithm. Now let's see what happens on the next iteration. We consider edge from S to A, it doesn't improve anything. This edge doesn't improve anything. This edge doesn't improve, this edge also doesn't improve, and this doesn't improve, and this doesn't improve, and this doesn't improve. And so already on the second iteration, nothing can be improved. So we actually can stop the algorithm just after one iteration, and it will take, instead of VE operations, just E operations, because we made just one iteration over all the edges, and often it will work just this way in practice. But for some graphs, of course, we will need many more iterations. So now we already know the final distances that the Bellman-Ford algorithm returns. And in the next video, we'll prove that this algorithm returns correct distances in the absence of negative weight cycles. Hi! In this video, we will prove that Bellman-Ford's algorithm returns correct distances from origin node to all the nodes in the graph in the absence of negative weight cycles. First, we need the following lemma. After k iterations of relaxations inside Bellman-Ford's algorithm for any k, then if we take any node u, dist value of u after these k iterations will be equal to the shortest path length from S to this node u, but among all the paths that contain at most k edges. So not all the possible paths, just paths which contain 0, 1, 2, or at most k edges. For example, after one iteration, we state that dist values of all the nodes will contain the best possible shortest path, which consists from 0 or 1 edges. We'll prove this lemma by mathematical induction, and the base case is after 0 iterations. All the dist values are infinity, and dist value of S is 0. And this is correct, because for S there is a path of 0 edges, which has length 0, and correct distance from S to S is 0, and dist value is also 0. And for all the other nodes, there is no path that contains 0 edges, and so the shortest path that contains 0 edges and goes to those nodes is infinity. Now the induction step is, if we proved for paths with length at most k, then we need to prove it for paths with length at most k plus 1. So we know that before iteration number k plus 1, dist value for u is the smallest length of a path from S to u which contains at most k edges. So what do we do on the k plus 1th iteration? Each path from S to u goes through one of the incoming edges, like from some node v into node u. And also paths of length k plus 1 go this way. They go k edges to some node v, and then they go through this edge from v to u. So when we try relaxing edge from v to u, we compare the current dist value, which is the smallest path length out of the path which contain at most k edges. We compare it with the smallest length of the path from S to u, which contains at most k plus 1 edge and goes through v. So all paths which contain at most k plus 1 edges and go to u, they go through one of the incoming edges, vu, and so we will compare with all the possible paths that contain at most k plus 1 edges and go from S to u. So if initially we had the best paths which contain at most k edges, after new iteration we have the best paths which contain at most k plus 1 edge, because we add one last edge from v to u to the best path which contains at most k edges from S to v. So the lemma is proved, and now we have two corollaries. First, that if a graph doesn't have any negative weight cycles, then Bellman-Ford algorithm correctly finds all distances from the starting node S. Why is that? Because it does v minus 1 iterations, and after v minus 1 iterations, for each node, its dist value contains the shortest path out of all paths that contain at most v minus 1 edges. But if there are no negative cycles, then any path, any shortest path, contains at most v minus 1 edge. Because if it contains at least v edges, then there will be a cycle inside it, and the cycle will be non-negative. So we can just remove this non-negative cycle from the path, and it will improve or stay the same. So any shortest path contains just v minus 1 edges or less. And so Bellman-Ford algorithm correctly finds the best shortest paths for each node. Another corollary is harder. Even if there is a negative cycle in the graph, that doesn't mean that there is no correct distance estimation from origin to some particular node, because that particular node may be not reachable from any of the negative weight cycles. So if there is such node u that there is no negative weight cycle from which it is reachable, then Bellman-Ford algorithm will correctly find distance from S to this node by the same reason, because if we have any shortest path from S to u, it cannot contain cycles because u is not reachable from any negative weight cycles, and so the cycle on the path from S to u must be non-negative, and so we can just remove it from the path, and the path will improve or stay the same. So any path from S to u doesn't contain cycles, and that means that any path from S to u, which is the shortest path, has at most v minus 1 edges, and this means that Bellman-Ford's algorithm will return actually correct value for the distance from S to u. And in the next video we will look into what to do with the negative cycles when they are present in the graph, and how to use it for your own profit, potentially making yourself a billionaire based on currency exchange. Hi! In this video you will learn to deal with negative cycles in the graphs. You will learn to detect whether there is a negative cycle in the graph, and to find a negative cycle if you know there is one. And you will use that in the next video to achieve infinite arbitrage. But before that, you really need to learn to detect negative cycles in the graphs. And this lemma will help you. So it says basically that there is a negative weight cycle in the graph if and only if you make one additional iteration of relaxation in the Bellman-Ford's algorithm and some edge is relaxed. First, let's prove that if there is some change in the last step of Bellman-Ford's algorithm, then there is a negative cycle. Assume, for the sake of contradiction, that there are no negative cycles. Then it means that all shortest paths from S to any node in the graph contain at most v-1 edges. We've already discussed that. If they contain at least v edges, then there is a cycle, and this cycle is non-negative, so it can be removed, and the path will be either improved or just stay shortest path. So no dist value can actually be updated on iteration number v, because we already found the optimal shortest path length with paths that contain at most v-1 edges, and we cannot improve anything after that. So this is a contradiction with the fact that the last iteration actually relaxes some edge, and so if it does, then there is a negative cycle in the graph. Now let's prove in another side that if there is a negative weight cycle, then there will be a relaxation on the iteration number v. Suppose, again, for the sake of contradiction, that there is a negative weight cycle, for example, a cycle of length 3, A, B, C, A, but there are no relaxations on the iteration number v. Now let's look at the following three inequalities. These inequalities basically state that edges AB, BC, and CA cannot be relaxed on the vth iteration. But if we sum these inequalities, on the left side we will have sum of dist values for A, B, and C, and on the right part we will have sum of dist values of A, B, and C plus sum of weights of the edges of the cycle. And from this sum of inequalities it follows that the sum of the weights of edges is non-negative. But we know that the cycle is a negative weight cycle, so this is a contradiction. And so we proved by contradiction that there will be some relaxation on iteration number v. So we proved our lemma, and now we know how to detect negative weight cycles in the graph. We just do one additional iteration of Bellman-Ford's algorithm, and it doesn't increase its asymptotic complexity, its running time. And now we can determine whether the graph is good or bad, whether it contains negative cycles or not. Now we want not only to detect whether there is a negative cycle or not, also want to find some negative cycle itself, at least one. Maybe there are many of them, but we want some negative cycle. So first we still need to run exactly v iterations of Bellman-Ford relaxation. And as we know, if there is negative cycle, then for some node v, it will be relaxed. Its dist value will be decreased on the last iteration. So save this node, and I state that this node is definitely reachable from a negative cycle, because if it was not reachable from the negative cycle, then any shortest path to this node will contain at most v-1 edge, and it won't be improved on the iteration number v. So it is reachable from a negative cycle, and also it is reachable from a negative cycle with at most v steps, because if you have a shortest path from S to v, which contains negative cycle inside, even if there are more than v edges from this negative weight cycle to v, then there is another cycle on this shortest path, and it also has to be negative, because otherwise we can remove it from the shortest path. So v is definitely reachable from a negative cycle with at most v steps. And we remember the previous node from which each node was updated last time. We store it in the pref values. So if we go by pref links from v, and we do that at least v times, we will be already definitely on this negative weight cycle, because we will already return to the cycle by at most v steps, and then we'll just go around this cycle for some amount of iteration. So if we go by v times back, we will be on the negative cycle. And then the only thing we need to do is just to save the position where we started, and then go once around the cycle until we come to the same node, and we will know that the nodes we saw during this round trip are the nodes of the negative cycle. So this is the algorithm, and it works in the time of Bellman-Ford's algorithm plus proportional to the number of nodes. So basically the same running time as Bellman-Ford algorithm. So now the question is, again, if you have a negative cycle in your graph of minus logarithms, does it mean that it is always possible to get as many rubles as you want from $1,000? And unfortunately, that's not always the case. For example, in this graph, there is a negative cycle between euro, British pounds, and Norwegian crowns. And you can check that if you multiply the conversion rates on the edges of this triangle, you will get more than 1, and it means that for €1 you can get more than €1. And this means in turn that you can get infinite arbitrage if you just make trades along the edges of this triangle for as many times as you want. But there is no possibility in this particular example to exchange euros for dollars. So you cannot exchange rubles for euros, then make many loops around this negative weight cycle, and then exchange euros to dollars. So this is not sufficient, and you cannot actually get any dollars from rubles. You cannot get any rubles from dollars in this particular case. And in the next video, you will learn how to determine whether it is possible to have an infinite arbitrage from rubles to dollars or from any other currency to any other currency, and not only to detect that, but to actually find a way to implement it if it's possible. Hi! In this video you will finally learn how to detect whether infinite arbitrage from some source currency to some target currency is currently possible. And not only that, you will also learn how to actually implement it if it is possible. But first, let's learn a criterion for the existence of infinite arbitrage. The lemma states that if we consider some source currency S, which we want to exchange into some target currency U and get as much as we want of currency U from a unit of currency S, then it is possible if and only if the node U corresponding to the currency U in the currency graph is reachable from some node W, which was relaxed on iteration number big V, where big V is the number of nodes in the currency graph, or just the number of different currencies which we consider. So we run the Bellman-Ford algorithm for exactly big V iterations, and if some node W was relaxed on the last iteration, and some node U is reachable from it, then it is possible to get as much as you want of U from the source currency S, and vice versa. If it is possible to get as much as you want of currency U, then it must be reachable from some node W, which is going to be relaxed on the last iteration of the Bellman-Ford's algorithm. So let's prove this lemma. First, we prove that if some currency U is reachable from W, which was relaxed on iteration number V, then the infinite arbitrage is possible. To see that, first note that as W was relaxed on iteration number V, then we know from the previous video that W is reachable from some negative weight cycle, which in turn is reachable from the node S. It corresponds to the picture on the slide, and so we can get as much as we want of currency W from currency S, because we can go from S to the node X of the negative cycle, which is reachable from S, then go as many times as we want through the negative cycle, return to the node X, and then go from this node X to node W, and using this way we'll get as much as we want of currency W. And then we know that U is reachable from W, we know that W is reachable from the negative cycle is reachable from S, so we can use this whole way from S to negative cycle, then go through the negative cycle as many times as we want, then go to W from there, then go from there to U, and this way we'll get as much as we want of currency U. So infinite arbitrage is actually possible. Now let's prove the other way around, that if we can get as much as we want of currency U from currency S, then U must be reachable from some node W, which is going to be relaxed on the last iteration of the Bellman-Ford's algorithm. So first, let L be the length of the shortest path from S to U with at most v-1 edges. Then we know that after v-1 iterations of the Bellman-Ford's algorithm, dist of U is equal to exactly L. And we know that exists infinite arbitrage from S to U, and so there exists some path shorter than L, strictly shorter, because we can get path for any length which is arbitrarily small, and so in particular there exists a path which is shorter than L. And so the dist of U will be decreased at some point. It will become less than L also. But we know that by the iteration number v-1, it is still equal to L. It is not less than L. So it will be still decreased even more on some iteration after iteration v-1. So it will be decreased either on iteration number v or on some of the further iterations. Now let's note that if at some point some edge from node X to node Y was not relaxed, and also node X was not relaxed itself, then edge XY will not be relaxed on the next iteration, because nothing has changed. The dist of X is the same, and dist of Y is not bigger than dist of X plus length of edge XY, and this didn't change from this iteration to the next iteration, so this edge won't be relaxed on the next iteration. And this means that if node Y was relaxed at some iteration, then there is some node X from which there is an edge to this node, and this node X was relaxed at some previous iteration. So basically only those nodes which are reachable from nodes relaxed on previous iterations can be relaxed at the current iteration. And so we know that the node U will be relaxed at some iteration starting from iteration V and further. And this means that U is reachable from some other node, or maybe the same node, but from node which was relaxed on the iteration number V. Note that U can be this node. For example, U can be relaxed exactly at iteration number V. And as we consider node to be reachable from itself, then this is a particular case in which U was relaxed on iteration number V and U is reachable from itself, so it is possible to get infinite arbitrage to U. But in any case, we proved that if infinite arbitrage from S to U is possible, then U is reachable from at least some node, maybe the same U, which was relaxed on iteration number V. So now we have a criterion for existence of infinite arbitrage. How to apply that criterion? So this is an algorithm to detect infinite arbitrage. So we first do exactly V iterations of Bellman-Ford algorithm, and we save all the nodes which were relaxed on the last iteration, on iteration number V. And let this set of nodes be denoted by A. Now we'll put all the nodes from A into the queue, and we'll use this queue for a breadth-first search. So we will start our breadth-first search not from a queue which contains just the first node from which we want to know all the reachable from it, but we'll put all the nodes which were relaxed on iteration number V into the queue and then start breadth-first search. And then this breadth-first search will find us all the nodes which are reachable from at least one of the nodes from the set A. So those will be exactly those nodes for which infinite arbitrage is possible. So all those nodes and only those can have infinite arbitrage. And this is a way to find all target currencies for which infinite arbitrage from a fixed source currency S is possible. But this is not enough. What we want is to actually, if infinite arbitrage is possible, is how to actually implement it. And here is the next algorithm. So let's suppose we've already detected that the infinite arbitrage to some target currency U is possible. And we determined that using breadth-first search from the set A. So we need to augment this breadth-first search, and we will remember the parent of each visited node, so that when a breadth-first search discovers a new node, it discovers it from some node which was discovered previously, and this is the parent of this node. And this is what allows us to reconstruct the path from the source node to the end node in the regular breadth-first search algorithm. So we will do the same thing, and this will allow us to reconstruct the path to the target currency U from some node W, which was relaxed on iteration number V. Then we will use the algorithm from the previous video to find the negative cycle from which W is reachable, because we know that W was relaxed on iteration number V, and so it is reachable from some negative cycle, which is in turn reachable from S. And if we go back by the parent pointers from W, we will find this negative cycle. So we'll find both this negative cycle and the path from it to W. And of course, we can also find a path from the source currency to this negative cycle by, for example, launching a regular breadth-first search from S until we encounter some node of that negative cycle. And then combining all that, we will have a path from S to the negative cycle, through which we can then go by as many iterations as we want. Then we will go by a path from this negative cycle to W, and then we'll go by a path from W to U, which we already know. And that gives us a way to implement infinite arbitrage from the source currency S to the target currency U. So, in conclusion, we can now implement the best possible exchange rate in the case it exists and there is no infinite arbitrage. And we can determine whether actually infinite arbitrage is possible currently. And we can actually implement infinite arbitrage from a given source currency to a given target currencies. And in a more general and abstract way, we can find shortest paths not only in the graphs where all the edges are positive, like graphs of navigation systems with positive times to go through an edge and length of the edge, but also in the graphs where negative edge weights are possible, such as the graphs of currency exchange. So we can basically find shortest path correctly in any graphs with weighted edges. That's what we've learned in this lesson.
Hello and welcome to the next module, in which we will be talking about minimum spanning trees. To motivate the study of this problem, consider the following toy example. Assume that we have 6 machines in our office and we would like to join them into a network by putting wires between some pairs of them, such that any machine is reachable from any other machine. Assume further that we can put wires only between some pairs of our machines. And for each such pair, we know the corresponding cost of putting a wire between them. For example, in this case, we are allowed to put a wire between these 2 machines, and the cost is 5, and we are not allowed to join these 2 machines by wire. Okay? One of the optimal solutions in this case is shown here on the slide. It is not difficult to check that in this case, indeed, any machine is reachable from any other machine. For example, to reach the right machine from the left machine, we would go as follows. First by this edge, then by this edge or wire, and then by this edge. The total cost of the shown solution is equal to 2 plus 1, which is 3, plus 3, which is 6, plus 4, which gives us 10, plus 2, which gives us 12. So the total cost is 12. And this is actually not the only solution in this case, because instead of using this wire, we may use this wire. The resulting solution is shown here on the slide, and it is not, again, difficult to check that in this case any machine is reachable from any other machine, and that the total cost is equal to 12. We will soon learn 2 greedy algorithms that will allow us to justify that in this toy example the optimal total cost is indeed 12. These 2 algorithms will also allow us to solve very efficiently in practice instances consisting of thousands of machines. In our second example, we have a collection of cities and we would like to build roads between some pairs of them such that there is a path between any two cities and such that the sum of the length of all the roads that we are going to build is as small as possible. Okay? In this case, the solution looks like this, and again, we will soon learn how to find this solution efficiently. Formally, the problem is stated as follows. We're given a graph G with a set of vertices V and a set of edges E, and we assume that this graph is connected, okay, and it is given together with positive edge weights. What we're looking for is its subset of edges E prime, such that if we leave only these edges in the graph, then the resulting graph is connected, and also the total cost of all the edges in E prime is as small as possible. Okay? So why the problem is called minimum spanning tree? Well, minimum corresponds to the fact that we are looking for a subset of edges of minimum total cost or minimum total weight. Okay? It is called spanning because we're looking for a subset of edges such that if we leave only these edges, then the resulting graph is still connected. So it spans all the vertices in our graph. And finally, the word tree corresponds to the fact that in each solution, the set E prime is going to form a tree. We will prove this fact on the next slide. Before proving that any optimal solution for the minimum spanning tree problem, any optimal solution E prime forms a tree, let me remind you a few useful properties of trees. First of all, just by definition, a tree is an undirected graph that is connected and is acyclic. That is, it contains no cycles. Recall that we usually draw trees as follows. So we draw them level by level, and they look like this. Right, in this case, we're actually talking about rooted trees. So this is a rooted tree, and in particular, this is the root of this tree. At the same time, this graph is also a tree, with the only difference that there is no root in this tree, and it is not drawn level by level. So once again, this graph is also connected, and there are no cycles in this graph, so it is a tree. There is no root in this tree. However, we can take any vertex, declare this vertex as a tree, and then hang by this vertex, and then this will allow us to draw this graph level by level. Okay. The next property is that if we have a tree with n vertices, then it necessarily has n-1 edges. Why is that? Well, let me illustrate this by drawing some tree. Initially, we have just one vertex and 0 edges. So initially, the property is satisfied. The number of edges is equal to the number of vertices minus 1. Let's then introduce some new vertex. So we attach it by an edge to the previous vertex. Then we introduce another vertex, and probably another one, and so on. So each time when we introduce a new edge, or when we introduce a new vertex, we also add a new edge. So initially we had one vertex and 0 edges. We added 4 vertices, and now we have, 5 vertices. Now we have 6 vertices and only 5 edges. So still the property is satisfied. Note that we cannot introduce a new edge without introducing a new vertex. Because if we introduced a new edge, it would mean that we are connecting 2 existing vertices by an edge. For example, like this. But this will necessarily produce a cycle, which means that this will give us a graph which is not a tree. Okay? The next property is that actually any connected graph with the number of edges equal to the number of vertices minus 1 is necessarily a tree. Well, let me emphasize that it is important that here we are talking about connected graphs. Because, for example, if a graph has the property that the number of edges is equal to the number of vertices -1, but it is not connected, that it is not necessarily a tree. A counterexample is the following. Assume that we have 4 vertices and there is a cycle on 3 vertices and there is one isolated vertex. In this case, we have 4 vertices and 3 edges. Right? So this is not a tree, but at the same time, this graph is not connected. There is no path, for example, from this vertex to this isolated vertex. Okay? And the last property says that an undirected graph is a tree if and only if there is a unique path between any 2 vertices. And this is also not difficult to see. First of all, if we have a tree, then of course there is the unique path between any of 2 its vertices. On the other hand, if we have 2 vertices and there are at least 2 paths between them, then this gives us a cycle, which means that this is not a tree. Okay? Now let me get back to proving that any optimal solution to the minimum spanning tree problem is indeed a tree. For this, consider some toy solution. So in this case, we have 6 vertices, and consider some way of joining them into some way of connecting them. Assume that our solution looks like this. So you see that this is not a tree because there is a cycle on these 4 vertices. Well, in this cycle, for any 2 vertices in this cycle, there are two paths, right? Because, for example, for this vertex and for this vertex, we can go either this way or this way. And this is true for any cycle. If we have a cycle and 2 vertices on this cycle, we can either go this way or this way, right? And this means that there is some redundancy here. In this particular case, we can remove, for example, this edge from this cycle or from this solution. This will only decrease the total weight of this solution, and the resulting set of edges will still be connected. Right? This proves that any optimal solution must be acyclic. And since any solution is required to be connected, this proves that any optimal solution is in fact a tree. The goal of this whole lesson is to present 2 greedy algorithms for the minimum spanning tree problem. Before going into the details of these algorithms, let me present you the high-level ideas of both these algorithms. So the first one is due to Kruskal, and the second one is due to Prim. The high-level idea of the algorithm by Kruskal is the following. So we go through all edges in order of increasing weight, and we repeatedly add the next lightest edge, which doesn't produce a cycle. Alternatively, the main idea of the Prim's algorithm is to grow a tree repeatedly. So initially it contains just 1 vertex, then we attach a new vertex to it, then a new vertex to it, and we always attach the new vertex to the current tree by the lightest available edge. Let me illustrate this again on a toy example. So for Kruskal algorithm, we repeatedly add the next lightest edge that doesn't produce a cycle. Initially, our solution is empty, so we just add the first lightest edge. In this case, the lightest edge has weight 1, so we just put this edge into our solution. And there is also another edge which has cost or weight 1, so we also add it to our solution. The next one has weight 2, we add it. At the same time, the next lightest available edge has weight 3. However, if we added it to our current solution, this would produce a cycle. So we skip this edge. The next lightest available edge has weight 4. We add it because it doesn't produce a cycle. Then again, we try to add the edge with weight 5 because it is the next lightest available edge. However, it produces a cycle, so we skip this edge and instead we add the edge of weight 6. Right? This gives us a solution, and we will soon justify that this method indeed gives an optimal solution. Now to the Prim's algorithm, it works in a different way. So it repeatedly grows just one tree. For this, it first selects a root for this tree. So I assume that this highlighted vertex is going to be the root of the tree that we are going to construct. At each iteration, we are going to attach a new node to this tree, and we would like to do this by using the lightest possible edge. So for this vertex, we have four edges going out of this node. One of weight 4, one of weight 5, of weight 6, and of weight 8. In this case, we select, of course, the edge of weight 4. So we attach it. Now our tree contains two nodes, and we would like to attach a new node to this tree by a lightest edge. So in this case, this is the vertex in the middle, and it has weight. The corresponding edge has weight 1. So we attach it. The next one has weight 2. The next one has 6, and finally the last node is attached by an edge of weight 1. Right? So in the next parts of this lesson, we will present the implementation details of both these algorithms, but we first will prove that both these algorithms are correct, namely that they produce an optimal solution. Both the considered two algorithms construct the solution iteratively, namely they start with an empty solution, with an empty set of edges, and at each iteration they expand the current set of edges by one edge, but they use different strategies for selecting the next edge. Namely, the Kruskal algorithm selects the next lightest edge that doesn't produce a cycle, while the Prim's algorithm selects the next lightest edge that attaches a new vertex to the current tree. What we need to prove to show that both these algorithms are optimal is that these strategies are in some sense safe. Namely, if at the current step we have a subset of edges which we call E prime, which is a subset of some optimal solution, then by adding this edge according to one of these two strategies to this set gives us also a set of edges which is also a part of some optimal solution. This will justify that at the end, when we have a tree, this tree is also a part of some optimal solution, which means that this is just optimal. Okay, so in this video we are going to prove a lemma which is called cut property, which will justify that both these strategies are indeed safe. The formal statement of the lemma is the following. Assume that we have a graph G with a set of vertices V and the set of edges E. Okay? Together with this graph, we are given a subset of its edges that we call X. X is a subset, some subset of the set of edges of our graph, for which we know that it is a part of some optimal solution. It is a part of some minimum spanning tree. Okay? Assume also that the set of vertices is partitioned into two parts. One part is the set of vertices, is some subset of vertices S, and another part, all the remaining vertices are V minus S. Okay? So we are given also a set of vertices S. And this set of vertices S satisfies the following property. No edge from the set X joins two vertices such that one of them lies in the set S and another one lies in the set V minus S. Okay? No edge from the set X crosses between S and V minus S. Okay? Finally, assume that E, the vertex, the edge E of the initial graph satisfies the following property. It is the lightest edge that joins the vertex from S with the vertex outside of X, with the vertex from V minus S. Okay, E is the lightest edge across this partition. Okay, then what the lemma states is that if we add the edge E to our current set X, then what we get will also be a subset of some minimum spanning tree. In other words, adding e to x in this case is a safe move. So since this is a long statement, let me repeat it once again using a small example. So assume that this is our graph G. So we are given a graph G. Together with this graph G, we are given some subset of its edges, shown here on the slide in blue. It is the set X. Okay, so this is just subset of the set of edges of our graph, and assume that we know that it is a part of some minimum spanning tree. Okay, so the set X is a subset of some minimum spanning tree. Okay, then consider some partition of the set of vertices into two parts. So this is one part, and this is all the remaining vertices. This is the second part. And this partition is required to satisfy the following property. No edge from X, on our picture, no blue edge, joins two vertices from different parts. In this case, it is satisfied. Indeed, any blue edge here joins two vertices that lie in the same part, right? Next, we consider the lightest edge in our initial graph that joins two vertices from different parts. Assume that this edge is E, shown here in red. Then what lemma states is that if we add this edge to our set X, then the resulting set of edges will also be a part of some minimum spanning tree. Okay, so this tells that adding E to our current sub-solution, to our current subset, which we grow repeatedly by one edge, to the subset is a safe move. We now prove the cut property. This is our graph G, and this is the subset of edges X, shown here in blue, and we assume that this subset X is a part of some minimum spanning tree, which we denote by T. Okay? In other words, X as a subset of edges is a subset of some minimum spanning tree T. Okay? Now we also have a partition of the set of vertices into two parts. The set of vertices S and the set of vertices V minus S, all that remains. E is a lightest edge in the initial graph, which joins two vertices from different parts of partition. So E joins a vertex from S with a vertex from V minus S. Okay? What we need to prove is that if we add the edge E to our current set X, then what we get is also a part of some minimum spanning tree. Once again, what we assume about X? We assume that X is a part of some minimum spanning tree T. Okay? And E joins two vertices from different parts of partition. And what we need to prove is that X with E added to it is also a part of some possibly different minimum spanning tree. Okay, so the minimum spanning tree, which contains X plus E, is not necessarily the same as T. Okay, so to prove this, we consider two cases. So first, if E happens to be a part of the minimum spanning tree T, then there is nothing to prove. Okay, once again, we assumed that X is a part of minimum spanning tree that we denote by T. If E is also part of T, then X plus E is a part of minimum spanning tree T. In this case, there is nothing to prove. We are just done. Okay? So assume that E is not a part of the minimum spanning tree T. Let's then consider the wall tree T. So it contains X. So now the edges shown in blue show the wall tree T. Note that if we add the edge E to the tree T, then it produces a cycle, right? Because in the tree T, there is a path between the vertices, between the endpoints of E. And when we add the edge E, it produces a cycle. In this case, on our example, this is this cycle. This is this cycle, I'm sorry. Okay, so this cycle So this is a cycle, and the edge E in this cycle joins two vertices from different parts. Since this is a cycle, it must go from... So the edge E joins, for example, the left part with the right part. Since this is a cycle, it must eventually at some point go from right part to left part, which means that there must be an edge in the tree T which also joins two parts. Okay, and we denote this edge by E prime, and in our case this is this edge. So this is E prime. Okay, now what I claim is that if we replace the edge E prime by the edge E in the current tree, then what we get is an optimal spanning tree. So why is that? First of all, the resulting tree is still connected, right? Because we just removed some edge E prime from a cycle. So this is still connected. It was connected before, and when we remove an edge from a cycle, it cannot disconnect the graph. At the same time, the weight of the edge E prime is at least the weight of the edge E, right? Because E is the lightest edge that joins different parts of partition, right? Which proves that the resulting set of edges is a tree of minimum possible weight, which in turn proves the cut property. We are now ready to present the Kruskal, all the details of the Kruskal algorithm. Namely, we will prove that the Kruskal strategy is optimal. It produces a minimum spanning tree of minimum total weight, and we will also present implementation details of this algorithm. Recall that the idea of this algorithm is the following. We start with an empty set X, and we repeatedly add to this set the next lightest edge that doesn't produce a cycle. So it is not difficult to see that at any point of time the set of edges X forms a forest. That is a collection of trees. Let me illustrate this. Assume that we have some set of vertices, and initially the set X is empty, which means that each of our vertices forms a tree of size 1, namely a tree that contains one vertex and no edges. Initially each vertex is isolated in our set X. Now we start adding edges. Probably this is the first one, then we add this edge, then this edge, then this edge, then this edge, for example. At this point of time, our set X consists of 3 trees. So this is the first tree, T1, this is the second tree, T2, and this is the third tree, T3. In particular, the tree T3 contains just one vertex. It is an isolated vertex. Okay? Assume also that the next vertex, that the next edge that Kruskal algorithm is going to add is the following. So it is the next lightest edge that doesn't produce a cycle. The first thing to note is that the edge E must join two edges that belong to different trees, right? Because if they were in the same tree, this would produce a cycle. Okay, now we need to show that that adding E is a safe move. For this, we need to use cut property, right? And in turn, for using cut property, we need to show a partition of the set of vertices such that E is the lightest edge in our graph that joins vertices from different parts of partition. To construct such a cut, let's just take all the vertices from one of these trees as one part of this cut, namely this is going to be the set S. So this is one part of our partition, and all other vertices is the other part of this partition. In this case, we see that E is the lightest edge that joins two vertices from different parts, right? Which means in turn that cut property justifies that adding E in this case is indeed a safe move. In other words, if our current set X is a part of some optimal spanning tree, then X with E added is also a part of some minimum spanning tree. Once again, initially the set X in the Kruskal algorithm is empty, which means that each vertex of our initial graph forms a separate connected component. So this is how initially the set X looks like. So each vertex lies in a separate connected component. Then we start adding edges to X. This creates a forest. In this forest currently we have 3 trees, right? This is the first tree, this is the second one, and this is the third one. Assume now that the next lightest edge that Kruskal algorithm considers is the following one. First of all, we need to be able to check whether it joins two vertices that lie in the same tree, or in other words, that lie in the same connected component. In this case, they lie in the same connected component, so Kruskal algorithm will not add it to the set X, because otherwise it would produce a cycle in our set X, right? Now, assume that the next edge that Kruskal algorithm tries is the following. Again, we need to check whether the corresponding two endpoints lie in the same connected component. In this case, it is not the case. They lie in different connected components. So we add this edge, and at this point, we should update the data structure that we use to indicate that now we actually merge trees T1 and T2. So what we need to check in our data structure is whether two given vertices lie in the same set or in the same connected component, and also if they lie in different connected components, we need to merge the corresponding two trees. So the perfect choice for data structure for this algorithm is, of course, the disjoint sets data structure. Once again, to check whether two given vertices lie in different connected components, we just check whether find of one endpoint is equal to find of the other endpoint of this edge. If they are different, then they lie in different connected component. And when adding an edge to the set X, we need to merge the corresponding two tree, and this is done by calling the method union of the corresponding two endpoints. We will now illustrate this on a toy example. This is a toy example where we have 6 vertices. Let's first call them A, B, C, D, and D, E, F. And let's assume that we have a data structure disjoint sets. And let me show the contents of this disjoint sets, of this data structure. So initially each vertex lies in a separate set. Now we start processing edges in order of non-decreasing weight, right? So the first lightest edge is AE. We check whether A and E at this point lie at different connected components. For this we call find of A and find of E. This gives us different IDs because they stay in different sets. So we add this edge to our current solution, and we also notify our data structure that now A and E actually lie in the same connected component. So now it looks like this. Okay, the next lightest edge is the edge CF. Again, we ask our data structure whether C and F belong to the same set, and it replies that they do not belong to the same set because find of C is not equal to find of F. So it is safe to add this edge to our solution. We also notify our data structures and C and F now lie in the same set by calling union of C and F. So now C and F lie in the same set. The next edge is AD, and we see that A and D lie in different connected components. So we just add this edge to a solution, and also notify our data structure that we need to merge sets that contain the vertex A and the vertex D. So now we have three different disjoint sets in our data structure, which actually corresponds to vertices of our three trees. So the first tree contains vertices A, E, D, the second one contains the vertex B, and the last one contains vertices C and F. Now, the next lightest edge is DE. It has weight 3. However, we see that D and E belong to the same connected component. This in turn means that if we added the edge DE to our current solution, this would produce a cycle. So we just keep the edge DE, and we continue to the next lightest edge. The next one is AB, and we see that A and B lie in different connected components, so it is safe to add the edge AB to the current solution. We also need to merge the corresponding two sets. So after this merge, our sets look as follows. Now the next lightest edge is the edge BE. It is of weight 5. However, B and E belong to the same set, so we skip it. And the last edge that we actually add to our solution is the edge BF. Right? It is of weight 8, and at this point we also merge two sets, and now all our vertices lie in the same connected component, which means that we constructed an optimal spanning tree. That is a spanning tree of minimum total weight. The pseudocode of the Kruskal algorithm looks as follows. First, for each vertex in our graph, we create a separate disjoint set. We do this by calling makeSet method of the disjoint sets data structure. Then we initialize the set of edges X by empty set. The next step is that we sort the edges, all the edges of our graph by weight. Then we process all the edges in order of non-decreasing weight. Okay, this is done in this for loop. Then for each such edge, we need to check whether adding it to X is safe or not, namely whether it produces a cycle or not. To do this, we just check whether U and V belong to different connected components. For this, we need to check whether find of U equal to find of V or not. If they are different, then they lie in different connected components. In this case, it is safe to add the edge UV to the set X, and we do this in this line. And also in this case, we need to notify our data structure that all the vertices that lied in connected components with U and V now lie in the same connected components, because we just joined these two trees. And this is done by calling union of U and V. Finally, in the end, we just return the resulting set X. It remains to estimate the running time of the Kruskal's algorithm. We start by sorting the edges. So this requires big O of E log E time, right? This in turn can be rewritten as big O of E log of V squared, just because a simple graph has at most V squared edges. This in turn can be rewritten as just E times 2 log V. Again, log of V squared is equal to 2 log V. So we rewrite it as follows, and this is nothing else as just big O of E log V, right? So this is an upper bound on the running time of the first step. Then we need to process all the edges. For this, we make 2E calls to the find operation. Why 2E calls? Well, just because we process all the edges, and for each edge we make 2 calls to the find operation, namely for one endpoint and for the other endpoint. Then we also make at most V-1 calls to the union procedure. Why V-1? Well, just because initially we have n connected components. Namely, when the set X is empty, each vertex of our graph forms a separate connected components. Then each time when we call union, we actually merge 2 connected components. And in the end of the run of our algorithm, we have just 1 connected component. So all the vertices lie in the same tree. So initially we have n connected components, in the end we have 1, and each time we call union, we reduce the number of connected components by 1, which means that we make exactly v minus 1 calls to union procedure. Okay, so we have roughly E calls to find and roughly V calls to union procedure. Now recall that if we implement the disjoint sets data structure as a forest or as a collection of disjoint trees, and we use union by rank heuristic, then the running time, the upper bound on the running time of each operation is just log V, which gives us the upper bound E plus V times log V. Recall also that in our case, the graph is connected, which means that E is at least V minus 1, which in turn means that E plus V is at most 2E, which allows us to rewrite it as follows. So the upper bound on the running time of the second step is actually the same as for the first step. It is big O of E log V, which gives us that the upper bound on the running time of the whole algorithm is big O of E log V. Now recall that we actually know that if for our implementation of disjoint sets data structure we use both union by rank heuristic and path compression heuristic, then we can state a strong upper bound. That is, instead of using log V here, we actually have log star of V, the iterated log, right? This gives us a stronger upper bound for the second step. Unfortunately, this doesn't improve the total running time because still the upper bound for the first step, I mean for sorting all the edges, dominates the upper bound for the second step. However, for some applications, the edges are given to us already in sorted order, which means that in this case we do not need to spend E log V time for sorting the edges. So that the total running time in this case becomes equal to E times log star of V, which makes the Kruskal algorithm in this case even more efficient. So in this case the running time is upper bounded by E times log star of V, which is nearly linear. In this video, we consider the Prim's algorithm. Recall that in this algorithm, the set X always forms a tree, and we gradually grow it. At each iteration, we attach a new vertex, which is not currently in the tree, to the current tree by the lightest possible edge. And this is in fact very similar to Dijkstra algorithm. Recall that Dijkstra algorithm finds the shortest path between two nodes by constructing the tree of shortest paths from a given source node. We will now illustrate this on a toy example. Consider the following toy example that we've already seen. We are now going to gradually grow a tree which will eventually become a minimum spanning tree. At each iteration, we are going to select a vertex such that it can be attached to the current tree by the lightest possible edge. To select such a vertex, we will use the priority queue data structure. So initially, we know nothing about the graph, so the cost of attaching each vertex to the current tree is just equal to infinity. So initially, the priority or the cost of attaching each vertex to the current tree is equal to infinity. That is, we show here the priorities of all our vertices in the priority queue data structure that we are going to use. Then we declare some vertex, just randomly picked vertex, as the root of the tree that we are going to grow. Assume that we consider this vertex as the root. Now we can change its priority to be equal to 0. It costs us nothing to attach this vertex to the current tree. It is the root. Now we need to process all edges going out of this tree, namely going out of this vertex. Namely, we change the priority of this vertex to 1 because we see that there is an edge of cost 1 that attaches this vertex to our current tree. And for this vertex, we change we change its priority to 8. Okay, now we have 5 vertices in our priority queue. I mean all the vertices except for the root, and the cost of one of them is equal to 1, or the priority. The priority of the second one is equal to 8, and the priority of the remaining 3 vertices are equal to plus infinity. So we select the vertex with the smallest priority. This is 1. So we attach it to our current tree. So our current tree looks as follows. Now we need to process all the edges that go out of this tree. Namely, when we add a new vertex, we need to check whether new vertices can be attached to this vertex. When we see this, first we see that there is an edge of weight 6, so we need to change the priority of this vertex to 6, because it now can be attached to the current tree by the edge of weight 6. Also, we change the priority of this vertex to 9. Okay? Now we have 4 vertices in our priority queue data structure, and we select the vertex with the minimum priority, which is 6. So which is vertex with priority 6. So now this vertex is also in our tree, which is joined by this edge to our current tree. Now we need to process all the edges going out of this vertex to vertices that are not currently in our tree. When processing the edges, we change the priority of this vertex to 4, and we change the priority of this vertex to 5. Namely, we just found a cheaper way of connecting this vertex to our current tree. Okay, now we have 3 vertices in our priority queue. So we select, we extract the minimum value. This gives us the following vertex. So we include it in our tree, which gives us and attach it by this node. Then we need to process all the edges going out of this vertex to vertices that are currently not in the tree. We see that we need to change the priority of this vertex to 1, because there is an edge of weight 1 that connects this vertex to the vertex which is currently in the tree, and we need to change this priority to 2. Right? Okay, great. Now we have 2 vertices in our priority queue, one of priority 1 and one of priority 2. So we select this vertex. Now it is in our tree, and it is connected by this edge, right? When processing all the edges going out of this vertex, we see that there is an edge of weight 3. However, it doesn't decrease the cost of attaching the remaining vertex to the tree, so we keep the priority of this vertex unchanged. So at the last step, we extract the only remaining vertex, which is this one, and we see that the cost of attaching this vertex to the current tree is equal to 2, and this is done by this edge. So now let's compute the total weight of the resulting tree. It is 2 plus 1 plus 4, which gives us 7, plus 6, which is 13, plus 1. So this gives us the tree of total weight 14. We now provide the full pseudocode of the Prim's algorithm. As we've discussed before, it is very similar to Dijkstra algorithm. So once again, the Prim's algorithm gradually grows the tree, which eventually turns into a minimum spanning tree. We use the priority queue data structure to keep for each vertex the minimum cost of attaching it to the current tree. At each iteration, we use priority queue to quickly find the vertex which can be attached to the current vertex by the lightest edge. So specifically, we do the following. Initially, we have for each vertex, we do not know the cost of attaching it to the current tree, so we just put infinity into the array cost. We also going to keep array parent, which will actually define as a tree. Okay, initially we do not, for each vertex of our graph, we do not know its parent. Then we select any vertex of our graph, u0, and we declare this vertex as the root of the tree which we are going to grow. We then update cost of u0 to be equal to 0. So we say that attaching this node to this vertex to the current tree is the cost of attaching this node is equal to 0 because it is already in our tree. We then create a priority queue. So at this point, and we use costs as priorities. At this point, all the vertices lie in priority queue, and the priorities of all of them except for u0 are equal to infinity, to plus infinity, while the priority of u0 is equal to 0. Okay, then we do the following. At each iteration, we extract the vertex with the minimal priority out of our tree. This means out of our priority queue. This means that we're actually attaching this vertex to the current tree. When we do this, we also need to go through all the neighbors of the vertex v and to check whether the edge that leads from v to this neighbor of v has actually cost less than the current cost or than the current priority of this neighbor. Specifically, we do the following. When we add the vertex v to our current tree, we iterate through all its neighbors. This is done in this for loop. So we iterate through all neighbors z of the vertex v, and we check if z is still in priority queue, namely if z is not in our current tree, and if the current cost of z is greater than the weight of the edge from v to z, then this means that we've just found a cheaper way to attach the vertex z to the current tree, right? And in this case, we just update the value of cost at z. So we assign cost at z to be equal to the weight of the edge vz, and we also say that in this case, if we attach the vertex v to the current tree, then this will be done through the edge vz, which means that that v is going to be the parent of z. Finally, we notify our priority queue that we need to change the priority of the vertex z to the updated value cost of z. Since the Prim's algorithm is very similar to Dijkstra's algorithm, its running time is also similar. So essentially what we're doing here is the following. We make v calls to extract mean procedure, right? And also we make at most e calls to change priority method, right? And the total running time depends on the implementation of the priority queue data structure. If we just use array to store all priorities and at each iteration, this means that change in priority is very cheap because we just change the corresponding value in our array. However, for finding the minimum value, we need to scan the whole array. In this case, we get v squared upper bound on the running time. Why is that? Well, once again, because extract mean in this case has running time big O of v. So this is v times big O of v, while change priority has running time big O of 1. Right? It is a constant time operation. Since the number of edges in the graph is at most v squared, this gives us big O of v squared. If, on the other hand, we implement our priority queue data structure as a binary heap, then both these operations have running time big O of log v. In this case, we have the following running time: v plus e times log v. And since in our case, again, the graph is connected, e is at least v minus 1. So this allows us to rewrite the whole expression as big O of e times log v. So once again, the running time depends on implementation. If we use array to implement our priority queue, this gives us v squared. If we use a binary heap, this gives us e log v. Which one is better depends on whether our graph is dense or not. We are now ready to summarize. In this module, we consider two greedy algorithms for the minimum spanning tree problem. The first one is due to Kruskal, and it uses the following idea. At each iteration, we add the next slightest edge to our current solution if this edge doesn't produce a cycle. To check whether the current edge produces a cycle or not, we use the disjoint sets data structure. Namely, for the current edge uv, we just check whether u and v belong to the same connected component. If they do, we just skip the current edge. The next algorithm is due to prim. It uses a slightly different but still greedy strategy. Namely, we greedily grow a tree. At each iteration, we attach a new vertex to the current tree by the lightest possible edge. To find such a vertex quickly, we use the priority queue data structure.
Hi! In this module, you will be working on a project based on advanced shortest paths algorithms. The project will be organized as a series of programming assignments similar to those you had in the previous modules. However, in these programming assignments, you will be working with real-world data based on road networks and social networks. Also, you will have more freedom to come up with your own creative ideas about how to improve your algorithms. You even can compete with your fellow learners on the forums on how fast does your algorithm solve a particular problem in the programming assignment. You've learned the classical shortest paths algorithms in two of the previous modules, and you've learned the breadth-first search algorithm, Dijkstra's algorithm, and Bellman-Ford's algorithm. The advanced algorithms can be faster thousands of times or sometimes even millions of times in practice. But those are optimizations which work for particular kinds of graphs. For example, some algorithms are very good for road networks and others are very good for social networks. All the advanced algorithms that we will tell you in the lectures of these modules are some optimizations based on the classic Dijkstra's algorithm. So it's good to go back and recall how Dijkstra's algorithm works and make sure that you can solve the problems based on Dijkstra's algorithm in the previous modules before starting on the project. In this lesson, we will study the idea of bidirectional search, and we will come up with the bidirectional version of the Dijkstra's algorithm. But first, let's recall what is the problem that we're solving. In mathematical terms, we're given a graph G which can be either directed or undirected, but it has non-negative edge weights. This is important. In all the lectures of this module, we will work only with the graphs with non-negative edge weights, such as travel times or distances. We're also given a specific source vertex S and a target vertex T, and we want to find the shortest path between S and T in the graph G. So the first question is, why not just use the Dijkstra's algorithm that we already know? It has pretty good worst-case complexity, E plus V times log V. This is pretty good, right? Can we even do better in the worst case? Well, it turns out that we can. Mikkel Thorup came up with an algorithm in 1999 that solves this problem for undirected graphs in linear time. Linear times in terms of number of edges and vertices of the graph. Such algorithm is still not known for directed graphs, but for undirected graphs we can definitely do better, and for directed graphs we can do better also, but we just still don't know the linear time algorithm. However, we're not just interested in the worst time complexity, we're interested in the practical performance of our algorithms. And in practice, the classical Dijkstra's algorithm on a graph of USA with 20 million vertices and 50 million edges will work roughly for several seconds on average. Several seconds sounds like a good thing, but when you use, for example, Google Maps, you don't want to wait for several seconds. You want the results to be on your screen in a blink of an eye, which in practice means that you want them under 100 milliseconds. And not only you, but millions of people simultaneously want those results in a blink of an eye. So that's why we need something significantly faster for such applications. Now let's consider how Dijkstra's algorithm progresses through the graph. You remember that it processes vertices in the order of increasing distance. It starts with the source vertex S, and then it processes it by considering the outgoing edges and finding the vertices on the other end of those edges and relaxing those edges. And so it goes to these vertices at distance 1, and the numbers near the edges are the weights of the edges, and the numbers inside the nodes are the distances to those nodes. And then it goes to another layer of nodes at distance 2. And so you see that the Dijkstra's algorithm actually goes in circles around the source vertex S. And this is no coincidence. So you remember the lemma that when a vertex U is selected via the extract mean procedure in the Dijkstra's algorithm, the estimate of distance to this node, dist of U, is guaranteed to be equal to the actual distance from the source vertex to vertex U. And also, all the nodes on the distance smaller than that have already been processed by that moment. This is guaranteed in the Dijkstra's algorithm. So actually a circle of processed vertices grows. And this is how it looks if we want to find a shortest path from source vertex S to the target vertex T. We start growing the circle around the node S until it touches point T. And as soon as it touches point T, we can actually stop the Dijkstra's algorithm. This is called early stopping. Instead of scanning all the vertices in the graph and finding the distance from S to all other vertices in the graph, we only find the distances to the nodes we need to actually find the distance to the node T and the shortest path to node T. This is an optimization of Dijkstra's algorithm already, but this is the simplest one. And here is the idea for the bidirectional search. Instead of going from S and growing the circle until it touches point T, we want to go simultaneously forward from S and backward from T until we meet. And as soon as we meet, we can find the shortest path between S and T by combining the half of the path from S to the meeting point and the half from the meeting point to T. In the algorithm, we won't go literally simultaneously. We will take alternating turns from S and from T. We will do a typical Dijkstra's algorithm from S. We will do one turn of that algorithm, and then we will alternate to T, and we will make one turn of the Dijkstra's algorithm backwards from T. To do that, we will need not only to know the outgoing edges from each node, but also all the incoming edges to each node. But other than that, we will do the regular Dijkstra search from S forward and the regular Dijkstra search from T but backwards. And we will alternate the turns of those Dijkstras. So then we will make one more turn from S and one more turn backwards from T. And then one more turn from S and then one more turn backward from T. And now we see that the vertex in the middle was discovered by both algorithms, the forward one and the backward one. And now we can reconstruct the shortest path from S to T, and we can fill in the correct distances from S to all the nodes on that path. Now let's see how it works compared to the usual Dijkstra's algorithm. So the usual Dijkstra's algorithm will cover and scan the nodes in this big circle with the center in S and touching point T. What will happen in the bidirectional search is we will be growing two circles of roughly the same radius until they touch. And this area covered by these two smaller circles is roughly proportional to the number of vertices scanned during the bidirectional search. So let's denote the big circle by C1 and the two smaller circles by C2 and C3. And the distance from S to the meeting point V, which is roughly equal to the distance from the meeting point V to the target node T, will denote by R. Now let's estimate the number of covered vertices by the area of the corresponding circle. So the area of the circle C1 is pi times the radius of C1 squared. The radius of C1 is 2R, so its square is 4R squared. and in the end the area of C1 is 4 pi r squared. And the area covered by bidirectional search is the sum of areas of C2 and C3. The areas of C2 and C3 are roughly equal, and the area of C2 is pi r squared. So the total area is 2 pi r squared. And we see that the total area covered by bidirectional search is roughly twice smaller than the area covered by the usual Dijkstra's algorithm. So let's see what happens actually on the real world networks when we use the simple Dijkstra's algorithm and the bidirectional search. This is a part of the map of USA with 1.6 million vertices and 3.8 million arcs, and we're finding the best shortest path in terms of the travel time. So here we try to find the shortest path from the small blue rectangle to the small green rectangle on the right edge of the map, and we color it with green all the nodes scanned by the regular Dijkstra's algorithm while it was looking for the shortest path. And on the next picture here, we see the result of the bidirectional search. And you see that there is something similar to what we draw on the previous slides. So there is something like a blue circle around the starting point, and there is something like a green circle around the target vertex. The green circle is cut in half because of the edge of the map, but in general this is the picture we imagine. And here is another example on the map of the full US, and we see a full circle around the green point, although it is not like a real circle, it's more like a rotated square, but this is due to the way we humans build the roads, because we build them from north to south and from east to west very often, and that's why the circle is more like a square rotated by 45 degrees. And the blue point is surrounded by something more like a half a circle, which is cut by the shore. So roughly we get a 2x speed up on the road networks, which is good but not great. We were hoping for something like thousands of times speed up. So, but this is true for road networks. And what if we look at the social networks? And in the next video we will see that indeed for social networks the bidirectional search idea works exceptionally well, and it will work thousands of times faster than the regular Dijkstra's algorithm. Hi! In this video we will apply the idea of bidirectional search to social networks data, and we will see that it will work exceptionally well, going up to thousands of times faster. But first, let's learn an interesting fact about our world. So in 1929, a Hungarian mathematician Frigyes Karinthi made a small world conjecture, which you probably heard of already. So the conjecture was that basically when we need to pass a message from any person on Earth to any other person on Earth, using only personal connections in between, we need at most 6 handshakes to do that. So that we need only at most 5 intermediary people to pass a message from anyone to anyone else on Earth. This is somewhat surprising, but it turned out to be close to truth in different experiments which people made after that conjecture. And this is called a 6 handshakes or 6 degrees of separation idea. And now let's look at the most popular social network, Facebook, given that 6 handshakes idea. So suppose an average person on Facebook has around 100 friends. Then if we consider friends of that person, it will be 100 times 100, roughly, that's 10,000 friends of friends. If we consider friends of friends, that will be 100 times more, or 1 million. And if we progress with that, we'll get that at 6 handshakes we will have 1 trillion people. Well, that's not actually possible, as there are only roughly 7 billion people on Earth, so it will be much less than that, but you get the general idea that the number of friends grows exponentially when we increase the distance. So now we want to find the shortest path from Michael to Bob via friends connections. So we want to know actually how many handshakes do we need to send a message from Michael to Bob. And if Michael and Bob turned out to be the two farthest people on the Facebook social network, then the regular Dijkstra's algorithm would have to look through all roughly 2 billion people which are on Facebook to find that shortest path. Now, what will happen if we consider a bidirectional search? So we'll only consider friends of friends of friends of Michael and friends of friends of friends of Bob. And if we know that the 6 handshakes conjecture is true, then there will be a common person among friends of friends of friends of Michael and friends of friends of friends of Bob. If we find that person in common, then we will find the shortest path of length at most 6 between Michael and Bob. And to do that, we can create a hash table, for example, of all the friends of friends of friends of Michael, or a sorted list, and then search the friends of friends of friends of Bob in that hash table or ordered list one by one to find the common person. And how many people will we actually consider in this case? We'll have roughly 1 million friends of friends of friends for both Michael and Bob. So in total 2 million people. And this will work in linear time if we use hash tables. So this will be actually 1000 times faster than using Dijkstra's algorithm, at least in the number of friends scanned. So this is going to work really thousands of times faster on social networks. And what we've just seen is a particular case of a more general idea called meet in the middle. And this applies not only to graphs. So in general, if you need to search for some best object of some kind, for example, the best shortest path or a best subset of people to create a team, then instead of searching for all possible objects, all the possible shortest paths, or all possible subsets of people, we can somehow divide all the possible objects into halves. For example, when we're searching for shortest paths, we can divide any path on the first half from the source and the second half to the target. And when we're talking, for example, about subsets of people, if we have n people, we can divide any subset of n people into 2 halves. First half consists of a subset of the first n over 2 people, and the second half consists of a subset of the second n over 2 people. And then we can search all the variants for the first half separately, all the variants for the second half separately, and then we just need to find the compatible halves. So for example, we again create a hash table or an ordered list of the first halves which are possible, and then for each particular second half we try to find whether there is a compatible first half to it in this hash table. And this is in general how meet in the middle works. And typically, instead of searching through all possible big N objects, this works in time proportional to square root of n, because only square root of n halves of those objects, square root of n of the shortest paths halves, and square root of n first halves of the subset of people. So this idea can be applied in many different problems to take a significant speed up. So in conclusion, we understood that the regular Dijkstra's algorithm goes in circles of increasing radius around the starting point. And the bidirectional search idea can reduce the search space. We can scan less vertices than if we go from one source and grow the circle. And on the road networks, it works roughly twice faster than the regular Dijkstra's algorithm. But if we use this meet in the middle idea on the social networks, or actually on many other problems, then it will roughly work as a square root of n instead of big N, if big N is the total number of objects we need to search through. And in social networks it can be 1000 times faster than the regular Dijkstra's algorithm. And you will actually see that in one of the problems of the programming assignments of this project. And in the next video we will actually come up with the bidirectional version of Dijkstra's algorithm. Hi! In the previous videos we've introduced the idea of bidirectional search. But now we need to actually specify how exactly will we extend the Dijkstra's algorithm to become bidirectional. First, let's recall how Dijkstra's algorithm works. So it needs to find the shortest path from some vertex S to vertex T. It initializes an auxiliary array dist with the values of infinity for all the nodes but for the starting node S. And for the starting node S, it initializes the distance estimate to 0. And then it goes in iterations. On each iteration, it calls extract min to choose the unprocessed vertex U with the smallest distance estimate. And there is a guarantee that by the time vertex U is extracted that way, its distance estimate is equal to the actual distance from the starting vertex S to the vertex U. And then we process U, meaning that we try to relax all the edges outgoing from U. And then we repeat this process until T is extracted and processed. So then we know that the distance to T is already equal to the distance estimate in the dist array. Now we need to introduce a notion of reversed graph for our bidirectional search. So the reversed graph GR for graph G is the graph with the same vertices and reversed edges. You have an example in the bottom of the slide when we have vertices A, B, and C. And the graph G is on the left with the edges going from A to B, from A to C, and from B to C. And in the graph GR, the vertices are the same, but the edges go the other way around, from B to A, from C to A, and from C to B. So this is very simple, and to build the reversed graph, we can just copy the vertices and then go through all the edges of the graph G, reverse them, and add them to the new graph GR. So the bidirectional Dijkstra's algorithm will start with building the reversed graph so that it can do the backward search from the target vertex. And then it will start Dijkstra's algorithm in the forward direction from the source vertex S in the graph G, and also the backwards Dijkstra's algorithm from vertex T in the reversed graph GR. So in the reversed graph GR, the regular Dijkstra's algorithm will be the same as the backwards Dijkstra's algorithm in the initial graph G. And then we'll alternate between Dijkstra steps in the forward search in G and in the backward search in GR. And we will stop as soon as some vertex V is processed. And you remember that processed means that it is extracted from the queue with the vertices, both in the forward search and in the backward search. As soon as that happens, we can compute the shortest path between S and T, and I will show you how in a minute. But first, a question. So let's consider this meeting point V, the first vertex that is processed in both the forward search and the backward search. We said previously that as soon as we meet in the forward and backward search, we can reconstruct the shortest path from S to T by taking the first half from S to the meeting point and then from the meeting point to T. So, is it right? Is it always the case that as soon as we meet in some vertex V, there is a shortest path from S to T that goes through V? So what do you think? Well, it turns out that this is not the case, and here is an example. S and T, we do alternating turns from S, then from T backwards, then from S, then from T backwards, and inside the vertices we have the distances on the left from S and on the right to T. And then we meet in the middle vertex, and we see that the distance from this vertex to T is 5, and the distance from S to this vertex is 5, and we can actually reconstruct the path of length 10 from S to T. But what if there was an edge, this green one, of length 4? This wouldn't contradict the progression of neither the forward Dijkstra search nor the backward Dijkstra search, because this edge has length 4, which is bigger than 3, and so the middle vertex will be considered before the vertex to the right from it in the forward search, and also the middle vertex will be considered before the vertex to the left from it in the backward search. So we will really meet in the middle vertex before even considering the edge between the vertex to the left from the middle and vertex to the right from the middle. But here we can see that the shortest path from S to T doesn't actually go through the middle vertex. It goes around it, and it is of length 8 instead of the path which goes through this middle vertex and has length 10. So it is not always the case that the shortest path go through the meeting point. So what exactly then do we need to do to compute the distance when we found the common meeting point? It is not always the case that the shortest path go through the meeting point. So what exactly then do we need to do to compute the distance when we found the common meeting point? And is it actually possible? Well, it is possible, but it is a little bit more complicated. So let's denote by dist of u the distance estimate in the forward dijkstra's from source vertex S and G, and by dist r of u the same, but the distance estimate in the backward dijkstra from T in the GR. So dist r is an estimate of the distance from u to the target vertex T. So after some node V is processed in both G and GR, I state that there exists some shortest path from S to T which passes through some node U, which is processed either in the forward search or in the backward search or in both, and the distance from the S to T is equal to the distance estimate of U in the forward search plus the distance estimate of the backward search from U. What it means is that there exists some vertex U that the shortest path from S to T, at least some shortest path from S to T goes through this vertex U, and this U is either processed in G or is processed in GR, and also the distance estimates for that vertex are already correct for both forward search and backward search. So of course, if it is processed in the forward search, for example, then we know that the distance estimate to this node is already correct, that the distance from source vertex to this node U is equal to its distance estimate dist of U. But if it's not yet processed in the backward search, in the reverse search, then this is not guaranteed in the general case for the dist R, for the distance estimate in the backward search. But we can show that for some node U, it is actually also a correct estimate, which is equal to the distance from U to the target vertex T. So there exists some node U and some shortest path that this node U lies on the shortest path, and both distance estimates from source to U and from U to target are already correct by the moment our forward search meets our backward search. Now let's prove this lemma. So we have these two gray circles which show us the scanned vertices by the forward search from S and by the backward search from T. And they touch in the vertex V, which is the meeting point. Now first, let's prove that if there is some node U which is not processed by forward search and is not processed by the backward search, and there is a shortest path from S to T going through this node U, that then there is also a shortest path which goes from S to T through V. To see that, first let's compare the first half of the shortest path from S to T going through U to the shortest path from S to V. We know that V is already processed in the forward search, and it means that the distance from S to V is at most the distance from S to U. So here the green path is less than or equal to the red path. Also, if we consider the backwards dijkstra search, we know that V is processed, but U is still not processed in this backward search. So the right half, the green right half, is also less than or equal to the red half. So in both halves, the green parts are less than or equal to the red parts. And this means that the path from S to T going through V is shorter or of the same length as the shortest path from S to T going through U. So it means that actually the path from S to T going through V is the shortest path. And so in this case, our theorem is proved. If there is at least one vertex U which is not processed by forward and not processed by backward search, and there is a shortest path going through this vertex, then there is a shortest path, another one, which goes through the vertex V, which is already processed by both forward and backward search. And of course, both distance estimates of V are already correct because it's already processed in both backwards and forward search. Now let's consider another case when there are no vertices which are unprocessed by both forward and backward searches, but we already meet at point V. So let's consider then any shortest path from S to T, and let's consider the last vertex U on such shortest path that is processed by the forward search. So U is the last vertex which is on the shortest path which is processed by the forward search. And then the distance estimates of U in the forward search is already correct. It is equal to the distance from S to U. Let's consider the next edge of the shortest path. It goes to some vertex W, and this vertex W has to be processed by the backward search. Why? Because W is not processed by the forward search, because U is the last vertex of the shortest path which is processed by the forward search. And W cannot be unprocessed by both forward and backward search because it lies on the shortest path. And so W is indeed inside the gray circle around T. It is indeed already processed by the backward search. And so the distance estimate of the backward search for W is already correct. It is already equal to the distance from W to T. Now what we know is that the distance between S and T is equal to the distance from S to U, which is equal to the distance estimate of U, dist of U, plus length of the edge from U to W, plus distance from W to T, which is already equal to the distance estimate of the backward search, dist R of W. And now what we want to prove is that this is also equal to the sum of distance estimate of U and the reverse distance estimate of U. So the first summand is the same. And now I claim that the distance estimate in the reverse direction is equal to the sum of the two other summands in the first equation. Why is that? Well, from one point of view, we know that the distance estimate of U is always bigger or equal to the real distance from U to T. Because the distance estimate in any moment of Dijkstra's algorithm is greater or equal to the real distance. From the other hand, we know that the vertex W is already processed in the reversed search. And when it was processed, in particular, the edge from U to W was relaxed in the backward search. And when it was relaxed, it made sure that the distance estimate of U in the reverse direction is at most this sum of length of this edge plus the distance estimate for W. So we know that distance estimate of U is at most length of edge from U to W plus distance estimate of W. But this sum is the length of the shortest path from U to T going through W. So in fact, we know that distance estimate of U is both greater or equal than the true shortest path from U to T, and also is less than or equal to the shortest path from U to T. And this means that it is exactly equal to the shortest path from U to T, and that the distance from S to T is actually equal to the distance estimate of U plus the reverse distance estimate of U. So now we've proven the theorem, and we can implement the algorithm as follows. We do the alternating turns of forward search and the backward search until we meet at some point V. And we remember which vertices are processed in forward search and which vertices are processed in the backward search. Then we take all those vertices which are processed at least in one of them, and for each of those vertices we minimize the sum of distance estimate of the forward search plus the distance estimate of the backward search. And for the node for which this sum is minimal, we know that there is a shortest path going through this vertex, and its length is equal to the sum of these two distance estimates. And then, to reconstruct the path itself, we can reconstruct the shortest path from the source vertex to this middle vertex in the forward search, and separately reconstruct the path from this vertex to target vertex T in the backward search, and then just join those two paths into a single shortest path from S to T. I won't show you the pseudocode in the lecture, but you can see it in the slides which are uploaded. So, in conclusion, a few remarks. First, the worst case running time of bidirectional Dijkstra is the same asymptotically as for the regular Dijkstra's algorithm, and we saw that it can differ, for example, twice for rod networks, but this is not an asymptotic difference. And speed up in practice depends on the graph. So for the rod networks, it's roughly 2x speed up, but for social networks, it can be thousands of times faster. From the other hand, the memory consumption is somewhat worse, but again, it is not asymptotically worse. It's just 2x to store 2 copies of G, the G and the reversed G, and also we'll need to store some auxiliary arrays for forward search and for backward search, so twice the memory for those also. So roughly 2x memory consumption. And you'll see the actual speed up on social networks graphs in one of the problems of the programming assignment of this project. Hi, in this lesson we will study the A-star algorithm. It is another optimization of the Dijkstra's algorithm for the case when you have a specific source and specific target, and at any point you have an estimation of how long does it take to get from this point to the target. This estimation doesn't have to be exactly precise, but if it is good enough, it can speed up your search a lot. An example of such estimation is very simple. If you have the coordinates of your target point and you have a phone with GPS controller and you know the GPS coordinates of your current point, you can have an estimation based on the distance by the straight line between those 2 points and the speed of your car. So this is the kind of information we can use to greatly improve the performance of the Dijkstra's algorithm. So let's first understand the notion of the directed search. And to accomplish directed search, we will need the notion of potential function. So we can take any function mapping vertices to real numbers, and it will be called a potential function. And then the value of this potential function on a vertex is called this vertex's potential. So this potential function defines new edge weights. If we had edge weight L of uv on the initial graph, then we can denote by L pi of uv the new edge weight, which is equal to the old edge weight minus the potential of the starting vertex plus the potential of the ending vertex of that edge. And it turns out that if we replace the old edge weights with these new edge weights, it doesn't change the shortest paths. Well, of course, it does change the distances between vertices. What I'm saying is only that the paths themselves, which were shortest in the initial graph, they are also the shortest paths between the same pair of vertices in the new graph, and vice versa. The shortest paths in the new graph with new edge weights are also the shortest path between the same pair of vertices in the initial graph. And to prove this, I need this lemma. For any potential function mapping vertices to the real numbers, for any 2 fixed vertices S and T in the graph, and any path P between them, the length of this path in the new graph with new edge weights is equal to the length of this path in the initial graph minus the potential of the starting vertex, and plus the potential of the ending vertex. Why is this important? Well, because if you fix the starting and ending vertex, then for any path, its length in the initial graph and its length in the new graph differ by a constant, because this constant only depends on the starting vertex and the ending vertex, and we fix them. And so if some path was the shortest path between S and T, then it will stay the shortest path between S and T in the new graph, because all the paths just add a constant to their length, and so the paths which were shorter than others, they stay shorter than others. And the same goes vice versa. If the path was shortest in the new graph, it was also shortest in the initial graph. And now let's prove this lemma. We consider some particular path P from S to T, and we also denote S as V1 and T as Vk, and the intermediate vertices V2, V3, and so on, Vk minus 1 are the vertices of this path. And now we consider the length of this path in the new graph with the new edge weights. By definition, it is equal to the sum of the length of the edges of this path, which is L pi of V1 to V2 plus L pi of V2 to V3, and so on. And then we can rewrite each L pi from Vi to Vi plus 1 by definition. And we know that L pi of V1 to V2 is equal to L of V1 to V2 minus the potential of V1 plus the potential of V2. So this first line is equal to L pi of V1 to V2. And each of the next lines is similar. It corresponds to the length of the edge in the new graph with the new edge weights. So we write each edge on its own line, and now we can notice that there are summands which cancel out. For example, pi of V2 here and pi of V2 here are with different signs, so they cancel out. And the same will happen with pi of V3 and pi of V3 here. And the same will happen with pi of Vk minus 1 and minus pi of Vk minus 1. So most of the terms, including this pi of Vk minus 2, will cancel out. The only thing that is left is the sum of the length of the initial edges minus the first potential of the starting vertex minus pi of V1 and plus pi of Vk, the last vertex. Those are the only two summands of the form pi of something which don't cancel out. And then we can rewrite this as the first summand is the length of this path in the initial graph, L of P, minus the potential of the starting vertex, because V1 is the same as S, and plus the potential of the last vertex, and Vk is the same as T. So the length of the path in the new graph is equal to the length of the path in the initial graph minus the potential of the starting vertex plus the potential of the target vertex. So we've proved our lemma, and so we know that the shortest paths in the initial graph and in the new graph with new edge weights are the same, although their lengths differ by some constant depending on the starting and ending vertex of the path. Now we can formulate an algorithm which can be called Dijkstra with potentials. So we take some potential function pi, and we'll launch the Dijkstra algorithm with new edge weights L pi instead of the initial edge weights L. And the resulting shortest path is also a shortest path in the initial graph. So the result of this algorithm is the same as the result of the initial Dijkstra's algorithm. But depending on the potential function pi, maybe it will come from the source vertex S to the target vertex T faster than with the initial edge weights, because the order of vertices that this algorithm considers can be different. So this is the idea of optimization. But does any potential function fit us in this case if we want to run Dijkstra's algorithm using the new edge weights? Well, the answer is no, because for any edge from u to v, the new length L pi of uv must be non-negative so that we can apply Dijkstra's algorithm for these edge weights. So such potential function for which this is true, that all the new edge lengths will be non-negative, is called feasible. Now the intuition behind the potential function is the following. Pi of v is going to be an estimation of the distance from the current vertex v to the target vertex t. So how far is it from here to t? If we have such estimation, we can often avoid going into wrong direction, and that's why we'll get a directed search. And typically in practice, pi of v is a lower bound on the distance from the current point to the target. For example, on a real map, a path from the current point to the target cannot be shorter than if we manage to go directly on a straight line from the current point to the target. This is often not possible because of houses or mountains, but if this is possible, this is the shortest path possible at all. And our real path cannot be shorter than the straight line segment between the current point and the end point. So A-star algorithm is basically this Dijkstra with potentials. So what does Dijkstra with potentials do? It goes in iterations, and on each iteration it picks the vertex v which minimizes the current estimate of distance to v. And what will it be equal to? We know that any path in the new graph differs from the same path in the old graph by minus potential of the starting vertex plus potential of the ending vertex. So we are going to pick v minimizing dist of v, which is the distance estimate if we ran the regular Dijkstra's algorithm on the same graph, which is basically the length of the best known path from the source vertex to v, minus pi of s plus pi of v. Now notice that pi of s summoned is the same for all v. So the vertex v which minimizes this expression is the same v that minimizes just dist of v plus pi of v. And in some sense, this is basically the most promising vertex, because pi of v is an estimate of the distance from v to the target. And so we picked vertex v with the minimum current estimate of the distance from source vertex to v, plus the distance from v to the target vertex. And this is, in turn, an estimation of the shortest path from S to T going through V. So this is why the search is directed. We always go not just to the closest vertex to S, which is still not unprocessed, but we also want it to be close enough to the target. And this is why, while we're searching, we avoid going away directly from the target. And then as soon as we find the vertex T as the vertex minimizing this expression in the Dijkstra's algorithm on this new graph, we stop. So, of course, this algorithm could still go through the whole graph before it gets to the target. But in practice, if we have a good estimate of the distance left from the current point to the target, we will get to the target and extract it much earlier. And on the way there, we will avoid a lot of turns in the wrong direction. Talking about the performance of A-star, it can only be seen in practice. It is an empirical algorithm and it depends on the quality of the potential function. And in the case when this potential function gives a lower bound on the distance from the current point to the target, which is most often the case, we have the following picture. The worst case is if the potential function is always equal to 0 for all the vertices. This is always a feasible potential function, but then the algorithm will work the same as the Dijkstra's algorithm. It will not work better, but it will work the same. And the best case is if your lower bound on the distance to the target is always actually equal to the distance to the target from the current v. Then the edge weights will be 0 if and only if this edge lies on the shortest path to the target vertex. So it will be very easy to distinguish the edges through which you should go and the edges through which you shouldn't go. If the edge has weight 0, then it leads you to the target. Otherwise, it is not optimal to go through this edge. So you only go through the edges with weight 0, and then you will only visit edges which lie on the shortest paths from the source to the target. And so you will explore the minimum possible number of edges at all before getting to the target. So this is the best case. And in practice, depending on the quality of your lower bound, you'll be somewhere in between. And it can be actually shown that the better your lower bounds, the tighter they are, the better will be the performance of the A-star algorithm. And in the next video, we'll see how to actually implement a bidirectional version of this A-star algorithm to improve it even more. Hi! In the previous video, you've learned the 8-star algorithm, which is an optimization of the regular Dijkstra shortest path algorithm using additional information. And in the previous lesson, you've learned that you can use a bidirectional search to optimize Dijkstra's algorithm. Now we're going to join those two ideas to optimize the A-star algorithm further and to get the bidirectional A-star algorithm. So bidirectional A-star algorithm is basically the same as bidirectional Dijkstra, but with the use of potentials. So now we need two potential functions. One potential function pi f of v estimates the distance from the current point to the target. This is needed for the forward search. But also we need an estimation for the backward search using Dijkstra's algorithm from the target. So we need another potential pi r of v, which estimates the distance from the source to the vertex v. Now we have a problem, because under these two potentials we can have different edge weights, because the new edge weight according to pi f is the initial edge weight minus potential of u plus potential of v. And the new edge weight under the reverse potential is the initial weight minus potential of v plus potential of u. And we need these two variables to be actually equal, because in our bidirectional Dijkstra's algorithm we use the fact that we're going through the same graph but just in different directions, forward and backward. But we need, for it to work correctly, we need the fact that the edges have the same weights going in forward direction or in backward direction. So how to solve this problem? So we need that L pi f of uv is equal to L pi r of uv, and if we rewrite by definition, we will see that this is equivalent to having pi f of u plus pi r of u equal to pi f of v plus pi r of v for any pair of vertices u and v connected by an edge. And actually we can make an even stronger claim that we need a constant value of pi f of u plus pi r of u for any u. If this is true, then of course for any two different vertices u and v, pi f of u plus pi r of u will be equal to pi f of v plus pi r of v, and then all the edge weights will be equal both in forward and backward directions. And the solution for this is to take any potential feasible potential pi f for the forward search, take any feasible potential function for the reverse search, and then create new potential functions. Pf of u is equal to half the difference of the forward and backward potential, and the reverse potential Pr of u is just equal to minus the potential for the forward search. If we pick such potentials, then the sum of Pf of u and Pr of u will be equal for any u, so this will be constant. And the only thing that we need to prove is that these potentials are both feasible. The forward one is feasible for the forward direction, and the reverse one is feasible for the backwards direction. We will prove this for the forward direction, and for the reverse direction it is just symmetric. So lemma states that if pi f is a feasible potential for forward search and pi r is a feasible potential for the reverse search, then their half difference is a feasible potential for forward search. Let's prove this. First, we know that pi f is a feasible potential, and so for any edge uv, length of this edge minus potential of u plus potential of v is greater or equal to the 0. Also, we know that pi r is a feasible potential for the backward search, and so the length of this edge minus potential of the ending vertex now v plus the pi r of u is also greater or equal than 0. Notice that in the first line we subtract pi f of u and add pi f of v, and in the second line we subtract vice versa pi r of v and we add pi r of u. This is important. So now we can sum up those inequalities and we'll get that 2 length of the edge from u to v minus pi f of u minus pi r of u and plus pi f of v minus pi r of v. All this is greater than or equal to 0. Now if we divide this inequality by 2, we'll get that the length of the edge minus half difference of potentials on u plus half difference of potentials on v is more than or equal to 0. And this means that the potential, which is pf, which is half the difference between pi f and pi r, is a feasible potential indeed. Now that we've proven our lemma, we have a very useful tool. If we have some kind of graphs with additional information for which we have good potential function, we can first take the graph with its regular potential function, then we can reverse the graph, take the potential function for the reverse graph, and then we can combine those two potentials into new potentials, which lead to equal edge weights under both forward and backward search. And it allows us to launch bidirectional A-star algorithm as bidirectional Dijkstra with potentials algorithm, and it will be the best of both worlds. It will be both bidirectional and directed search, and so it will work probably faster than both just bidirectional Dijkstra and just A-star based on regular Dijkstra's algorithm. The question which is left is where to get those potentials, and in the next videos we will discuss some of the examples of where we can get good potentials from. Hi! In the previous videos we've introduced a new algorithm called A-star, and we even created its bidirectional version, but this all was somewhat abstract, because to implement this algorithm in practice we need some potential function, and we don't know yet where to get that potential function so that it is feasible and good enough. So first we will prove a lemma. Remember, we were talking about lower bounds. We were talking that most of the time potential function of a vertex is a lower bound on the distance between this vertex and the target. So now we'll prove that actually if potential function is feasible and the potential of the target vertex is less than or equal to 0, then this potential function is indeed a lower bound on the distance between the current vertex and the target vertex for any vertex v. To prove that, we should know that first L pi of xy is non-negative for any xy if pi is feasible by definition of feasibility. And so also L pi of any path p, the length of any path in the new graph, is also non-negative. Then we take any shortest path between v and t and call it p. And then we know that 0 is less than or equal to the length of this path, because the length of each path in the new graph is non-negative. And this length of the path in the new graph is equal to the length of the path in the initial graph minus the potential of the vertex v plus the potential of the target vertex. But now we remember that the potential of the target vertex is non-positive. So this is less than or equal to length of the path in the initial graph minus potential of vertex v. And we know that this final expression is bigger than or equal to 0, which means in turn that the potential of v is less than or equal to the length of the path in the initial graph, which is the shortest path between v and t, so it is equal to the distance from v to t. So we've proven our lemma. Now it's time to introduce at least one specific potential. And we'll start with the one we already discussed several times. We'll just prove that this is really a good feasible potential. So we consider a road network on a plane map where any vertex has its coordinates x and y. Then the potential given by Euclidean distance, and the Euclidean distance between 2 points is basically the length of a line segment connecting those 2 points, is given by the formula pi of v is equal to Euclidean distance from v to the target, which is in turn equal to the square root of the sum of squares of differences of the coordinates of v and the target. So we state that this potential is feasible and that the potential of the target vertex is 0. And if we prove this lemma, this in turn means, given the previous lemma, that this potential is always a lower bound on the actual distance in this rod network from v to the target. But this is also obvious in itself, because this potential is equal to the straight line segment length between v and the target. And of course, no path in the rod network can be shorter than the length of the straight line segment between the current vertex and the target vertex. So our previous lemma makes sense in this case. Now let's prove that this is a good potential. So we know that for any edge uv, the length of this edge is greater than or equal to the Euclidean potential, to the Euclidean distance between these two nodes, because segment is the shortest path between 2 points in a plane. Now we see that the potential of any node u is equal by definition to the Euclidean distance between this node u and the target node, and then we can use the triangle inequality for the Euclidean distance to state that the Euclidean distance between u and t is less than or equal to the distance between u and v plus the distance between v and t. Now we know that the Euclidean distance between u and v is less than or equal to the length of the edge between u and v, and the Euclidean distance between v and t is exactly equal to the potential of v. So we see that pi of u is less than or equal to L of uv plus pi of v. And we can rewrite this as L of uv minus pi of u plus pi of v is non-negative. And this is, by definition, the length of the edge in the new graph with new edge weights. And we see that all the edge weights in the new graph are non-negative. And that's why the potential pi is really feasible. And also it's obvious that the potential of the target vertex is 0, because it's basically the distance from the target vertex to itself, and it is equal to 0. So to implement an actual specific A-star algorithm on a plane map, we need to find the shortest path from source vertex to the target vertex. So for each node v, we can compute, either pre-compute or compute on the fly, the potential, which is equal to the Euclidean distance from v to t. To do that, we just need the coordinates of v and coordinates of t, and this computation works in constant time. And then we just launch Dijkstra's algorithm with potentials pi of v, and this will be our A-star. And even with the Euclidean distance potential, this will work faster than the regular Dijkstra's algorithm, and you will see that in one of the problems of this project. Hi, in this video we will consider another better way to find a good potential function for A-star. It will be based on landmarks. So first, a lemma. Let's fix some vertex A, and we will call this vertex a landmark. Then we choose the potential function pi of v equal to distance from this landmark to the target minus distance from this landmark to the node v. And by distance, I mean the distance in the graph we're looking at. So we can, of course, not know this distance beforehand, because to find this distance, we need to launch some shortest path algorithm. But let's suppose we know the distance from the landmark to all other vertices beforehand. Then we can use such potential. And I state that this potential is feasible and that the value of this potential on the target vertex is 0. So let's prove this lemma. First, we write the length of the edge with this potential by definition, and then we rewrite it as length of the initial edge minus distance from landmark to the target plus distance from landmark to distance u, then plus distance from the landmark to the target. And so this cancels out with the minus distance from the landmark to the target, and minus distance from the landmark to node v. And this is in turn equal to distance from landmark to u plus length of the edge from U to V minus distance from the landmark to V. And now this is non-negative due to triangle inequality, because distance from A to V cannot be bigger than distance from A to U plus length of the edge connecting U to V. So we just proven that the edge weight for any U and V in the new graph is non-negative, so the potential we provide is indeed feasible. And also the value of this potential on the target vertex is just a difference of d from A to T with d from A to T, which is 0. So this is a feasible potential with 0 value on the target, and so this is actually a lower bound for any node V on the distance from V to the target. So what can we do with this? We can select several landmarks, which are basically any vertices of the graph. So we can select them any way we want, and we can optimize how good we select those landmarks, and hopefully our algorithm will become better because of that. So we select those landmarks, maybe 10 landmarks for example, and we pre-compute the distances from those landmarks to all other vertices. So to do that, we'll need to launch something like this Dijkstra algorithm, which will find the distances from one node to all the others. We cannot really save anything on this one because we need distances to all other vertices. So bidirectional search or A star won't help us here. We will need to find distance to all the other vertices, and we will need to scan the whole graph. But this can be done on the pre-computation stage. And then for any landmark A, we have the following inequalities. The distance from any vertex V to the target is greater than or equal to distance from A to the target minus distance from A to V due to triangle inequality. And also, due to another triangle inequality, we have another lower bound that distance from V to T is greater than or equal to distance from V to the landmark minus distance from target to the landmark. We can use both if we can pre-compute the distances not only from landmarks to all the other nodes, but also to landmarks from all other nodes. But to do that, we just need to reverse the graph and run Dijkstra algorithm from landmarks, from each of the landmarks again. And now we can use the tightest lower bound out of all those lower bounds for each node V. So we take maximum over all landmarks A that we selected of both differences. And this will be the tightest lower bound we have. And this will still be feasible potential. We can show that. And you know that the tighter the bounds, the better the algorithm works, the faster your A star search will find the target vertex. So by choosing the landmarks wisely and maximizing the lower bounds over them, we can speed up our A star search a lot. And now let's think, how should we select the landmarks? The intuition is that a good landmark appears either before the starting vertex or after the target vertex, and then the lower bound induced by this landmark will actually improve something. And this is if we fix the source vertex V and the target vertex W, then good landmark is the one which is either before V or after W. But we need to select a set of landmarks that will work best for any query. So for any query from source to target, we need some landmarks which are before S and some landmarks which are after T. And so it makes, for example, to choose the landmarks on the border of our map. For example, here on a map of US, we have landmarks in the rectangles which are red and yellow. And in this particular search, in the middle, from green area to blue area, we used the four yellow landmarks, meaning that only the lower bounds from those four landmarks actually improved our search in some way. And this just supports the idea that the landmarks should be before starting point and after the ending point in some sense. And here is another example of A star with landmarks. And again, red and yellow rectangles are landmarks. And again, yellow rectangles are those landmarks which were used in this search. And you see that how much less vertices do we really visit with an A star search, which is, by the way, also bidirectional A star search, than with the regular bidirectional search. Because in the regular bidirectional search, we had those fat circles surrounding each of the source and target rectangles. And here we have only small tiny streams of scanned vertices colored in green and blue. So this set of only something like 20 landmarks significantly reduces each sequential search, but with the cost of pre-processing. So to do fast, we need to pre-process our graph and to compute distances from 20 vertices to all other vertices in the graph. So either we have a separate time to pre-process our graph and save the results, or this is only applicable if we know that we'll get a lot of queries in our problem. So if we get just one query, it's faster to find the shortest path from source to target directly without first trying to find the shortest path from 20 vertices to all other vertices in the graph. But if we have 1000 queries to find the shortest path, then already pre-computing for 20 landmarks can be beneficial, because it will only take us 20 searches from those landmarks, and then each of the subsequent 1000 searches which were given as queries will be significantly faster. And in the problems of this project, in the programming assignment, you will have both problems where you need just to compute the results for queries, and you will have problems where you will have a separate time to pre-process your graph as you want, and then you will answer the queries. And there we will offer you another algorithm in the next lesson, which works really well for huge rod networks. But you could also try, instead of or in addition to implementing that algorithm, to also implement this A star with landmarks algorithm. And you can try different ideas on landmark selection. And it is known that really a very good choice of landmarks can lead to very fast algorithms for subsequent queries on the shortest paths. So in conclusion, we've introduced A star algorithm, which is basically a direct search, and direct search can scan fewer vertices and a lot fewer actually, as you just saw on the pictures. And A star is a direct search algorithm based on Dijkstra and potential functions. And we can also make A star bidirectional to make it the best of both worlds, both a bidirectional Dijkstra and a Dijkstra with potentials. The Euclidean distance is one example of a potential for a rod network on a plane. And we can also use landmarks to create a good potential function. And if we create several landmarks and we choose them wisely, so that there are landmarks before and after source and target vertex for any source and target vertex, then this can speed up our algorithm even more significantly. Hi! In this last lesson of the Advanced Shortest Paths module, we will study the contraction hierarchies algorithm. In the previous lessons, we've learned the idea of bidirectional search, and we've studied the bidirectional Dijkstra's algorithm, which can be thousands of times faster when applied to social network graphs. However, for rod networks, it typically gives just roughly 2x speedup. And in this lecture, we will study an algorithm that gives much better speedup, thousands of times and more. And the idea for such speedup is the following. Long-distance trips go mostly through highways. For example, if you consider this long trip by car from San Francisco to New York, and if you look at the navigational directions, then you will see that basically you need to first merge into a highway, then you need to merge from that highway into even a bigger interstate highway, go through it, then exit to a smaller highway, and then exit to a street, and then get to your address. And this is the general case. When you need to get from some point A to point B, you need to first merge from streets to a highway, then merge from there into an even bigger highway, and repeat that maybe several times, and then start exiting. You exit to a smaller highway, then to an even smaller highway, and then exit to a street, and then go to your address. And so less important roads merge into more important roads. And there is some kind of hierarchy of those roads, which is obvious to humans, but we don't know that hierarchy when we're given a graph. So the idea is to use this structure of the shortest paths in the real road networks, and this will allow us to actually avoid scanning many small roads, many not important vertices in the graph, because if you go from San Francisco to New York, then most probably you don't need to go through small streets somewhere in Las Vegas or Chicago. Most of the way you'll be going through a big highway, and you won't go into small streets in the middle of your trip. And there are algorithms which are based on this idea: highway hierarchies and transit node routing by Sanders and Schultes. And transit node routing is one of the fastest known algorithms for shortest paths in real road networks. They can be millions of times faster than the classical Dijkstra algorithm. But those algorithms are pretty complex. And in this lecture, we will study the construction hierarchies algorithm, which is at least thousands of times and more faster than Dijkstra, but it is pretty simple, and you will be able to implement it as part of the project of this module. And you will be even able to play with it and implement different your own ideas and heuristics to improve it even further. So the idea of the construction hierarchies algorithm is to order the nodes by importance. Instead of ordering the highways by their importance, we order the nodes. And the idea is that the importance of the nodes on your shortest path should first increase and then decrease back. And for example, these could be points where a highway merges into another highway, and you can't really get away without passing through this node. And then, if this is true, that the importance first increases and then decreases back, we can use bidirectional search from source to the most important node on our shortest path. This is a forward search. And then from the target to the most important node on our shortest path. This is a backward search. And then when they meet in the common middle point, which has the biggest importance on the path, then we have the path between source and the target. So the idea is about which nodes are important, which are not. First, many shortest paths involve important nodes. If you look at this map of the US, you will see that there are many big roads coming out from big cities, and that's no coincidence. And as most of the shortest paths, which are long distance, go through these big roads, they also go through these big cities. So big cities are important nodes, and many shortest paths go through those important nodes. Another idea is that the important nodes are somewhat spread around, because in each region of the map you have some big city, some capital of the state, or some biggest city in the state, which is important node, such that many shortest paths again go through it. You can't just have one single important node and everything else is unimportant. You always have them spread out through all the map. And another thing is that important nodes are sometimes completely unavoidable. For example, for many different source points in San Francisco on the left shore, and for many target points in Oakland on the right shore, there is no other way to get from the source to this target via some shortest path and bypass this treasure island in between. And so this treasure island node is very important because you cannot just avoid it with the shortest path. And the construction hierarchies algorithm uses this scheme of shortest paths with preprocessing, when you don't just get a graph and then instantly start to answer queries, how long does it take to get from A to B? No, instead, you first get the graph and you get some time to preprocess it. It can be a long process, it can take a few hours or even days, but then when you're ready and you've saved the results of your preprocessing, you can answer the queries for distance and shortest paths much faster. And you work with this preprocessed graph to do that. And this is a very practical case. For example, in Google Maps or in Yandex Maps, that's what people do. They first preprocess the graph, and then they push the preprocessed graph and the algorithm into production, and then they can answer your queries millions of times faster without you noticing it. And it doesn't matter that we have to spend a few hours or a few days before pushing the graph into production, because it happens behind the scenes. And so the general schema is you preprocess the graph, then you implement a special algorithm to find distance and shortest path in this preprocessed graph, and then you reconstruct the shortest path in the initial graph and show it to the user somehow. In the next videos, we will first study how the preprocessing works for the construction hierarchies. Then we'll study how to implement the distance and shortest path queries. We'll prove the correctness of the overall algorithm, and we will point out some very important optimizations of this algorithm. And in the end, we will understand how we can actually measure the importance of the nodes that this algorithm uses and how to implement this importance in your algorithm. Hi! In this video, we will study the preprocessing phase for the construction hierarchies algorithm. So the general idea is that we will be eliminating nodes of the initial graph one by one in some order. When we eliminate the node, some of the shortest paths that existed in the initial graph can be gone because they were passing through this node. And in this case, we will need to add some shortcuts so that we preserve the distances, so that the distances between any two nodes that are still in the graph are the same that the distances between these nodes in the initial graph. So we'll add some shortcuts, some new edges to the graph. And in the end, we will get the augmented graph, which has the same set of vertices as the initial graph. It also has all the edges of the initial graph, but apart from them, it also has all the added shortcuts as edges. This is the augmented graph, basically the graph with augmented set of edges. And also, we will output the order of the nodes that we used in this preprocessing. So this is the general scheme. Now, how does the node contraction work? So let's look at this very simple line graph, all nodes in one chain. The nodes are numbered, and they're numbered already in the order in which we are going to contract the nodes in this example. And let's look what happens when we contract the node. So first we contract node number 1, it goes down, means that we contracted it, and actually what's on the top line is the graph which is contracted. And the node is in green because it's already added into the augmented graph. And you see that there was a path from node 6 to node 4 which went through node 1. When we contracted it, it's no longer in the graph, so there is no path from 6 to 4 in this graph. And then we need to reconstruct that path, and so we add a new edge between 6 and 4, which is colored in blue on the picture. And the length of this edge should be equal to the length of the path between 6 and 4, which went through 1, because that was the only path, so it was the shortest path between 6 and 4. So we add a new edge of length 5, because the length of the shortest path between 6 and 4 was 5, and now after adding this edge it is again 5. And all the shortest paths, all the distances between the nodes which are still in the graph on the top, they are preserved. Now what happens when we contract node 2? Well, nothing really happens because no shortest paths between the nodes which are left in the graph went through the node 2. So it's an interesting case. Now let's contract node 3. And again, there was a shortest path between 4 and 5 going through node 3, and it had length 3. So we add a new blue edge of length 3 directly between nodes 4 and 5. When we contract then node 4, it is the most interesting node because it already has 2 blue nodes, but nevertheless, when we contract it, we remove the path between node 6 and 5, which went through 4 through 2 blue edges, and we need to reconstruct that path. So we add a new edge directly between nodes 6 and 5 of length 8, because the path was of length 8. And notice that in the initial graph there was a path from 6 to 5 which went 6 to 1 to 4 to 3 to 5, and the total length was 3 to plus 2 plus 1 plus 2, which is 8. And now we just added one edge of length 8 between 6 and 5. And in the end we contract node 5. Nothing changes because no shortest paths between other vertices, which are still in the graph, which is basically only node 6, went through node 5, and we don't need to contract node 6 because it's the last node in the graph. And you see that the nodes in the new picture are at different heights, and this just symbolizes that the higher is the node, the later it was contracted, and the higher the node, the more important it is. So we first contract or remove the least important nodes, and the nodes which are left in the end are the most important nodes, and we draw them from bottom to top in the order of increasing importance. Now let's see what happens in general when we contract node V. So there can be some edges incoming into V from some nodes U1, U2, and maybe some others. There can be some edges outgoing from V, for example, to nodes W and W2, and maybe some others. Also, there can be some undirected edges connected to V, and then there will be both an incoming edge from the other end to V and an outgoing edge from V to the other end of this edge. And also, there could be directed edges from the same node to V and from V to this node. So some node can be both in the bottom part of the example and in the top part of the example. But that doesn't really matter much, and we will discuss everything on this particular example. So what happens if V is contracted? Then V will be deleted, and the edges from U1 to V and from V to W1 will also be deleted. And let's suppose that this path from U1 to W1 of length 2, 1 plus 1, was shortest in the initial graph. Then we will need to add a new edge directly from U1 to W1 so that we preserve the distances. So what will be the length of this edge? And the length of this edge will be of course 2, because the length of the new edge must be equal to the length of the corresponding incoming edge plus the length of the corresponding outgoing edge. And for every pair of edges, U1 to V, V to W1, or U2 to V and V to W2, or U1 to V and V to W2, for each such pair we need to add a new edge with a shortcut. But we don't have to add shortcuts always. So let's consider this another example with nodes U2 and W2. There is this path from U2 to W2 going through V of length 5, 3 plus 2. However, it could happen so that there is another path from U2 to W2 which doesn't go through V and has a length of just 3. Then it is shorter than the path going through V. And then if we delete node V, the shortest path from U2 to W2 doesn't change because it doesn't go through V. And so in this case we don't have to add a shortcut. And in practice we don't want to add a shortcut when we can avoid that, because when we add a shortcut, we increase the number of edges in the preprocessed augmented graph, and then our queries will work slow. Less edges, faster queries. So we really want to avoid adding shortcuts, and we need to find such paths, and such paths which don't go through the contracted node and are shorter than the corresponding path going through the contracted node. They are called witness paths because they are witnesses that we actually don't need to add a shortcut. And in the next video we will discuss how to efficiently search for those witness paths so that we don't have to add shortcuts in the preprocessing phase. Hi! In this video we will learn how to find those witness paths that we need from the previous video. So just to remind you, when we contract node V, then for any pair of incoming edge from some node U to node V and outgoing edge from V to some node W, we want to check whether there is some witness path from U to W which doesn't go through V and has length at most equal to the sum of those length of two edges. If there is such path, then there is no need to add a shortcut from u to w after contracting v, because the shortest path between u and w will stay the same even if we don't add this shortcut. And search for such witness path is called a witness search. So first, a few definitions. Let's call a node u a predecessor of v if there is an edge from u to v, either directed or undirected. And also let's call w a successor of v if there is an edge from v to w, again either directed from v to w or undirected. Now, witness search is actually very straightforward. So we need to check for each predecessor of v and for each successor of v whether there is a witness path between this predecessor and this successor that doesn't go through v and that has a length which is smaller or equal to the length of the incoming edge plus the length of the outgoing edge. So for example, in this picture, for u1 and w1 we need to find some path, and it is drawn to the left, which doesn't go through v and has length at most 1 plus 1, which is 2. And also for pair u1 w2 we need to find also a path which is drawn to the right under v, which doesn't go through v again and which has length equal to or smaller than 3, 1 plus 2. To do that, for each predecessor ui of v, we just run Dijkstra's algorithm, regular Dijkstra's algorithm from that ui, and in that Dijkstra's algorithm we always ignore node v, so we don't add it to the queue, we don't extract it from the queue, because we want only the paths that don't go through node v. So this is essential for good query performance, because again, if we don't do this witness search, we don't find the witness paths, then we will have to add shortcuts for every pair of neighbors of v, for every predecessor and every successor. And this will add a lot of new nodes in our augmented graph. And in a graph with a lot of edges, it's very hard to find shortest paths. It will take a long time. So it is essential for us to find as many witness paths as we can and don't add the corresponding shortcuts. But we also want the preprocessing to work pretty fast, and so we want to optimize this witness search. So there are two ideas for optimization. First is we can stop Dijkstra's algorithm when the distance from the source becomes too big. Basically, if we search starting from some predecessor, and the distance from this predecessor to the node currently extracted is very big, then it cannot be a witness path, because it cannot be already shorter than the sum of the incoming and outgoing edge. And this is one idea, we'll discuss it in detail in a minute. And also another idea, we can limit the number of hops. So we can only allow the Dijkstra's algorithm starting from some predecessor to go through at most, let's say, 5 edges. If it cannot find a path to some successor, we just say that there is no such path and we add a shortcut. Of course, we won't find all the witness paths this way, but we will do it fast, and this is a trade-off between the number of edges, shortcuts added in the augmented graph, and the speed of the preprocessing. So first with stopping Dijkstra. So in this example, if we found in our Dijkstra running from the node ui some node x, to which the shortest path is of length 4, then it is already useless, because this length 4 is more than the maximum sum of incoming edge into v plus outgoing edge from v. So it's 4 is more than 1 plus 2, which is 3, and so there is no way there can be some witness path going through x to either w1 or w2, because it will be already longer than 4, and so it will be longer than the path from ui to the corresponding w through v. So in general, if when we extract node x, extract min from the queue, the distance from the source to this x is already bigger than the sum of the maximum incoming edge and the maximum outgoing edge, there is no witness path going through x, and so there is no point to exploring further from X. We can just stop the algorithm here, because all the nodes which will be extracted further in the Dijkstra's algorithm will be even further than X by the property of the general classic Dijkstra's algorithm. And so basically what it means is that we can limit the distance by the sum of two edges, the maximum sum of two edges, and as soon as Dijkstra finds node which is further from the source, we just stop the Dijkstra's algorithm. There is another small improvement, but it can be actually significant in practice. Consider any predecessor W prime of any successor W of V. So for example, there can be an edge from W prime to W2 of length 1. And then let's see. For example, we found some path from UI as the source of Dijkstra's algorithm to W prime. And that path has length just 1. Then we already know that there is a witness path between UI and W2, because the path from UI to W2 through V has length 3. And now the path from UI to W2 through W prime has length at most 2, because there is a path from UI to W prime of length 1, we go through it, and then go through edge of length 1, and we get a path of length just 2, which is shorter than the path through V. So this is indeed a witness path. So using this idea, we can just go up to nodes which are previous to last, which are predecessors of our successors of V, and then stop there. So basically what it means is that we limit our distance by the difference of the sum of the two longest incoming and outgoing edges minus the length of the last edge on the path from some predecessor to some successor of V. And then there are two criteria during the Dijkstra's algorithm. If we found some W prime which is connected directly to some successor of V, and the distance to W prime plus the length of this edge is smaller than the corresponding path from the source to the corresponding successor, then we've just found a witness path. And if the distance to some node is already bigger than this maximum of maximums in the bottom of the slide, we just stop the Dijkstra's algorithm, because we cannot already find a witness path, because all the nodes are already too far. Another idea for optimizing the witness search is to limit the number of hops in Dijkstra. And by hop, I mean just a jump through an edge. So we consider basically only shortest paths from the source, from some predecessor of V, which contain at most k edges. As soon as our Dijkstra's algorithm considers a node which is at least k plus 1 edges from the source, we don't actually process this node, we ignore it. And if a witness path is not found using this Dijkstra's algorithm, we just consider it as if there is no witness path, and we add a shortcut in the preprocessing phase. And so this is a trade-off between preprocessing time and the size of the augmented graph. If k is small, then we won't find many witness paths, and then we will add many shortcuts. But our preprocessing will be faster. And in practice, you can change k gradually from the start to the end, and typically k is small in the start, for example k equals 1, and then in the end k equals to 5, and this can be based on the degree of the vertices that you're contracting. So these are the ideas for speeding up the witness search, and this is all for preprocessing. So in the next video we'll study how to actually do the queries in the preprocessed graph after we preprocess it by contracting the nodes and adding the shortcuts. Hi! In this video we'll study how to actually find the distance between nodes in the augmented graph after preprocessing it using contraction of the nodes. So the main idea is that we will use bidirectional Dijkstra, and this bidirectional Dijkstra will only use some of the edges of the augmented graph. So you remember that when we contracted the nodes, we placed them from bottom to top in the order of increasing importance and also in the order of contraction. So the later the node was contracted, the more important is this node. And so we draw this arrow with node order from bottom to top. And we'll consider only the upwards edges. So, for example, if we need to find the shortest path between node 2 and node 3 in this graph, the path will look like this. It will go first by edges which go up to some node with the biggest importance. For example, in this case it will be node 6. And then we will go by edges down from that node 6 into node 3. And to find such path, we will use bidirectional Dijkstra, which will start both from 2 and from 3. And from 2 it will go by forward edges which go up. And from 3 it will go by backwards edges which also go up. And then they will meet at some node and we will find some path which goes first up and then goes down. This is the general idea, but it is somewhat different still from the classical bidirectional Dijkstra's variant. So in the bidirectional Dijkstra, as soon as we find some node that is processed both by the forward search and the backward search, we stop and compute the shortest distance. In this case, we don't stop when some node was processed by both searches. We stop only when the extracted node is already farther than our current estimate of the distance to the target. This is the pseudocode for the function compute distance, which takes as inputs source node S and target node T and returns the distance between them. Of course, it also takes as input, for example, the graph and the reverse graph for the bidirectional search, but I just omitted those details. Note, however, that you only need to store in the graph the edges which go upwards. So we have a node A and node B and an edge from A to B. If A was contracted earlier than B, then you need to store this edge. But if B was contracted earlier than A, then this edge goes downwards. And so you don't need to store this edge. You can just delete it because it won't be used at all in the queries. And so you don't need to store it in the preprocessed, in the augmented graph at all. So we start with the initializing variable estimate, which will store our current estimate of the distance between the source and the target. And we initialize it with plus infinity because currently we don't know of any path between source and target. Then we do the standard initialization of the bidirectional Dijkstra. We fill the arrays with distance estimates for the forward search and the backward search with plus infinities. And we also set the distance in the forward search from the source to 0 and the distance in the backward search from the target also to 0. And we also have the lists of the processed nodes for the forward and the backward searches. Then we'll have the main loop. And this loop goes while we still have some nodes to process, either in the forward Dijkstra or in the backward Dijkstra. Which means that basically in our priority queue that we use for the Dijkstra algorithm, there still are some nodes, either in the queue for the forward Dijkstra search or in the queue for the backward Dijkstra search. While there are still such nodes, we try to extract a node in the forward search if there is still something in the queue for the forward search. And this node will already have the distance estimate which is equal to the distance from source S to this node V. So if the distance from S to V is already bigger than the estimate of the distance from S to T, we don't need to process node V, and we don't need to put it in the queue and to process the nodes which are the successors of V. So we only do that if the distance estimate of V is smaller or equal to the current estimate. Then we process, basically we do the same we do in the regular Dijkstra step, and then we need to also update our estimate. So if V is processed in the reverse search, we check that by if V in proc R, then it is processed in both searches because V has just been processed in the forward search and it is also in the list of processed nodes in the backward search. So it is processed by both forward and backward searches. This means that its distance estimates both in the forward and in the backward search, are already equal to the corresponding distances from S to V and from V to T. And so we know the length of the shortest path going from S to T through V. This path has length equal to dist of V plus dist R of V. If this length is smaller than our current estimate of the distance between S and T, we need to update it. And that's what we do in this if statement. And then we try to do the backward Dijkstra search, and it is completely symmetric to what we have here for the forward Dijkstra search, so I don't write the code for that. And this while loop goes and goes until all the nodes in all the queues for forward and backward search are processed, and then in the end we just return our current estimate of the distance between source and the target. Now it seems that we already know everything. We know how to preprocess the graph using the construction of the nodes. We also know how to implement queries using bidirectional Dijkstra. So are we done? Can we actually go and implement this algorithm? Well, of course we're not done, because for example, we don't know yet whether this algorithm works correctly or not. So compute distance procedure returns some estimate of the distance between source and the target, but is it always correct estimate? Is it always equal to the distance between S and T in the initial graph or not? We don't know that yet. Also, this compute distance procedure only returns us the estimate of the distance between source and the target, but it doesn't return the actual shortest path between source and the target in the initial graph. But that's more of a technical moment. Using the standard bidirectional Dijkstra algorithm, we can reconstruct the path in the augmented graph between source and target using the special array with the previous node in the shortest path from source to this node, and the same for the backward search. And then some of the edges could be shortcuts instead of the edges of the initial graph. But then when we do the preprocessing, we should also store in the shortcut not just the edge, but also which two edges were there before we added this shortcut. And then we can recursively take the shortcut and replace it with the two edges that were before this shortcut. And then if some of those two edges are also shortcuts, we recursively get the edges that were there before these shortcuts were added, and so on. And then we will eventually reconstruct the path in the initial graph, which only contains the edges of the initial graph. And in the next video, we will actually prove that this algorithm works correctly, that the estimate from the compute distance procedure will always return the correct distance between source and the target. Hi! In this video, we will prove that the algorithm suggested in the previous video for finding the distance between two nodes in the augmented graph always returns correct result. First, let's formally define the augmented graph. So, augmented graph G+ has the same set of nodes V and has the augmented set of edges E+, which contains all the initial edges E of the graph G, along with all the shortcuts added at the preprocessing stage. And the lemma states that the distance d+ of st between any two nodes s and t in the augmented graph is equal to the distance between the same nodes in the initial graph. And note that this makes sense, because actually the only thing we are doing is we are adding shortcuts, and those shortcuts are not shorter than the path which was initially between those two nodes. It just has the same length as the path through the contracted node V in the initial graph. So always when we add the shortcut, we don't do anything with the path. But more formally, first thing to note is that edges are only added to G, so if there was some shortest path between S and T in G, it will also be present in G+. And so distance in the augmented graph is at most distance in the initial graph. But also, if we add some shortcut from U to W, then at that moment there was a path from U to W through V of length of the edge from U to V plus length of the edge from V to W. But this is equal actually to the length of the shortcut added. So there was a path before adding this shortcut from U to W through V. So if there is some shortest path from S to T going through this edge UW in the augmented graph, then in the initial graph there was a path going from S to U, then from U to V, from V to W, and then from W to T, which has the same length. So there is a path of the same length in the initial graph. And so the distance in the augmented graph is the same as the distance in the initial graph. Now let's also define the rank of vertex, which is the position of this vertex in the node order returned by the preprocessing stage. So basically it's the importance of the node. So if our node was contracted first, it has rank 1. If it was contracted last, it has rank n, where n is the number of nodes. And the higher the rank, the more important is the node, and the later it was contracted. Also, let's denote increasing and decreasing path in the augmented graph. So a path is increasing if the ranks of the nodes of this path in order increase. And also it is decreasing, again, if the ranks of the nodes in this path decrease. And what we want to say is this lemma, that for any source and target, there is a shortest path in the augmented graph, which is first increasing and then decreasing. So it contains two halves. And the first half is a path which is increasing. The second half is a path which is decreasing. And those two halves meet in some node V. This is a justification of our bidirectional search, which goes only through edges which are going upwards. So the forward search goes through edges upwards to V, and the backward search goes from target through backward edges which go upwards also to V. And then they meet. And if we prove that there is always a shortest path of this form, then our algorithm from the previous video works correctly. Now let's prove it. But first, let's look at this proof of the idea. So again, we draw here nodes such that nodes in the bottom are less important than the nodes in the top. And want to prove that for any source S and any target T, there is a path of this form when it first goes up and then goes down. But what if that's not the case? What if there is some shortest path, but it's not always going first up then down? And then there is some node, UK, for which it goes first down then again up. And so both its neighbors are higher. Then let's consider the moment when this node UK was contracted. Both its neighbors are higher, so they were contracted later than UK. And so when UK was contracted, both those nodes were in the graph. And those are neighbors of UK. So when it was contracted, two cases. First, there was a new shortcut added in blue. Then what we can do is we can remove UK from this shortest path and then just use the blue edge instead of it. The length will stay the same because the length of the shortcut is equal to the length from UK-1 to UK and then from UK to UK+1. And there is no more problem with this node UK, which is smaller than both neighbors. The second case is that no shortcut was added, but then a witness path was found. And this is drawn in green. But then all the nodes in the witness path were present when node UK was contracted. So they were contracted later. So they're actually higher than node UK. So when we remove UK again, we can replace it with the witness path and we'll remove our problem with UK. This doesn't prove yet the general case because there still can be some other places where this going first up then down is violated. So now let's prove formally. So assume for the sake of contradiction that no such path from source to target which first goes up and then goes down exists. Then for any shortest path from S to T, there is some node UI of this path such that its rank is smaller than the ranks of both neighbors, as in the example. And we call all such nodes local minimums. Then for any shortest path between S and T, denote by M of P the minimum rank of a local minimum of this path. So there can be several local minima on this path, but we denote by M of P the minimum rank of all of those. Let's consider the shortest path P star with the maximum M of P among all the shortest paths between S and T. And then consider the local minimum UK, which has the rank equal to this M of P. And then there are two cases. When we're constructing UK, either there was a shortcut added between UK minus 1 and UK plus 1. Then there is a shortest path with this shortcut instead of the current path from UK minus 1 to UK plus 1. And this shortest path P prime doesn't contain UK. And UK has the minimum rank of all the local minima in the path P star. So M of P prime is strictly bigger than M of P star. And this is a contradiction with the choice of P star, which has the maximum M of P of all the shortest paths. In another case, when we were constructing UK, there was a witness path from UK minus 1 to UK plus 1. And it was comprised of nodes which have a rank higher than rank of UK, because they were constructed after UK. And so there is another shortest path, P double prime, with this witness path instead of the path UK minus 1, UK plus 1. And again, M of this PW prime is strictly bigger than M of P star, which is again a contradiction with the choice of P star. So now we have a pre-processing via node construction. We have an algorithm for querying via bidirectional Dijkstra in the augmented graph. And we have proven that this algorithm always works correctly. So are we done now? Well, turns out we're not done yet, because the question is how to select the node order. Our algorithm so far doesn't specify how does it order the nodes for construction. And it turns out that the ordering of the nodes influences the preprocessing time and the query time very significantly. And so in the next video we will finally discuss how to order nodes in such a way that both preprocessing and query work fast. Hi! In this video you will learn how to construct a good node ordering for the construction hierarchies algorithm. So far, if you think about it, our algorithm works correctly for any node ordering. If you just choose any order and pass it to the processing procedure, it will construct the nodes in this particular order and return an augmented graph. If you then run queries on this augmented graph using the bidirectional Dijkstra approach from the previous videos, everything will work correctly, because the correctness proof doesn't depend on any particular order. However, this order will influence the order of operations in the bidirectional Dijkstra algorithm for the queries, and actually it will heavily influence the time required for queries and for preprocessing. So we want to choose a good node ordering so that our preprocessing and our queries are really fast. First thing we want from the order is we want to minimize the number of added shortcuts, because each time you add a shortcut you add an edge to the augmented graph in the end, and the more edges the slower your Dijkstra algorithm will work. So we want less shortcuts. Second, you want to spread the important nodes across the map, because from the common sense it follows that there are important big cities in every sufficiently large region of the country, of the map, and then in each state, if you divide it into sub-regions, there are still relatively big cities which are important nodes, and so on. And this should work well in practice. And third, you also want to minimize somehow the number of edges in the shortest paths in general in the augmented graph. So basically you want to make your graph look less like a road network graph and more like a social network graph, where bidirectional Dijkstra algorithm is so much faster than the regular Dijkstra's algorithm. Because any two nodes in a social network are at most 6 edges away, and then bidirectional Dijkstra finds with forward search and backward search in just 3 steps they meet each other. You want the same in the augmented graph, and you can somehow become close to it by adding shortcuts in the right places. So in general you want these 3 things. Now we'll discuss how to do that. So we want to order nodes by some importance. So we need to introduce a measure of importance for that. And then we will at each step construct the least important node. However, when we contract a node, the properties of the nodes which are neighbors of this node can change, and then importance can also change for those nodes after that. So in general, the algorithm will work as following. We will keep all the nodes in a priority queue ordered by importance, so that we can extract the least important nodes very fast. But of course, priority will be something like minus importance, so that the head of the priority queue contains the least important node, not the most important one. Then, on each iteration, we will extract the least important node, and we want to contract this node, but first we need to recompute its importance, because it could have changed because of the contractions of the other nodes. Then, we need to compare its new updated importance with the importances of all the other nodes. And to do that, we will take the head of the priority queue, because we already extracted this node from the priority queue, it's no longer there. So we will compare the importance of this node with the smallest importance of all the nodes which are still in the queue. If the importance of the extracted node is still minimal, then we can safely contract it, it's the least important node. Otherwise, we will need to put it back into the priority queue, so that we can extract a node with even smaller priority from it. Of course, this is only approximate, because at some point we could extract the node, recompute its importance, and then decide that it has really the least importance of all the nodes in the queue. However, there is some other node which is still in the queue, which has smaller importance, but we haven't yet recomputed it, and so we don't know about that, but that's okay. We will try just to order the nodes approximately by this importance. Also, it can seem that this process can go on and on indefinitely, but we will show that it will actually stop after a finite number of iterations always. Why is that? Well, if we don't contract the node, we update its importance and it actually changes. And after that, its importance is corresponding to the current set of nodes which are still not contracted. And after at most number of nodes attempts, all the nodes will have updated importance. And then the node with the minimum updated importance will be contracted after that, because it will be extracted and it will have the smallest importance at that point. And then when we recompute its importance, it will turn out to be the same, because it already has updated importance. And then we will just contract this node. So eventually this kind of iteration always contracts a node. And in practice, it usually takes 1 or 2 iterations usually to actually contract something. So this works typically fast. Now we'll talk about the importance criteria. So first is edge difference. It is related to the number of shortcuts added and minimizing the number of edges in the augmented graph. Second one is number of contracted neighbors, and it is related to spreading the nodes across the map. So if there are already many neighbors of this node which are already contracted, then we will probably contract some node in some other place, because we want to spread important nodes and also spread unimportant nodes. We don't want everything to be clustered in one region. Also, shortcut cover is connected with how important that node is, how unavoidable it is. Do you remember the picture with an island between San Francisco and Oakland, the Treasure Island, which was unavoidable if you go from San Francisco to Oakland, if you want to go with the shortest path? So shortcut cover will somehow approximate how unavoidable a node is. And the last one, the node level, has something to do with the number of edges in the shortest paths in the augmented graph. So now we will go through all of these in detail. So edge difference. Basically we want to minimize the number of edges in the augmented graph. So when we try to contract the node V, we can actually compute how many shortcuts would be added if we actually contract this node. We can also always compute the number of incoming edges and number of outgoing edges of any node. Then we can compute the edge difference, number of shortcuts added minus number of edges deleted, which is the degree of this node. And this is called edge difference. And the number of edges increases by edge difference after contracting V. So this influences both the number of edges in the final graph and also the number of edges in the graph being preprocessed, which is important because influences the preprocessing time. So what we want is to contract nodes with small edge differences first. Contracted neighbors, I already told about this. We want to contract a node with small number of already contracted neighbors so that the nodes which we contract don't cluster in one place, but they are actually spread out in all the regions of the graph. Shortcut cover is very important. Basically, it says how many nodes are there such that we cannot avoid visiting our node if we want to go to those nodes. More formally, if we have some node V, we compute the number of neighbors W of V such that we have to create a shortcut either to W or from W in the case we need to contract V. And this basically means that when we contract V, we lose some shortest path to W, and that's why we need to create an additional shortcut. And so V is important for W. And if V is important for many its neighbors, then it's important. And so we need to first contract nodes with small importance, with small shortcut cover. Node level is an upper bound on the number of edges in the shortest path from any node S to node V in the augmented graph. It can be shown formally that this is an upper bound, but I'll tell you the intuition. So we initialize the level with 0, and then when we contract some node V, we update the level of its neighbors. So for a neighbor U of V, either we could get to U somehow without going through V, and then contracting V doesn't influence its level, or we could go to U through node V. But then to go to node V, we needed at most level of V edges, and then one more to get from V to U. So that's why level of U needs to be maximized by level of V plus 1. So in the end, level of V is an upper bound on the number of edges on the shortest path to V. And so we want to contract nodes with small level, because first we need to contract non-important nodes. In the end, we propose the following importance measure. We just sum up all those 4 values. Note that this is a heuristic value, and you can actually play with weights of those 4 quantities in the importance and see how preprocessing time and query time change. But we think that just summing them up will already work pretty well. However, each of the 4 quantities is necessary for fast preprocessing and queries. If you avoid implementing at least one of them, probably preprocessing or query time will be too long. But then you can further optimize with the coefficients. For example, 2 times added distance plus 3 times contracted neighbors and so on. So it also means that you need to find a way to compute all of these quantities efficiently at any stage of the preprocessing, both in the beginning and also when you need to contract a node, but you have already contracted some other nodes. This is not very hard, and we'll leave this as an exercise to you. So, we did a lot of work. We've come up with a preprocessing stage. We need a particular node ordering with that, and we've come up with a complex importance measure for nodes for that. And also we need to do bidirectional Dijkstra, but not classical bidirectional Dijkstra. We need to do some tweaks in the query stage. So, is it all worth it? It turns out that yes, it is well worth it. If we take, for example, a graph of Europe with 18 million nodes and launch the classical Dijkstra's algorithm on it, and we generate random pairs of vertices in different places of Europe and then compute the shortest distances, and on average it will work for 4.3 seconds. However, if we launch contraction hierarchies on the same graph with the same pairs of vertices and we tweak the heuristics inside the contraction hierarchy as well, it will work on average just for 18 milliseconds, which is almost 25,000 times faster. So it is very well worth it. For example, for a service like Google Maps or Yandex Maps, working 25,000 times faster means that you actually can provide your service to millions of users and do it blazingly fast. And this speed up will only increase if you increase the size of a graph. For example, if you go from the graph of Europe to the graph of the whole world, the speed up will only increase. So now it seems that we know everything. We know how to preprocess by contracted nodes, ordered approximately by their importance, and we have some importance measure for that. We know how to query using bidirectional Dijkstra algorithm. And our importance function is heuristic, but works really well on rod networks graphs. And this algorithm works thousands of times faster than Dijkstra. If you tweak it really well, it can work even tens of thousands times faster, but at least thousands of times faster. This is what is guaranteed for your own implementations. You will try to do that in the programming assignments of this project for this module, and you will see that your solutions are actually much faster than the classical algorithm, and you will need them to work thousands of times faster to actually pass the assignment. And also, we actually encourage you to compete on the forums on whose solutions is the fastest. So you can take the result by the grader and then post it on the forums, and someone can organize the result table with the top results. And it's very interesting how you can come up with your own heuristics for improving this algorithm, because you see there are a lot of heuristics in the last part of this lecture, and you can come up with your own ideas, and maybe they will be so good that you will speed up everyone else's solution 10 times or 100 times. So really try to do that. We will also show you some pointers to where you can get the data for real graphs of the rod networks of some parts of US and the whole US. And in the end, this could become your own open source project, which you could show, for example, to potential employers. So we wish you good luck with the advanced shortest paths.